It's in the morning in Turkey, and today our first keynote speaker is Dr. Kevin Tranberg, and he's from U.S. National Center for Atmospheric Research. Dr. Tranberg received his PhD in meteorology from MIT, and he served as the lead author in 3 previous scientific assessment reports of the Intergovernmental Panel on Climate Change, IPCC, in 1995, 2001, and 2007, and shared the 2007 Nobel Peace Prize, which went to IPCC. He's an expert on climate modeling. He edited a 788-page book titled Climate System Modeling in 1992. And he has published 575 scientific articles, including 67 books or book chapters, and over 286 refereed journal articles. He's among the highest cited environmental scientists. If you are teaching a heat transfer course using Incroper and DeWitt, you may remember the Earth's energy budget figure in chapter 12, which is based on Dr. Tranberg's 1997 work. Today, he will tell us about Earth's energy balance, global warming, and consequences we are observing. The screen is yours, Dr. Tranberg.
Thank you very much. It's dusk here, late evening, and the lighting is a bit peculiar. So anyway, I'm now activating my presentation on the screen. And as was just mentioned, the topic of this talk is about a perspective on climate change from the flow of energy standpoint. The AR6 Working Group 1 report has just been released, and a lot of it was exactly the sort of things that we were talking about back in 2007 in the report that I was very much involved in, except now things are a little bit more unequivocal, a little bit more definite. And what I have been doing is looking at the physical relationships rather than just the statistical relationships of how things come about. And that's what we're going to talk about here today. And so this schematic on the front page here shows the flow of energy from the sun into the earth. And then the outgoing radiation is a lot more uniform. And because of the geometry and the rotation of the earth, the net radiation has a profile with latitude as given on the left here. A lot more radiation is received in the tropics than at high latitudes, and the energy is being lost at high latitudes. And so when we deal with the energy on Earth, from the standpoint of climate change, the issue is the increasing greenhouse gases, in particular carbon dioxide. And so the planet then has to warm up because of the increased trapping of the radiation. And the outgoing long-wave radiation increases, and it does so as the temperature increases until it matches the absorbed solar radiation. But in the real world, there's a lot of feedbacks and complexities. And so a very fundamental measure of what's going on is the energy imbalance. And that accounts for all of the complicated feedbacks. And so this has not been dealt with a great deal in the past, and that's partly because it's been difficult to get a good handle on the observations as to what's going on. But in our 2009 paper, we had a schematic flow of the overall, as a function of the vertical, the flow of energy through the climate system. These are all global mean values. And here I'm only going to focus on a couple of these. One is at the top of the atmosphere, the incoming radiation, the reflected, the difference is about 240. The outgoing is about 239, and the energy imbalance here is 0.9 watts per square meter. And I don't have time to go into all these other things here. And so we've got around about 0.9 watts per square meter, and I'm going to justify that number in much more detail later on. But if you add that up over all of the square meters of the Earth, it comes to 500 terawatts. That's 500 with 12 zeros after it, and it's a tremendous amount of energy. In fact, in 2018, the global electricity generation was 5.7 terawatts, and so it's according to that, it's about a factor of 90 less. This may not be quite right. I just revised that number. But anyway, it suggests that the effects of humans through electricity generation and other activities is quite small compared with this energy imbalance. And it's mainly through this interference with the natural flows of energy that really matters. And so another way of comparing it is this overall flow of about 240 watts through the climate system, watts per square meter. And it's relatively small compared with that. And so you can't go outside and feel the effect of this. And the only way you can feel it is if it accumulates over time. And so I'm going to talk about where it accumulates and where it really matters and what that does in that case. And so from the standpoint of energy, the overall energy imbalance, we're dealing with energy, and global warming is really global heating. One component of that is the increase in temperature at the surface. And the recent IPCC report bases a lot of statements about the global mean surface temperature, whether it's 1.1 degrees Celsius above pre-industrial as it is now, or can we stop by 1.5 or 2 degrees Celsius, or will we get to 3.5 degrees Celsius by the 2200? And that's just an indicator. And so what happens with this extra heat is that it warms the land and the atmosphere. A lot of it goes into the ocean, which expands and raises sea level. A lot of it melts land ice, which puts more water into the ocean, and that raises sea level. And it melts sea ice, which doesn't raise sea level, but the water then gets warmed up. And a really complicating component is that it evaporates surface moisture, which affects the amount of moisture available for rainstorms and cloud, and it can change the reflectivity. So how much gets reflected back to space. But over 90% of it, some 93% of it ends up going into the ocean. Now, if we have extra heat with the human body sweats, we perspire. In other words, water is a key. And for homes, we can use evaporative coolers, swamp coolers, if it's not already moist. And so evaporation works, in other words. And for the planet Earth, it certainly works because 70% of the planet is the ocean. And so in droughts, there's no moisture available, and so evaporation does not work. Another example, if the sun comes out after a shower, then the first thing that happens is that the puddles dry up and then the temperature goes up. And so water plays a key role. This is the global mean surface temperature as estimated by NOAA. 2016 is the warmest year on record. Last year was the second warmest, and maybe the COVID pandemic had something to do with that because of less pollution around. But in general, the warmest years are El Nino years. There's a lot of raggedness in the past, and that's because the record is a bit more incomplete. Prior to 1958, the International Geophysical Year, we don't have observations in Antarctica, for instance. And the pre-industrial level is down here. The zero value is the 20th century value. And then we can put the annual values of carbon dioxide on here. Here's the score over here. The pre-industrial value is about 280. And the 20th century value is, again, the zero value. And we're up to about 415 parts per million by volume. And I put them together this way to suggest that there's a relationship because we can prove that there actually is. And about half of the increase in carbon dioxide has occurred since 1985. And so everyone that's listening here has been a part of this, in fact. Well, if we are looking at the top of the atmosphere radiation, which we've got good measurements from satellites since in March of 2000, this is the record we get, the individual monthly values, and then this is the 12-month running mean value. And I've also put on here the total solar irradiance, which is a relatively small component, so that it's not the changes in the sun which is doing this. Now, the measurements from space are not accurate enough to give us the absolute value. They can't actually give us the Earth's energy imbalance, but they give us assuming the errors are systematic, because there's mainly one instrument in space, and so it's not recording the whole time. And the estimate is from other measurements, which I'll talk about, that the zero value is about 0.7, and that puts these recent values at around 1.2 watts per meter squared. And the reason is because of decreases in low cloud and loss of Arctic sea ice. And so we've got these measurements in place. Now, what about the atmosphere? Well, warmer air can hold more moisture at a rate of 7% per degree Celsius. And with global warming, more heat means it goes into drying as long as moisture is available. And that gives more evaporation, which puts more moisture into the atmosphere. And so in places where it's dry, it just dries things out more if that's possible. Trees wilt, plants wilt, and then the temperature has to go up. And so it increases the risk of fire. And in the cases where more generally the case, the moisture gets caught up in rain systems and it rains harder. And so if we have a parcel of air that's got some moisture in it and it runs up against a mountain and it rises, or it's part of a weather system so that the air goes up and it rises, it expands, and then, whoa, suddenly we get a downburst of rain. And so if we have a thunderstorm like this, the main source of the rain is from the convergence of moisture into the storm from afar. And we know roughly how far that is. The rain area, this is about a factor of 10 times the rain area overall. And as a result, if there's more moisture in the environment, it means that it rains harder. So this is the overall schematic of the flow. You have increasing greenhouse gases going on. There's global warming and global heating. There's surface heating and there's surface evaporation. On the heating side, the temperature increases, which increases the atmospheric temperature and it increases the water holding capacity. And on the other side, if there's moisture available, it actually puts more moisture into the atmosphere. So the combination of these two things mean that there's enhanced precipitation rates. It rains harder or it snows harder. And there's enhanced latent heating in the atmosphere. And this applies to, because all weather systems feed on the available moisture, and it applies to all of these different kinds of weather phenomena, including hurricanes. And so there's enhanced storm intensity as a consequence of this. Now, in the atmosphere, if we look at the total atmospheric energy, this is what it looks like overall. There's a number on here in terms of zettajoules. But if we look at the changes over time down the bottom, and these are actually 12 months running means, the mean is only about 5 terawatts in terms of the heating that's going on, the overall increase here. But the variability is quite large from month to month and from year to year. And a lot of that is because of El Nino events. And so this is the actual time series of what's going on in terms of the heat content of the atmosphere, which includes the moisture content through latent heat. And here, this is a La Nina event. This is an El Nino event, another El Nino event here. And so the heat content of the atmosphere and the temperature of the atmosphere goes up. That's why 2016 is the warmest year on record from the standpoint of the global mean surface temperature. Now, another place that the heat accumulates is in ice melting. And so we have things like this around the world, and Arctic sea ice is going down steadily at a rate of over 40% in the summertime. But this is extent, not volume, and we really need volume in order to deal with the heat content. But we have estimates of that. Now, in Antarctica, it's melting. Well, this is Greenland. It's melting around the edges, and in Antarctica, it's mainly melting in the West Antarctic ice sheet and in the Antarctic Peninsula. And so we have estimates down the bottom now of how much Greenland is melting. It's a rate about 2 terawatts. The East Antarctic ice sheet over here is actually picking up more snow. And so it's actually accumulating snow. And so this is going in the other direction at 2 terawatts. The West Antarctic ice sheet is, through its melt and so on and warming, is taking up 2.5 terawatts. The Antarctic Peninsula about 0.5, and Antarctica as a whole is around -1. And so Greenland and Antarctica we can put together for the major ice sheets. And then as an example, a couple of years ago in 2019, and this has been happening very recently in Greenland, the snow or the ice cover has been rather dirty with the melt, all of the accumulated dust on top of it. And we have these rivers of water and moulins where the water is flowing down to base level, and this can destabilize the overall ice. And so there have been some exceptional events like this. Now, what about land? If land is wet, the heat goes into evaporation, but in a drought, the heat accumulates. And so we have both drying and heating going on. And this is in dry conditions is when we get the accumulation and we can see the effects of global warming. So if we have 0.9 watts per meter squared, let's say one, over a 30-day month, that's 720 watts per meter squared over 1 hour. Well, that's 720 watts is the equivalent power of a small microwave oven. And, 1 square meter is about 10 square feet. These occupy about 1 square foot. And so this is equivalent, this energy imbalance is equivalent to a full powered microwave every square foot for 6 minutes. 6 minutes. No wonder things catch on fire. And so this is a physical argument as to why there is an increase in wildfires all around the planet, and especially in certain parts in Greece and Turkey and in the western parts of the United States this year. I'll come back to that. So if we look at land as a whole, how much energy is going into land? And there's a lot of land which is managed. These are irrigation circles. And there's some numbers here about how much humans have actually changed land, and we use irrigation, of course, as an example here. Forest has increased in general, but there's been a loss in the tropics and an increase in the extratropics. And overall, bare ground is estimated to have increased by 3%. If we have heating at the surface, as there has been with global warming, it takes about 50 years to penetrate to about a 50-meter depth. So, the ground is actually heating up very slowly, and the estimates as to how much it's heating up are somewhat uncertain, but I'll give you a number later. So what about the oceans, ocean heat content? Here we have to deal with just the ocean heat content, the heat, rather than the kinetic energy and the potential energy and the latent energy components. And we have an observing system called Argo. There's about 3,800 of these floats that go down and sample the top 2 kilometers of the ocean with a cycle time of about every 10 days. And we've got reasonably good global observation since about 2005. But using that information, we've been able to construct what's happened back in time. And this is the estimate back in time with some error bars on here of the global mean ocean heat content. And you can see it's been warming very steadily in recent times. And this is what it looks like as a function of depth. These are the so-called stripes giving you the amount of warming that's been going on in any individual year. And you can see in the top 500 meters, it really starts warming in here, and you can see it in the global mean here. But we don't get warming between 500 and 1,000 kilometer depth until the 1990s, and a bit deeper, 1.5 down to 1.5 kilometers. It's late 1990s, and the bottom layer of the Argo floats, 1,500 to 2,000 meters. It's after about 2005 that the main warming has occurred. And so this contributes to sea level rise, and this is the overall estimate of sea level rise since 1992, when we've had altimeters in space. These are the different altimeters, Topex Poseidon and Jason series. And I've put some lines on here to indicate that the overall sea level rise has been about 2.8 millimeters per year up till, say, about 2011. And then there was this big dip in 2011, and it's taken off since then at around about 4.5 to 5 millimeters per year. This big dip was when there was a lot of rainfall on Australia in a La Nina event, and also in other parts. There's more rain on land in La Ninas, and in El Ninos, 2016, there's more rain on the ocean, and so more drought on land. And so we see fluctuations in sea level relating to the amount of water on land. And that's the main source of these fluctuations in here. 1998 was a big El Nino. You see this peak back in here. And so sea level has gone up by quite a lot. And the overall warming is responsible for about 47 millimeters of global sea level rise. And so the overall synthesis is that we have about 3.4 terawatts going into the atmosphere. Thawing permafrost is about 2 terawatts. I haven't had time to go into detail on all of these aspects. The land warming as a whole is estimated to be about 14 terawatts. And the Arctic sea ice is about 3.8 terawatts. I showed you the reduction in Arctic sea ice, and we can estimate that. Greenland is about 2.6 terawatts as a whole. So this includes the surrounding regions of ice, not just the 2 terawatts that I had before. And Antarctica as a whole is about 1.2 terawatts in this estimate. Glaciers, melting glaciers around the world, the estimate's about 3.4 terawatts. And so if you add up all the ice, it comes to about 11 terawatts as a whole, 11 terawatts. So the land is about 14, and we can add all of these up. And so the non-ocean component is about 30 terawatts, which is about 7% of the total, which we estimate is about 460 terawatts. The ocean is about 430 terawatts. And that converts to 0.9 watts per meter squared. And so this is 2005 to 2019. And there's an error bar that I put on this. This is our latest estimate of how much energy, the energy imbalance is. And I talked about that and some of its consequences and how it compares with some other things earlier. So there's a lot of regional manifestations of this, of course. I've talked about things mainly from a global standpoint up till now. And so we can estimate the net surface flux of energy into the oceans. And so the blue areas here, this is for 2000 to 2016. The blue areas are where the heat's going into the ocean. The red is where it's coming out. The main areas where it's coming out are over the Kuroshio, off the east coast of Asia, and over the Gulf Stream off the east coast of North America, where there's cold, dry air in wintertime flowing out over the very warm ocean. And there are huge fluxes of heat into the atmosphere in these regions. Now you'll see in the Arctic that there's generally heat coming out of the ocean into the atmosphere and being radiated to space in general. And in general, in the subtropics here, there's heat going out. That's mainly through evaporation. And there's some interesting patterns down here and around New Zealand where I am now. This is the Campbell Plateau, and these all correspond to bottom topography and fluctuations in where the Antarctic circumpolar current is going. And so these are real. We can reproduce these in models, as it turns out. But in general, what this means is that the heat in the ocean flows from the blue areas to the red areas. And so we have currents that actually carry heat in the ocean, and we can actually back out what those currents are doing in terms of moving heat around. Now, I pointed out before that there's a lot of red up here and up here. This blue is not enough to compensate for that. So some of this blue here or here has to go around into the Atlantic, or here into the Atlantic, and heat gets transported northwards to compensate for all of this heat that's coming out of the ocean in the Arctic with the seasonal melting of ice and so on, and in the North Atlantic. Now, I don't have time to go into all of the details of this. I'll just show you from a zonal average standpoint. This is the net at the top of the atmosphere, the required transport that occurs. So the heat is taken from the tropics to higher latitudes in the northern hemisphere and in the southern hemisphere. This is the measured amount in the atmosphere through the reanalyses that we can process. And then this is the ocean that we can get as a residual. And then the ocean component is over here. And by dealing with all of the ocean heat content properly, we can divide it up by ocean, and we get the Atlantic here, we get the Pacific here, and the Indian Ocean is here. This does not take into account the Indonesian through flow. We can actually account for that, but it turns out the Pacific and the Indian Ocean are coupled through this region here, and there's a certain amount of heat that just goes round and around Australia. So this is what it looks like overall. And then south of 35 degrees south of Africa, it all gets combined into the Southern Ocean component, because mixing occurs with the Antarctic circumpolar current and so on. So I don't have time to go into that. And instead, what I'm going to talk about now are the changes in extremes that are a consequence of this. So with higher temperatures and heat waves, there's wildfires and other consequences, but there's fewer cold extremes. But there are more extremes in the water cycle, the hydrological cycle, more intense precipitation, longer dry spells, increased risk of flooding and drought, more intense storms and hurricanes and tornadoes. And this makes major challenges for a water manager. So I'm going to talk about that now. And so this is a bell curve indicating things like temperature under normal conditions. And then what global warming is doing is it's moving that curve to the right. So there's fewer cold events, there's more heat events. And so out here, where there used to be, 1% of the time events, suddenly events are happening 10% of the time or something like that. This is where the biggest changes are occurring. And that's what we're seeing very much this year, in fact. And so I'll talk a little bit about hurricanes. We get asked, I actually can't read my screen, something blocking it at the top here. But are hurricane disasters natural? And I've used some examples here in this, So this was, I started this slide in 2017, 2018, 2019, but I haven't got the last couple of years. I'll deal with those separately. And so, yes, hurricanes are natural, but they're now supersized when they occur. They tend to be bigger and last longer. And I would suggest to you that they would not have occurred without human-induced climate change, or at least not have occurred the way they did. And so they've been further exacerbated by poor preparedness in many places, although there has been some excellent preparedness that has improved in places like India and Bangladesh. So these are the kind of damages that occur with typhoons and hurricanes. There's wind damage when the storm comes ashore, but there's a coastal storm surge. But then the heavy rains and the flooding can extend a lot further inland by 1,000 kilometers or more in many cases. So with climate change, we expect that there's more activity. There's more intense hurricanes, bigger hurricanes, longer lasting hurricanes. There could even be more hurricanes, although in general, we don't expect that to be the case. And there's more flooding rains. And one reason why we don't expect there's more is because one big hurricane can take a lot more energy out of the ocean than 3 or 4 or 5 smaller hurricanes. And that's a key role of hurricanes. So if we go to 2020, there was a tremendous amount of activity over Southeast Asia, and all of these storms went in particular into Vietnam. And I've got some of them here and showing just a little bit of the damage. And so there's tremendous activity last year going into the southern part of Asia. And then there was also a record year in the Atlantic. Now, these storms weren't the biggest or the most intense that we've seen, but there was a record number last year. And by late in the season, by the middle of November, it was actually the 30th named storm in the Atlantic that had occurred, and that had not occurred before. And so this has continued as we went to December, to the Southern Hemisphere summer. There was some devastating storms, and this one here, Yasa, there's Fijian Islands here, and now here the Fijian Islands are straddling the eye here, and so there was tremendous damage that occurred, and I'll show you some of that damage here. In fact, there were 2 hurricanes that hit Fiji in the summer last year. And then some recent flooding and heat waves. There was tremendous flooding. Again, this is mainly 2017 to 2019 in Southern Asia in particular, and then in Venice, in the UK. And then there was flooding in Japan in the early part of July in 2018. And then the second part of July, there were record heat waves with temperatures over 40 degrees. And so here's a single location where they had both of these different kinds of extremes in the same month, and a tremendous amount of damage with a lot of deaths and a lot of people with heat stroke. Thank goodness they didn't get it quite that bad in the recent Olympics. And then, of course, we have all of these wildfires. There was 2018 was the record at that time for the number of wildfires. And there's some statistics here on some of the damage that occurred. And again here, and also in Brazil, even in the Amazon, and a large number of wildfires. And then at the end of the year, we went into this tremendous bushfire season in Australia. And there was all of these very dry conditions in November 2019. And there were all of these wildfires that occur and put a tremendous amount of smoke that we saw downstream here in New Zealand, where I'm located. And a lot of it actually got into the lower stratosphere, and it was seen in South America and all around the Southern Hemisphere. And it actually caused a veil in the lower stratosphere for a while, because it can hang around there a bit longer and block the sun. And so it actually had an effect on global warming. It depressed global warming slightly as a consequence. Now, in 2020 in California, there was more wildfires than in 2018. And so that was the worst on record. It looks like it might be exceeded this year. And so there's some numbers here for the tremendous damage and the temperatures that were recorded at this particular time, with smoke manifested in various places and getting as far as Europe. And so with the wildfires in Australia and all of the wildfires in California, that put enough carbon dioxide into the atmosphere that it more than compensated for all of the reduction in burning of fossil fuels by less driving of cars because of the pandemic around the world. So there was no reduction in the rate of increase in carbon dioxide in the atmosphere. And then this year, there was this major heat wave. This is Portland, Oregon. This is the overall measurements as a function of time of year that have occurred since 1979. And then suddenly we had these 3 days of outstanding records, temperatures in degrees Fahrenheit of 110 or thereabouts. And all of this heat was occurring up into Canada and British Columbia, and the town of Lytton. They received a record of 49.5 degrees, where their mean temperature at this time of year is 24 degrees Celsius. So tremendous heat there. And then 3 days after this was, or 2 days after this was recorded, there was a wildfire that went right through the area and wiped out the whole town. And so the hundreds have died from this heat wave. And this is part of the circulation, the anticyclonic conditions that brought that about. So in 2021, there's been in Western Canada and in the US, this is 2020 in Los Angeles County. In 2021, you can see the difference in how dry conditions were. And down the bottom, this is the drought monitor in the Western US in 2017, 18, 19, 20, 21. It's most widespread. And consequences, all these wildfires. Lake Mead in, where is it, Nevada? You can see how much the water has dropped. This is wildfire, and this is actually a winery in Napa Valley, and all of the wine has been contaminated and destroyed by the smoke, and the grapes have been destroyed by the smoke. And then because this conference is in Turkey, I highlighted some of the recent wildfires in Turkey here. And also, of course, in the news at the moment, there's a lot going on in Greece. And so here's some of the consequences. And this was from an airplane showing all of the wildfires in Turkey that have occurred, and tremendous amount of damage occurring, and global warming is a part of the cause of this. And then in July, there's been some devastating flooding. You've heard about it all in Europe, in Germany, and the Netherlands and Belgium, with over 200 dead. And it was actually quite well forecast, but people were not adequately prepared for it. And these are all some pictures that occurred at that time. And then in China, they had, over 300 died in a major downburst that occurred and flooded the subway there. And in Mumbai, India. And in New Zealand, this probably didn't make the international news, but there's been extensive flooding in the South Island in an episode a little bit earlier in winter, and relatively recently in the northern part of the South Island and right in the northern part of the North Island. Just tremendous flooding that has gone on. So it's occurring in many places around the world. So it has costs. Climate change is happening. It's caused by human activities. We can estimate that really the difference is relatively modest. Let's say 10%. That's certainly what we can estimate, say, in terms of the overall impact on rainfall. But this means that records get broken and thresholds are crossed, so things break and they flood and things burn and people die. This is an extreme nonlinearity. And so instead of in a hurricane, $1 billion in damage, which you might expect, the damage is $100 billion. It gets greatly amplified. And I've talked with a number of economists, and they agree that they just can't deal with this kind of nonlinearity. And the estimates of the costs are greatly underestimated. And maybe this is one of the reasons why politicians haven't responded to these kind of warnings adequately. And so this is what I call the straw that breaks the camel's back syndrome, that the economic damage has been greatly underestimated. I'll be interested to see after this year, with all of the damage that's going on, and I think it's being much more widely accepted that there's a climate change component to this as to how much gets blamed on climate change. But I think a lot of that methodology that's used for that, you can't just take to it, because things are broken. And so suddenly, instead of $1 billion, you've got another $90 billion. And so the $90 billion is what should be subscribed to climate change. So I have a book which I have produced in my time during the pandemic. It has just gone through the galley proofs, and it's available. This is the cost of it in US dollars, in pounds here, and the cover probably won't look quite like this, but this is the title of the book, and it deals with all of the things I've talked about here, and it doesn't have much in the way of equations. It's got a lot of graphics, and it talks about the physical reasons as to why a lot of stuff is happening. And so you can send me an email at this address here, and I will send you the order form, and you can order that book from Cambridge University Press and get a discount, get a 20% discount. You can either get a hard copy, which is twice the price of the paperback, but I will stop sharing there, and hopefully that will stay up. Did it? No, it didn't. Let me put this back and just exit the slideshow. That didn't work either. So anyway, I'm done. Any questions? Yeah.
Thank you, Dr. Tranberg. We have a question in Q&A from Dr. Dinchak. It's about the forest fires. Is there a way to achieve local atmospheric conditioning, just like indoor air conditioning, to avoid drying and heating, which results in forest fires? Imagine the relative humidities in the forest fire zones drop down from 35 to 50% to 8 to 10%.
Yes, I mean, ironically, perhaps one of the things that has cooled off the land more than anything is the smoke from the forest fires themselves. But yeah, in general, under the conditions of a drought or dry conditions, there is settled weather, anticyclonic conditions. And so the skies are relatively clear. The sun is beating down, and you have to compete with the sun. And so, anything, this is why people have talked about painting roofs white or having any roads that are white, but it's rather difficult. Instead, I think there's a lot of work that needs to be done in cutting down on the litter and the ability to things, especially dry lightning, a thunderstorm that doesn't have any rain attached to it, but it has lightning from initiating a wildfire. Cutting down on that, and also quite a lot of wildfires get lit by carelessness or deliberately by people through arson. And so I think that's the best adaptation to it. It's trying to build resilience in that way.
Thank you very much. I have a question about increasing certainty of climate modeling. So from the earlier reports of IPCC up to this sixth report, those confidence levels are getting better and better. So yeah. What are the factors going into that? So what is the thing we are understanding better related to climate now compared to the older times?
Yeah, so the computers have gotten bigger and faster. And of course, there are thousands of processes on an individual computer. And as a result, the models have increased in resolution. And so some models are being run at 25 kilometer resolution for climate purposes. And there are models that are being run for limited areas and limited times at much higher resolution. And so even at 25 kilometer resolution, the models can resolve or have rather crude looking hurricanes, for instance, and the previous models did not. And so they're better simulating a lot of the phenomena. And certainly in terms of today's climate, the models do a lot better. There are still issues about how clouds will change in the future. And some models are souped up and tend to get rid of the clouds. And they've had too much warming. But the IPCC has done an assessment of that, and they've taken that into account. But they've been able to do a lot more aspects, not just globally, but also regionally. There's quite a lot more confidence in what they can say about what is happening. And also in even the water cycle is done a lot better than it was in the past. And so there's generally more confidence in the models, and a lot of it relates to increased computer power. Well, another factor is that the individual models are being run multiple times. So this is what we call an ensemble. At NCAR, rather than just run the model once, we run it 40 times. And so then you can sample the different weather conditions, and you can average, and you can take out the weather components, or you can look carefully at the El Nino components, and then you can look at the climate change component. And that's another key thing, actually, for sorting out the climate change signal from the noise of natural variability.
Thank you very much. So as the uncertainty gets smaller, in fact, in the past, probably people couldn't understand the urgency because the uncertainty was on the same order with the number most of the time in the results.
So I talked a bit about the uncertainty in models, but the other area where uncertainty has been greatly reduced is in the observations. And that's what I talked about here, in particular in the ocean. Before, we didn't know what was going on in the oceans adequately, and we couldn't understand, therefore, what had happened adequately in the past. And now we have a much better understanding of that. Let's see, 8 years ago, we couldn't put together a sensible Earth energy imbalance estimate, and now we can. And, and so I told you what that was and all of the different components to it. It would be very nice if we had much better time series as to what's going on in land. But, we've got these boreholes at places that people didn't bore the holes in the ground to measure the temperature. They did it because they're drilling for water or for some other purposes, to put a building in place or things like that. And also in the ice, in the cryosphere, there are a number of estimates from different methods that differ by uncomfortable amounts. So there's quite substantial error bars in just what's happening in Greenland and Antarctica, but still the overall estimates put those numbers. I gave them a ballpark number. It's not where the main energy is going, and so now we've got some numbers, and we can understand physically what is going on, and that gives us a much better basis for saying what's happening in the future.
Thank you very much. It was a very, very interesting talk, and it was very timely. So I only had a chance to go through the executive summary of the report that was released yesterday. Thank you. So,
all right, I hope people will be interested in my book, and send me an email, or I can send you a copy of what I received from Cambridge University Press in terms of how to order it.
Thank you very much. Thanks.
Thank you.
So we should move to our second keynote speaker today. So our second keynote speaker is Dr. Jean-Lei Niu. He's the chair professor of Building Environment and Energy at Hong Kong Polytechnic University. He received his BS and MS degrees from Tsinghua University and his PhD from DAF University of Technology. Among other honors, he's a fellow of American Society of Heating, Refrigerating, Air Conditioning Engineers. He has more than 300 publications and 2 US patents. He's currently co-editor-in-chief of Energy and Buildings. Today, he will talk about progress of thermal energy storage technologies for air conditioning of buildings, especially with the use of phase change materials. So, floor is yours, Dr.
Thank you, Professor Tari, for your kind introduction. I hope that you hear me okay.
Yes, we can.
Okay,
hear.
that's great. Thank you. First, I have to I'd like to say my complimentary remark for the presentation from our previous speaker, Professor Kevin Tranberg, which gave excellent background of my research. By training, I'm an air conditioning engineer, and yet over my academic career, I think I'm I'm a traitor of the air conditioning industry. Because I believe that the wide use air conditioning is one of the culprits of the global warming, the climate change. I keep on saying that to my students, to our colleagues, and which happen to be the overall objective of my research is really to reduce the use of air conditioning in our buildings. Right now, I'm staying in Hong Kong, and we are experiencing a hot summer again, a record hot summer in Hong Kong. 33 something every day for a whole 2 months, in the past 2 months. And so our research is really to look at the alternatives to reduce the energy use. So today I focus on the one particular technology, that is the thermal energy storage. We are trying to see how the technology can be explored to reduce the energy we use in our buildings. So that is the for that, I thank the previous speaker for the excellent background of why we are doing this research. First, I'd like to give a kind of historic perspective of energy storage, and then how the thermal energy storage has been playing a major role, even in our traditional architectural design. Probably the only mechanism in our traditional architecture that keep us comfortable. But today I will focus more on the more active mechanical systems, how this technology can be combined with the modern, say, air conditioning climate control system design to reduce and to minimize energy use. So that is overall of my say, framework of my talk today. Actually, it's not so long ago, we rely on some natural energy to keep us cool in the summer. These slides come from the ASHRAE, the American Society of Heating, Ventilation, and Conditioning Engineers, illustrating the a big industry not so long ago that happened in the say in the 19th century. People harvest ice in the winter and store them in the ice house, and then sell them in the summer. And that is that was not so long ago, okay? That's just about 100 years ago, in fact. Yeah. And if you have the chance to travel to London, in fact, there is a so-called ice trade museum in London, which is located not far from the King's Cross railway station, and you can have you can actually see the barge and some other machinery used in that time, and that is how our ancestors used natural cooling to keep us comfortable in the summer. Energy storage happened to be the actually the resource for the fossil fuel we are consuming today. In China, we explored natural gas probably about 400 years ago. Yet industrial revolution came, we know, in the 18th century, in the 1780s or 1760s. That drastically changed the energy flow of on the Earth, which happened to be covered by the previous speaker. But I'd like to show you a comparison of the, say, the energy accumulation rate with regard to the fossil fuel. We agree that it's about 300 million years ago, all the fossil fuels were buried underground by this natural process. And how long that has been, actually, I didn't find out the figure, but that was a long geological period. What's happening now is that since the Industrial Revolution, we are digging out these fossil fuels within 226 years. And this is the energy, basically the discharging of those accumulated energy from the underground. And that is believed to be the reason of the climate change. And this may be a detour from the topic I'm supposed to cover, but technologically, rechargeable battery is one of the, say, successful engineering technology that is changing our lifestyle. I think everybody is holding a mobile phone or smartphone nowadays. Not so long ago, we knew the cellular phone was very bulky, and that was because of energy storage technology was not good enough at that time. The battery needs a long time for charging, and yet the density was low. Another successful technology is the lithium-ion battery used for the electric cars. Here we have a figure. The battery of a car can be charged within 30 minutes for you to drive over a distance of more than 300 kilometers. And if you charge your car for 1 hour, you can drive your car for 500 kilometers. And that was a great achievement, I would say. In fact, currently in many cities in mainland China, all taxis have to be changed into electric cars. And for the taxi drivers, the charging time is the time that they cannot do any business. So the charging time becomes very critical for the taxi drivers. And but somehow this is the something that has been achieved with the battery energy storage. So long you have a supercharger, you can charge the car very quickly. Now the reason I'm introducing using battery as example is trying to illustrate the very important concept of so-called charging and discharging time. These indices are also important for the successful application of any thermal energy storage technology in buildings. Using the slides on the left, I try to illustrate that the short charging time and a long service life of any storage device is maybe a desirable feature. But for building applications, we may have some other desirable feature. That is, your device may also allow slow charging and allow a very high intensity discharging. For instance, the hot water system we use to take a shower, you take a shower in a very short period of time. I think some of us do that. We probably within 5 minutes, within 10 minutes. Yeah. But the charging, if you are using a natural resource, for example, you use a solar collector, and depending on whether you have a good suitable climate, you may not have all the, say, the high intensity solar radiation all the time. In that case, a slow, low solar intensity charging should also be acceptable. Therefore, you would require a system that allows slow charging, and yet which can give you the high discharging rate you need. So that is these are the two performance indicators for the thermal energy storage for our buildings, which I will illustrate in a moment. But I do like to share a breakdown of the energy use in our buildings. Here I use the building in Hong Kong as an example. The left chart shows us the breakdown of the energy we use within our buildings, in our commercial buildings. Okay, basically all buildings except residential buildings in Hong Kong. If you look at breakdown, space air conditioning consumes a quarter of the total energy used in buildings. The hot water and the refrigeration are primarily used in commercial restaurants, in a metropolitan city. So that contributes another 12%. So in total, there's almost 40% of the energy used for cooling, and for the hot water used in hotels, in restaurants. Therefore, this form of energy eventually are the thermal energy. If you look at the energy consumption in the residential building sector, you would see that again, one fifth of the energy, 20%, more than 20% used for air conditioning, and nearly another 20% for hot water use. This is primarily the hot water consumed for taking a shower in a hot climate. So that altogether, it's about 40% of energy we used. Yeah. Of course, in the past 1.5 years, we spent more time working from home to cope with the ongoing COVID-19 pandemic. And I think we probably will consume more for our computers, for our equipment at home. But that give us idea about why we say the building is one of the culprits of the energy consumption. And so if you wish to cut the CO2 emission, we have to look at how the energy are being consumed in buildings, then reduce this building use. Then I come back to the topic I'm supposed to talk about today, which is the thermal energy storage applications for building and for buildings, especially for building heating and cooling. I like to start with a very short summary of how passive application has been playing a major role in our building or in our dwelling environment. And this is the wisdom embedded in the traditional architectural design before the use of any other heating and cooling technology. We know our ancestors know how to use the thermal mass to moderate or to regulate our indoor climate. We rely on very thick walls and heavy floors of clay, natural rocks, and bricks to moderate our climate. And when our ancestors knew that we can combine the use of window, which may allow a lot of solar penetration, and which may allow the natural ventilation in the hot summer, so that the solar energy can be stored in the cold winter in the building materials, and through natural convection cooling of the heavy walls and heavy floors, the cooling nighttime cooling can be stored indoors. Therefore, your maximum temperature in the cold winter will be raised, and the hot temperature in hot summer will be reduced due to this diurnal variation, or the use of the diurnal variation of the ambient climate and the solar radiation, so that no matter how cold or how hot the outdoor is, your indoor climate could be significantly different from outdoors. Yeah. So in that sense, thermal energy storage is not a new technology. And it is a technology that has been used by our ancestors even before modern science came into existence. Yet, the emerging new material, what we call now phase change material, offers many new opportunities. So in the research community, in fact, ever since the energy crisis that happened in the late 1970s, researchers have explored various possibilities of using phase-changing material in building envelopes or embedded into building, say, walls, ceilings, or even floors as a kind of passive measure to reduce energy, the mechanical energy that is needed for cooling and heating. Okay. Today, I'm not going to speak too much about this passive technology. My colleague, Professor Zhang from South China University of Technology, has done a lot of work in the recent years. And here I gave a reference of the his review they have given in the journal Renewable Energy, and the interested colleagues may refer to this publication. Probably in the next half an hour, as I'll be spending more time in illustrating the active mode of application of thermal energy. One technology that has been widely used is the ice storage for hot water for air conditioning use. For example, ice storage has been used maybe in the past 30 or 40 years to reduce the peak electricity demand that is needed for air conditioning. And we run the chiller or the refrigeration system during the night and store the ice. And then the ice is used during the day for the air conditioning system. And that has been used successfully in many countries as a commercial application. In many countries, we use electrical water heater to heat up water in the low, say in the off-peak period, so that you pay a lower price for the electricity energy you consume. And then you can use the hot water, take a shower, or take a bath anytime you like. And so this is these are the practices. But more recently, I think in the research community, we are exploring the opportunities of use a natural cooling source to store cold water, which can be used for cooling. And this may include the use of sky radiation and natural evaporative cooling to cool some water or another material, and then the stored energy can be used for air conditioning. But for these kind of applications, there are a lot of challenges because the time that available for you to obtain the lower temperature cooling is very short. For instance, if you want to use the nighttime cooling to cool down some water, and the lowest temperature happens before the sunrise, and that's only lasted about 1 or 2 hours. So you wish to finish this storage or the charging process in a very short period of time. So you need a very high charging intensity, and that is not easily say achievable with the current thermal storage devices, which I will illustrate in a moment. The same happens with a solar panel hot water heating. If the solar, say the sunshine time is not long in the climate where you stay, you wish to have a short-term charging, and that is also very demanding for a solar panel design. Another application of thermal storage is found for our modern data center cooling. Nowadays, we rely so much on the internet, and we know these are the data center plays an instrumental role And the energy intensity for the data center is very high. And the servers need to be cooled, mechanically cooled all the time. And to ensure the reliability of those servers, we have to provide a standby cooling system. So in case of any electricity outage, the cooling has to be sustained. And we need a standby cooling, and that is provided by the cooling storage. In a moment, also I will talk about this, say, cooling storage that serve the data center. So this gives you idea that the thermal energy storage are being played and can have the potential to play in the future. Therefore, we require a kind of variable charging or discharging rate for the device. And we also try to avoid any energy loss during the storage, and which would be a great challenge. We also need a very high storage density, and that is not always achievable. Here, I try to illustrate the concept of the ice storage, the role ice storage played in modern air conditioning. The picture above shows a typical room which may be heated in the winter by a radiator, which may be cooled by a ceiling panel, a radiant ceiling panel, combined with the air conditioning system. Now, with ice storage, we would run a refrigeration system which can produce ice in ice storage tank. And during the day, when the office is in operation, then a water will be circulated through the heat changer that goes through the ice storage tank, so that a room is cooled by the ice stored during the night. Okay, so in such a way, the daytime requirement for the air conditioning system, the energy requirement will be reduced. And that will help to level, say, the demand curve in a city on the electricity, and that improves the energy efficiency of our power generation. And this slide illustrates the current successful design of ice storage. In fact, running in the tank is a tube in which is either the refrigerant and the say a brine that use the glycol that can run below the freezing point of ice. Okay, so that the ice tank will work at a temperature below 0 degrees. And that is the advantage that increases the energy intensity of the storage tank, but that also lowers energy efficiency of the storage process, because for air conditioning, we don't really need such a low temperature. Therefore, in more recent years, researchers are looking at the other options, which is to use the sky radiator or a cooling tower to store the cooling at a moderate temperature that around 10 degrees rather than at 0 degrees Celsius. Yeah. And we can extend this storage to off-peak electricity cooling. In this slide, I tried to illustrate the stratified, say, chilled water storage. On the left-hand side, it shows a water tank that stores the water at 10 degrees Celsius. Oops. And so as say hot water flows into the tank, and the cold water will come out from the bottom of the tank. But I wish to draw your attention to the time scale shown on this slides. In fact, the whole tank can only last about 300 seconds, which is basically 5 minutes. Yeah. And can you imagine that you have a battery on your phone that can only last 5 minutes? But unfortunately, that is the case with the hot water storage for a data center. Yeah. So that in doing so, we are hoping that the standby chiller can be started within 10 minutes. So once you have 2 storage tanks, the 10 minutes altogether can provide a time for the chiller to be start up based on the say a diesel engine that is located within the building, just in case there is an electricity outage, so that the data center can continue to operate without the losing of any data. This just shows you how the a thermal storage tank look like in our laboratory. And this slide showing you the idea how a building, as illustrated by this transparent plastic box, can be cooled by a natural cooling source that may come from underground, may come from the natural river or the sky radiator. Therefore, the core device for thermal storage system is the so-called stratified tank, as illustrated on the left-hand side of this slide. And the cold temperature fluid would be introduced in the tank at the bottom, and see the hot fluid will be dispelled from the tank. So you have a large temperature difference. Okay, in the lower part is the cold fluid, and in the upper part it's the hot fluid. So in such a way, you have a drastic temperature difference, or we call it stratification, which is very essential for an effective storage device. Such a device will allow a variable charging and discharging rates, and to minimize any possible energy loss in the storage process. And ideally, the fluids is not necessarily water. It can be a media, another fluid which has a much higher specific heat, and that is the research is about in the recent years. The reality is far from that ideal storage. Okay, the water may be well mixed instead of stratified, and the water density, because the specific heat of water is not that high, so therefore the water storage tank is very bulky, and the time it can serve is also very short, as I have illustrated. And the current PCM technology has not been matured to be commercially say competitive in comparison with water or ice storage. Because of time, I think I wish to quickly illustrate two possible breakthroughs. One is to develop a functional thermal fluid that may have equivalent high specific heat, apparent specific heat, so that with the same temperature difference, it can store a much higher energy. And one way to do this is to disperse a phase change material into water, so that you have either a slurry or you have an emulsion. The differences between the two is that the slurry has the particles has a shell, while the emulsion PCM doesn't have a shell. In other words, it's the oil. You may simply say it's the oil that are dispersed in water, while a micro-encapsulated PCM is like you have the micro-sized eggs that are dispersed in water. Okay, these are two alternative technologies that may have application as the functional thermal fluid to replace water, which I will illustrate in a moment. Alternative technology is to say enhance the thermal conductivity of phase change material, so that the enhanced PCM material will be embedded into the traditional shell and tube heat exchanger design between the tube and the shell, so that the apparent storage capacity of the tank is increased. And this is alternative. Today I'm going to illustrate some of the recent progresses in my research group, but also from other researchers in these two directions. Basically, a thermal function fluid will be looking like a milk, in which the phase changing material is dispersed into the water in fine droplets, which can be in the size of here in 20 micrometers, as shown in this picture, or here as microcapsulated. Okay, you may say it's microcapsulated droplets in water in this side. In this case, it's also about 20 micrometers. Okay. Of course, there are a lot of you can have a lot of choices of phase changing material. One of the problem you have to overcome is to increase the conductivity of the phase changing material, which is very challenging. Another key index is the so-called supercooling, which is the temperature you have to further cool below the apparent melting temperature of the material. And this is a very undesirable temperature difference you have to resolve. Okay. These slides basically illustrate the relative size of the shell and the PCM for a successful, say, MPCM in water slurry. Because the shell of a the capsule of say slurry may have a limited service life, so the alternative emulsion without the shell may be a better option. And in these slides, we have developed some samples that can allow us to suspend PCM droplets in water as a milky submission emulsion. Okay. And in conjunction, we can use nano particles as additive to control also the subcooling, so that the thermal properties become more desirable. For the sake of time, I skip a few slides. I wish to illustrate the concept of so-called stability of the emulsion, so that they don't form say blocks in the application. Here we have a video illustrate the stability of this emulsion. So the milky products can be actually transformed into a transparent one, to so that the droplets will be further reduced to the scale of the nanoscale. In fact, the whole emulsion become kind of semi-transparent. The purpose is not to increase the transparency. The purpose is to increase the stability, to make sure the emulsion is has a good fluidity for a long-term period. This is very important for a thermally function material. At least in the laboratory, we have done this. Okay. Second, I wish to illustrate there are two modes of application. One is to use pure PCM and placed between the tube and the shell of shell and tube design, so that the apparent storage capacity can be introduced. We have both experimentally and numerically examined how the thermal conductivity will be critical. Okay, if the conductivity of the material is too low, you will end up only a small percentage of the material will be used, as illustrated by this chart. Okay. Only when the conductivity, for example, is enhanced by at least 5 times. Okay, illustrated by the curve of these 2 slides. In these slides, a large percentage of the phase change material can be used. In other words, if you use too much material, it will be counterproductive, and the energy storage will become lower rather than becomes higher in comparison with just the pure water tank. For the sake of time, I illustrate this concept here. For instance, this is the experiment that we have performed. Imagine this is the storage tank in which chilled water of 5 degrees was stored and discharged into the building to cool your room. And then, because the room does not require this 5-degree low temperature, so we use some return water to control the supply. Okay, this is the pure water storage. Now we are saying we can introduce a shell tube design by embedding the phase change material between the tube and tank, so the water only flows inside the tube. How does this shell tube design work? And in these slides, we illustrated this. There are a lot of curves in this chart. For the time being, you can forget about this curve. Concentrate on this figure here, 2. Okay, range from 0 to 2. 2 means that the tank can store energy twice of the tank of same size of water. Yeah, and this is the actual experimental results we achieved with the optimal design of the shell and tube. When we use a material that has a high conductivity, and this is achievable. Okay. Alternatively, we tried this pure liquid to replace water. Here we have this thermal function fluid that replaces water. And how does it work? Well, we have done both simulation and experiments. Basically, in simulation, it performs to the level to ideal water stratified tank. Yeah, it's not that fantastic, I have to say. But if we can manage this stratification better, then using validated simulation, we illustrate it as indicated by this line. Such a design can provide 25%, 1.25 times storage capacity of a water tank. So that is still a kind of achievement, and we are fairly proud of. And that is one of possibility. Yeah. So because of time, I think I have to stop here. And what I wish to say that with the say phase changing material, some of the shortcomings, for example, the energy loss with ice storage may be avoided by using the phase changing material. And the size of storage device will not be so bulky as the current water tank. Therefore, a better energy efficiency and compromise in reduce the storage device, the size of storage in a building may be achieved, I have to say. So that is my own say assessment of development of technology. With that, I think I just stop here, and I may have time to answer probably 1 or 2 questions. Thank you, Mr. Chairman. Yeah.
Thank you, Dr. New. We have one very quick question. It's about whether or not any building codes developed or implemented in Hong Kong to impose energy storage practices.
Sorry, Professor Tarek, I think I didn't hear you very clearly, probably because of my microphone. I'm sorry.
So are there any developed building codes in Hong Kong imposing thermal energy storage practices?
No, our current code has not included thermal storage yet. I think for several reasons, because in Hong Kong the energy, the charge, the day and night temperature difference is not large. The current ice storage will not be very encouraging if you use ice storage, because the ice storage, because of lower energy efficiency of ice storage, it does not save electricity that much. It may reduce the electricity bill a little bit, but from point of view energy, from point of view environmental protection, the benefit is very minimal. For that reason, the code does not cover energy storage. Unfortunately.
Thank you.
Yeah.
Thank you very much.
Yeah.
I guess we passed our ending time. I want to thank both of our speakers and attendees for this very nice session. So I hope you continue to follow the rest of the thank you.
Thank you.
Good morning, everybody. Does everybody hear me clearly? Professor Emre Artun, do you hear me?
Yes, I can.
Okay. I think we are on time. We will start this session, this so-called specialized session on the new dimensions in fossil fuels. I will be chairing this session this morning. I am Professor Dr. İsmail Boz from Istanbul University Cerrahpaşa. And we will start our session with Professor Emre Artun. Just a brief background about Professor Emre Artun. Professor Emre Artun, he is currently holding an associate professorship at the Istanbul Technical University. And he's going to talk about the machine learning-based modeling of hydrocarbon reservoirs. Stage is yours, Professor.
Thank you very much, Professor Boz.
Right.
Okay, so I would like to thank the organizing committee for putting together this nice program and for inviting me. It's a great pleasure to be here with you today. So I'm going to talk about machine learning-based modeling of hydrocarbon reservoirs. First, a little bit introduction. So if you look at the history of science, we can easily observe the evolution of science through different paradigms, such as empirical science, theoretical science, and computational science. And these days, we are going through another era, which is mostly data-driven science, which tries to incorporate all the previous findings with the significant data that is collected in different industries. And this is mostly driven by data-driven models, analytics, and machine learning. And we also know this period as digital transformation, where all the industrial operations have been trying to adapt to this new era. So today I will first briefly give an overview of what is machine learning, and I will talk about how we can approach the reservoir modeling problem using machine learning. And then I will present two example studies which focuses on reservoir characterization and performance forecasting in hydrocarbon reservoir systems. And I will conclude with the future outlook and some concluding remarks. So machine learning is actually a modeling approach, and it fully relies on data of some phenomenon. The data may come from the nature, we can generate the data by ourselves using different types of other types of models, such as reservoir simulators. Sometimes algorithms may be used, statistical algorithms, to generate random numbers, but all in all of them are data, and we can incorporate these data into our modeling through machine learning algorithms. The phenomenon is a practical problem of interest that we try to solve. Every model is built to solve a certain problem, and here it's the same. And we classify these problems as into two groups. They can be either a prediction of a certain parameter or a couple of parameters, or it could be a classification type of problem. And the workflow is broadly the same. We use a data set. There is no physical equations or models, although they can be integrated to some extent. We need to start with a data set that represents the examples of that phenomenon. Then we use machine learning algorithms to convert this to build a statistical type of model, which can give us the desired predictions or classification results. And if we rely on this model, if we think that its accuracy is to the certain standards, we can use it to solve the problem, to make a decision or design some sort of a process that we would like to solve. The workflow includes data acquisition. Then we clean the data, because data in nature is not necessarily always clean. It's not always tidy, so we need to work on it a little bit to do some pre-processing. And after that, we use that data to model, to build the model through a training stage. This is here where machine learning algorithms comes into the picture. We set aside some part of the data set to validate and test our model. And if we think that our model is really reliable, then we deploy it to use it in real operations. There are three types of algorithms. Supervised learning includes both inputs and outputs. Unsupervised, we don't have any specific outputs, but we just have a set of data with inputs, but we just want to classify the data set into certain groups. And reinforcement learning is the most advanced type of machine learning algorithms, which is the building block for robotics. So where artificial intelligence come into the picture. Here, there is no data, but the systems learn the certain behavior by themselves through an exhaustive trial and error search with certain penalty and reward mechanisms. They really learn as they go along. So why machine learning is now very important? Actually, machine learning is not very new. It is as old as 1940s when McCulloch and Pitts tried to first mathematically describe what a biological neuron does. But now it is really getting more important because simply the data that we collect increased significantly in recent years. Also, the computational power has been increasing, both in terms of hardware and software. It gets cheaper and it becomes easier to access these facilities. And the problems that we deal with gets more complex as we go. We are looking for more extreme efficiency. We are looking for more sustainable solutions. On the other hand, the population is increasing, resources are limited, so lots of natural complex problems makes pretty much every problem more difficult. So the question is, can we use data to solve these problems? Why machine learning is getting important in the oil and gas industry specifically? There are similar motivations here. The computational power is increasing. Companies are trying to adapt digital transformation. And the question is, can we collect more and more data, and can we use this data to build reliable models to make better decisions in the industry? That's the whole idea. But also, when we look at the problems specific to oil and gas industry, we are dealing with more complex problems here as well. The industry downturn in mid-2010s, recently COVID-19 pandemic. We need to be more economic in our operations. Sustainability and climate change are creating some sort of a pressure to be more environmental efficiency. We are trying to reduce our carbon footprint in our operations in oil and gas. And also we are dealing with complex systems such as unconventional shale, for example. Still, the theoretical foundations are not in place. We cannot accurately model these systems using the conventional reservoir engineering theory, which makes it difficult to make decisions. So why not use the data to try to understand these processes better, such that we can maximize the efficiency, and also we can model physical aspects better in some systems. So how we can approach to the reservoir modeling problem? It is similar to other problems. We first need to identify our objectives. Why do we need a model? Why are we trying to build a model? What kind of a decision making we are going to use it for? What are the available data? What are the parameters that we have? What are the parameters that we want to predict as a result of this model? We should define these first. And after that, based on these objectives, the data set part comes into the picture. We need to develop a data set. We need to have a data set, either from readily available data, or we need to create the data ourselves using some sort of other models. But essentially, these data must represent the instances of the reservoir in the time and space domain. Therefore, we can capture both the static and dynamic characteristics of the fluid flow in the hydrocarbon reservoir system. After we have the data sets for our needs, we design the training algorithm, we train the model, we validate the model, and once we are satisfied with the prediction capability, we can use it as a predictive tool to make further decisions about the operations in the field. So moving on to some examples. The first one is a characterization example where we try to correlate surface seismic to well logs. Well log is a very high resolution data that we have in order to characterize the reservoir. And general regression neural network is a good training algorithm for time series approximations. So we try to predict from limited seismic data to obtain the full cross-section characterization. And we tested it with density log. Here you can see some predictions, and predictions were accurate. And we generated the gamma ray log through a 2D cross-section. These are white are the actual log lines, and the colored map shows the prediction of the algorithm, which can be used for selecting completion intervals, new well locations. Once we have good characterization of the reservoir, we can make lots of decisions about the reservoir's development. The second example is about an enhanced oil recovery process, which is cyclic injection into a single well. We inject, we soak, we wait for a while, and then we produce oil and gas to improve the oil recovery. This can go as many cycles as want. This is an interesting problem because there are lots of different design parameters that must be optimized to get the most value out of this process. So here we used a numerical simulator. This time we didn't have real data, but we want to generate data using a reliable numerical simulator into a hydraulically, in a hydraulically fractured well. And we tested injection of nitrogen, CO2, and methane mixture into Appalachian sandstones, which is in the northeastern United States. The soaking process is what is really driving this process through diffusion. And we model this using molecular diffusion theory. And as a performance indicator, we used incremental oil production and injected gas, the costs and income as a result of these volumes. And we created an efficiency indicator, which tells us how efficient this injection design is. So after collecting 9,000 different scenarios, we analyzed data and we observed that soaking period and CO2 concentration are relatively unimportant. On the other hand, nitrogen as a cheaper gas option positively affects the economic efficiency. So by just looking at the cross plots, you can get some insights about the process, which is the real value of this modeling approach. And then we said, okay, let's train a model that can actually predict the efficiency. And we used a neural network to do this. And again, by just looking at the results, we can gain some insights. For example, numerical error accumulation is observed as the correlation coefficients gets lower as we go from 5 years to 20 years. Because we use a numerical simulator, the error propagates because there are more number of time steps, longer simulation times. So we can see that here. Other than by analyzing the data, we saw that soaking period and CO2 were not that important. So when we removed them from the data sets, we actually saw an improvement in the prediction results. So therefore, we simplified the model so we get better generalization capabilities. And when we analyzed the neural network weights, we saw that nitrogen is actually very important, similar to what we observed, and soaking period is really least important parameter. So they were consistent with what we observed in the exploratory analysis. So looking at the future possibilities in this area, there are lots of debates going on recently, how the future petroleum engineers should be, what are the improvements that they need to have. And it is actually clear that next generation engineers should address the needs for sustainability, for lower carbon requirements. They should be more efficient in everything. And the digital transformation is really the key to achieve these. The job requirements will require more sophistication in terms of digital skills. So the next generation must be more digital savvy, and they should be ready to code, work with these data sets to build these kind of models. And this is a message to both, students and academia. I am also an academician, so we are trying to incorporate these into our curriculum right now. For example, we are offering new courses to address these issues and to help the students to develop their skills in this domain. Visualization is always a problem, and it needs to be improved. It keeps being improved, but the key here is to integrate different types of environments, such as business intelligence tools, databases, and machine learning models. Each of them are applied very efficiently within themselves, but when you come into the integration part, it is always difficult because database environment is different, the modeling part is different, the business intelligence visualization is different. Different skilled people are working on these, but how to integrate them is always a challenge, and it's an ongoing research area. Another aspect of it is how we can incorporate physics more into machine learning models. Can we explain why these models do what they do? This is something, this is also an ongoing research area. Can we incorporate more physical laws as much as we can, so we can rely on more to the results that these models predict? Can we incorporate subject matter expertise more into the models, again, so that we can rely on them more? These are different approaches, and how we can integrate them, when we should use them, that's the real key. So to conclude, I can say that a new data-intensive era has already started in reservoir engineering and modeling. This is very clear, especially in the last decades. There have been lots of successful applications, and machine learning has been proven to be a successful modeling approach in multi-scale reservoir characterization, performance forecasting of complex systems, decision-making in challenging problems. I presented two examples of these, but you can find many more in the literature. And the important future needs are, first of all, since this is a data-driven approach, we need more data. Unfortunately, in the industry, data is not readily available. They are confidential, but some data democratization initiatives can be helpful, which actually already started slowly, but I'm hoping that it will improve more. Exploratory data analysis is important before starting to any modeling study. We need to work on how to incorporate physics and domain expertise more into these models. And in the training part, I think next generation engineers should be digital savvy to be able to work with huge data sets. And this is a message, as I said, to both educators and students, to be more ready for the digital transformation in the industry. I would like to thank you very much for your attention, and if you have any questions, I'll be happy to try to answer.
Thank you very much, Professor Emre Artun, for this enlightening talk. Okay, from the audience, if there's any question, we have 1 or 2 minutes more. We will wait. We would like to be on time for the next speaker. In the meantime, especially the students, raise your hands and ask questions. All right, sir. Thank you very much again for this enlightening talk. As a chemical engineer, I have also benefited, believe me. I mean, that's a very interesting topic, especially machine learning. And I've been interested, but I've never had the chance to work with any machine learning system during the last 30 years or so since I have been entered into the academy. Anyway, thanks again. Our next speaker is Dr. Özge Bozkurt. Dr. Özge Bozkurt, she is going to join us from the TÜBA Research and Development Center. She's going to talk about what's going on, what type of research is carried at TÜBA Research and Development departments. Okay, stage is yours, Dr. Özge.
Thank you, Mr. Boz, for the nice introduction. Hello, everyone. I'm Özge Bozkurt from the R&D department of Turkish Petroleum Refineries. In my speech, I will talk about the motivation on clean fuels, TÜBRAŞ operations, renewable fuel research at TÜBRAŞ, and the outcomes of my doctorate thesis study on alternative fuel additives. Shortly to introduce myself, I have bachelor degrees in molecular biology and genetics and chemical engineering. I specialized on biofuels during my master thesis studies. I conducted my PhD in the field of heterogeneous catalysis. After receiving my doctorate degree, I joined TÜBRAŞ as a chief R&D engineer, and I am currently the product owner of renewable fuels portfolio. In this first section of my speech, I would like to explain the importance of clean fuels. These are the fuels having low carbon intensity in their life cycle from field to the wheel of the vehicle. Coal, oil, and natural gas are fossil fuels whose origins descant back to ancient oceans and swamps of 300 million years before. Currently, fossil fuels are the main energy source of global economy, with more than 80% share. About the crude oil reserves, Venezuela, Middle East, and Canada have the largest oil reserves. And an average person is using 4.5 barrels of oil each year. Considering the current oil consumption and the oil reserves, there is crude oil for the next 50 years. The global greenhouse gas emission breakdown shows the energy sector as the major emitter. The greenhouse gas emitted is mostly carbon dioxide. Fossil fuels are used for energy production in industry, in transport, and in buildings for heating or electricity purposes. And these are done with the conversion of chemical energy into mechanical or electrical energy. When we look at the life cycle of crude oil, the major greenhouse emissions source from oil production and fuel combustion, and crude oil refining has a slight share in the emissions. And as seen from the hydrocarbon combustion equation, burning fossil fuels adds ancient carbon back into the atmosphere, resulting in a carbon positive life cycle. According to the annual carbon dioxide emission graph, historical emission profile rises by the Industrial Revolution, triggered in the mid-19th century. And currently, as we see from this plot, China, Europe, and United States are the major carbon dioxide emitters in the world. At the same time, average temperature rise is associated with greenhouse gas emissions. Last year, the average global temperature reached 1.2 Celsius above the pre-industrial level. It is expected to be 1.5 Celsius in 30 years and 3 Celsius at the end of this century. Unfortunately, there is an irreversible climate change risk above the 2 Celsius limit. And now let's mention about the widespread actions for combating climate change. Paris Agreement is a global action aiming to limit the global temperature rise at 1.5 Celsius at the end of this century. Green Deal of the European Union targets to create a European Union economy with net zero greenhouse gas emissions in the year 2050. The parties of these actions intend to reduce their fossil fuel usage and shift to renewable energy sources, such as biomass, solar, or wind. Also, we see that the number of energy efficiency, waste recycling, and carbon capture projects are increasing in number. I would like to emphasize on the effect of biofuels in mitigating climate change. The fuels produced from biomass feedstock are called biofuels. We see that there is a rich variety of feedstock, including forest residues, crops, green plants, and organic waste. And on the right, in the biofuel life cycle, carbon dioxide from the atmosphere is incorporated into the biomass by photosynthesis. And in the end of the cycle, this carbon dioxide is emitted from the engine. And there are still some carbon dioxide emissions in the life cycle. They can be minimized by integrating renewable energy solutions during feedstock pretreatment, biofuel production, and in logistics. In this section, I will be reviewing the actions of TÜBA R&D and Koç University TÜBA R&D Center on clean fuel research. I would like to say that TÜBA has a strong model bringing scientists and engineers together for high quality research. To look at TÜBA in brief, TÜBA is the first producer in Turkey's refining sector and the largest industrial enterprise in the country. TÜBA operates 4 oil refineries, namely in İzmir, Kırıkkale, and Batman, with a total of 30 million tons of annual crude oil processing capacity. The company headquarters is now in Istanbul, and there is a trading office located in London. TÜBA activities include crude oil supply, crude oil refining, and sales and distribution of petroleum products. Products of the largest volumes are diesel, gasoline, and jet fuel. Sustainability is prioritized in TÜBA from investment decisions to the operating mode. The sustainability targets of TÜBA are nourished by the United Nations Sustainable Development Goals. For example, under responsible production, there are projects in TÜBA for reducing the water footprint in the refineries, increasing the energy efficiency, for instance, by heat integration, recovering solid waste by industrial symbiosis, namely selling the solid waste to other industries, and improving the logistics infrastructure with the railway to lower the greenhouse gas emissions. TÜBA monitors the global actions and legislations and is aware of the increasing utilization of renewable energy and clean fuels. R&D is an important pillar in TÜBA sustainability targets. Let's talk about the TÜBA R&D Center. The 11-year-old TÜBA R&D Center builds its project portfolio in correspondence with TÜBA strategy and also considering the future of the oil and gas sector. There are 44 researchers with 9 PhD and 25 master graduates. The laboratory and pilot plant buildings contain more than 150 equipment and several dedicated areas for fuel analysis, material and catalyst characterization, reactor operations, pilot and lab scale, distillation and fuel blending equipment. And about the TÜBA R&D organization, we are working for 2 goals, profitability and sustainability. Profitability is to support the refineries with hydrocarbon characterization, material characterization, digital sensor and robotic technology development and data analysis, as well as to start commercializing novel solutions. Sustainability, on the other hand, is related to the research and development of new technologies for the future refineries. Those are not yet in the market. We have an agile organization structure. The whole R&D is a tribe, and there are 8 squads, you can call them teams, working autonomously, yet in very good alignment. Each squad is divided into portfolios representing the topics of the R&D strategy, For instance, a renewable fuels portfolio is under the Environmental Sustainability Squad. TÜBA R&D sets strong collaborations with national and international universities, research centers, small, medium enterprises, and large enterprises. Our projects are funded by in-house, the inside the company, national or international funding mechanisms. TÜBA has a joint research center with Koç University. I will talk about it now. Koç University TÜBA Energy Center was established 9 years before with the funding support of TÜBA. KUTEM is a hub of fundamental and applied research that is recognized internationally. It is also a practical school preparing grad and undergrad students for R&D careers in the industry. There are 3 laboratories, 3 main research fields in KUTEM, fossil fuel, biofuel, and solar fuel fields. Fossil fuel research concentrates on improving the efficiency of fuel production technologies and also developing processes to reduce greenhouse gas emissions. Biofuel research tries to use the non-food and non-feeds feedstocks such as algae, switchgrass, or forest residues for fuel production. And solar fuel research focuses on photocatalysis for the production of hydrogen from alternative sources. So far, KUTEM researchers have published more than 300 papers in these research fields. In this section, I will be mentioning about the 4 biofuel projects of TÜBA R&D, in which 3 of them are conducted in collaboration with KUTEM. So let's start with the European Union projects. TÜBA works actively in the European framework programs for research and innovation. So in the Horizon 2020 program, we were selected the most successful Turkish industrial company with 17 accepted projects and 7.8 million euro funding. Currently, we have 11 active projects. They are in the fields of carbon capture and storage, light hydrocarbon transformation, energy efficiency, water treatment, digitalization, industrial symbiosis, and biofuels. So I would like to give an example of our biofuel project. The IBAYA project has brought TÜBA together with 8 pioneering universities, research centers in Europe. In this project, pyrolysis oil and black liquor is going to be upgraded with a novel electrochemical method to be co-processed in petroleum refineries for the production of renewable transport fuels. About the TÜBİTAK projects, TÜBA has so far ran 3 TÜBİTAK projects on biofuels with KUTEM. So from recent to the old ones, in the first one, biofuel integration in refineries project, 2 PhD students at Koç University are working on the oxygen removal reactions from bio-oils to obtain renewable refinery feedstock. In the microjet project, we are in collaboration with Boğaziçi University, and we are trying to convert the microalgae oil into renewable fuel by the hydroprocessing routes. Hydroprocessing is a very basic route in a petroleum refinery, so we already know the technology. And the glycerol certification project is successfully completed. It was my doctorate thesis study. In that study, we used the glycerol from biodiesel and isobutene from petroleum refinery for glycerol certification to obtain glycerol ethers, which are used as renewable fuel additives. In this last section, I would like to share with you the outcomes of my PhD thesis on glycerol-based fuel additives. Esterification of glycerol is an industrially promising reaction as it produces the glycerol ethers that can be used as fuel additives, namely the fuel oxygenate section of fuel additives. And the desired ethers, as you see in the green frame, are the D and 3 ethers because they have better solubility in hydrocarbon fuels. We conducted a detailed catalyst screening study with more than 80 solid acid catalysts, including ion exchange resins, zeolites, and heteropoly acids. We selected the best catalyst candidates and also the catalyst candidates maybe for the possible application. And we also performed catalyst modifications and improving the bronzed acid strength resulted in improved desired product yields. And we made a study on the catalyst modification. We modified Imbalance 15 ion exchange resin catalyst by exchanging some of its protons with sodium. Acid strength of the remaining protonic acid sites increased with increasing sodium exchange. And we proved it with the FTIR-based methods, further validated by density functional theory calculations. We also performed flow reactors test for the first time in literature in this reaction, and we now have a patent on that. By providing this reactor operation, we, for the first time in literature, revealed that the desired products, the DN3 ethers, they are produced as the primary products in the reaction at high acid strength. And we also had a chance to compare the flow reactor with batch reactor operation and found out that a flow reactor is much more effective in terms of products yields. And blending the desired ethers in gasoline enhanced the octane number and reduced the vapor pressure. Power and emission tests performed in a gasoline engine dynamometer, again for the first time in literature, revealed the commercial potential of the glycerol ethers because they had sometimes superior performance compared to the conventional gasoline oxygenate, which is called methyl tertiary butyl ether. When concluding my presentation, I would like to summarize that the clean fuel technology approach of TÜBA R&D is enriched by the vision of young and qualified researchers who are following the emerging technologies, creating powerful research collaborations nationally and internationally, benefiting from the very strong research infrastructure, both in Koç University and in TÜBA, thus preparing TÜBA for the challenging future. Thank you, dear audience. If you have any questions, I would be happy to answer.
Thank you very much, Dr. Özge. Okay, we are expecting a few questions since we have 3 minutes more. You can either directly approach to her by writing direct message, either in Turkish or English, or talk to her via Zoom. All right, just to fill the gap, I felt a little bit more hopeful about our future since I have learned that large petroleum companies are now working on the biofuels, hydrogen, all the clean technologies. Especially we have some contributions from the Tüpraş, the largest petrochemical company in Turkey. I was not aware of these type of works because we considered the Tüpraş as just a solely dedicated to the petroleum, but I am really happy to hear about the ongoing research bits projects. Okay, questions?
Thank you.
Thank you.
All right. So now our next speaker is from University Le Mans, Dr. Salome Lamier. Salome Lamier holds a PhD from University, Salome Lamier holds a PhD in geosciences, and she has specialized in generation, migration, and fracturation of fluids. But as far as I understand, she is currently working in the GEOL Europe as an application engineer, where she develops new application skills on electronic microscopy. Stage is yours, Dr. Salome.
Thank you. So, do you see my screen?
Right.
Okay. So good morning, everyone, and thank you for being here. First, I would like to thank the TÜBA World Conference for inviting me for this talk, and more precisely, the Professor Samisen. So in this presentation, I will highlight the importance of the studying of natural fracture in the source rocks, and more precisely, the BIF vents. So just to introduce you, the work that I will present is a synthesis of my thesis work done over 3 years at Le Mans University and funded by the petroleum company Total. So as an introduction, I will briefly recall what a source rock is. We know that sedimentary basins are composed of several layers of rock with characteristics of their own. So one of these rocks, the source rock, has the particularity to be very clay-rich, and which induce a low permeability and then a strong anisotropy. Indeed, these rocks contain diagenetic fluids trapped in the clays. And moreover, the source rock has the particularity to be very rich in organic matter. So during the burial, with the increases of pressure and temperature, this organic matter will be transformed into kerogen and then into oil and into gas. So thus, the source rock will generate its own hydrocarbon and diagenetic fluids, better known as oil. So it is important to know that commonly in petroleum exploitation, the oil will be extracted not in the source rock, but in rock called the reservoir rock, where some hydrocarbon will have migrated. So this is what we call the conventional system. But at the beginning of the 21st century, another exploitation has been developed, and this time by extracting directly the oil in the source rock. Indeed, as you can see, it is important to know that only 2% of the oil migrates into the reservoir rocks, while 98% remained in the source rock. So those oil companies have developed a method of induced hydraulic fracking using horizontal wells, allowing to generate a porosity in the rock and recover hydrocarbons. This is what we call a non-conventional system. So in the simulation, if you take a look on the simulation model, the induced fractures are supposed to extend vertically, but the problem is that this rock also contains its own rheological barriers, the natural fractures. So taking natural fractures into account, the simulation models more look like this one. And you have to know that natural fractures can influence the propagation of induced fractures in different ways, either as barrier or as drains. In both cases, the induced fractures will be deviated from their initial patterns. So natural fracture influence the distribution of induced fracture, and it is crucial to understand that distribution within the source rock. Just as a reminder, source rocks contain fluids, and these fluids will promote the development of natural hydraulic fracturing. Within the source rock, we often find a family of fracture, very atypical, parallel to the bedding, filled with fibrous calcite and containing hydrocarbons. They are commonly called BIF vents. Because of their horizontality and recurrence, their study is essential for the oil exploitation of the unconventional system. So now, if we look at the distribution and referencing of these calcite vents worldwide, we notice that they are located exclusively in organic rich rocks in sedimentary basin, and more specifically in mature source rock. What I mean by that is that this rock have already generated some hydrocarbons. The blue point on the map that are not located in mature bedrock areas are areas where the maturity condition of the source rock are not known from the literature. So we can conclude that it is important to emphasize that we have a first order link between the BIF distribution and hydrocarbon generation within the source rock. So for our case of study, the study of the calcite vent is therefore important for industry and fundamental. It's important for industry because the BIF are located in source rock of economic importance and will influence the exploitation of oil. And for the academic world, because of these vents are paleomarkers of the history of the basin, whether for paleostress, rock fluids interaction, and the timing of the hydrocarbon generation. Thus, in this presentation, I will try to synthetically answer to the three main issues below, namely, what are the parameters controlling the distribution of BIF? What are their spatial morphologies and distribution in 1, 2, and 3D? And can we better constrain the origin of the fluids fed these vents? And what is their timing in the history of the basin? To do this, during my thesis, I performed a multi-scale and multi-proxy analysis of BIF for one case of study, the Vaca Formation, located in the Neuquén Basin in Argentina. So our case of study is in the Neuquén Basin in the South America, located in the south part of the subduction zone of the Andean Cordillera. This sedimentary basin has three potential source rock. The oldest one is the Los Moles source rock, mainly overmature and therefore without economic interest for the petroleum companies. The second one is the Agrio Formation, which is mostly immature and therefore generates few hydrocarbons. In these two source rock, almost no BIF has been found. The last one is the Vaca Formation, which is located from the oil and gas window, depending on its location in the basin. And it is notably very rich in organic matter and produces a lot of gas, which makes it a world-class source rock, widely studied and exploited by the oil majors. It is also a very high concentration of BIF, making the best candidate for the study of our BIF vents. That's why we chose this source rock. So now talking about these BIF vents. We first investigate the distribution of BIF over 650 meters of sedimentary cores on 10 different wells by surveying a detailed log. It's important to say that the wells cover the beginning of the oil window with a vitreous reflectance around 0.6% to a dry gas window with a vitreous reflectance around 1.8%. We were able to identify three characteristic BIF families. Micro-BIF with a lenticular shape and a length for less than 5 centimeters embedded within mudstone. Macro-BIF, which are divided in two subfamilies. First one are BIF inside, which are located within the same facies. And second one, BIF at interfaces, which are located at the sedimentary interface of two facies. This different fracture family seems to be controlled by different parameters. So which one are they? For that, we perform a statistical analysis BIF distribution. And sorry, when we focus only on the macro BIF, it appears that for each well, they are preferentially located at the sedimentary interface, whether within the same facies. Thus, the sedimentary interface creating a zone of weakness and will facilitate the establishment of this fracture. If now we look at the micro-BIF, it appears that they are distributed in facies with the higher organic matter, and therefore hydrocarbon generation represented here by the TOC, which is the total organic content of the source rock. The micro-BIF are therefore created by the fluid overpressure and caused by the increase in volume of the fluid during the oil generation. So to sum up, the facies interface creates a located zone and helps to locate located micro-BIF location. And the TOC will induce the hydrocarbon generation and it will induce fluid overpressure and favorize the micro-BIF location. So now if we take a look on the maturity, and if we look at the number of micro-BIF per meter in light brown on the graph and the cumulative thickness of micro-BIF per meter in dark brown as a function of the maturity of the well, we can see that the thickness and frequency of the BIF increase with the maturity of the rock. Thus, for the source, the more the source rock will generate hydrocarbon, the more the overpressure will facilitate the generation and the opening of fractures, which will fill with the calcite and will form the BIF vents. Regarding the internal morphology of BIF observed with an optical microscope, it appears that these vents provide information on the tectonic stress during their generation. Indeed, by the deformation of its calcite fiber, the BIF records the paleostress and the direction of the deformation. Moreover, mainly BIF shows several generations of calcite, materialized here by arrows, dark and red, of different colors on the image, indicating that this fractures was reopened and enlarged at several times during the history of the basin. BIF is generally composed on its center by a median zone, shows symmetrical growth on either side of this zone, with growth from the median zone toward edges. However, some BIF, like this example, show growth only on one side, and it suggests a difference in rheology between the two edges. So BIF record tectonic stress and several generations take place in several times during the basin history. Now, if you want to constrain the spatial distribution and the morphology of the BIF, we went to the field to observe the outcrops of the Vaca Muerta in the Neuquén Basin in order to better understand their morphology. So we also performed a sedimentary and fracture log in 2 canyons, 300 meters apart. It appears that some BIF cross both canyons and those have lengths exceeding 300 meters. This category of BIF has been called the continuous BIF. Whereas the second category, this time called discontinuous BIF, present lenticular shaped fractures grouped in TOC-rich areas. And we reproduce one of these 2D canyons in photogrammetry in order to have a 3D view of this fracture and faults. So it appears that the discontinuous BIF are always less than 10 meters long. So to conclude, once again, 2 different factors will influence the distribution of the BIF. The continuous BIF will extend over several hundred meters along the sedimentary interface, while the discontinuous BIF are smaller and located in areas of fluid overpressure induced by hydrocarbon generation. So when we look at the composition of BIF, it turns out that they are mostly composed of calcite. Several studies, which I will not detail in this presentation, show that the calcite come from the dissolution of the coccolith present in the matrix of the Vaca Muerta formation. But nevertheless, some of BIF present in smaller quantity of crystal of barite, attesting a hydrothermal origin. Other BIF are composed only by crystal of gypsum, coming for their part from the leaching of pyrite present in the matrix. The fact that there interest all the fractures suggests a late setting in the history of the basin during the uplift. So there is different fluid origin that fed BIF during their generation and formation. Talking about fluid origin, the observation of coexistence of aqueous and hydrocarbon primary fluid inclusion in the same generation of BIF shows that BIF take place in mature environments during the oil and gas generation. If we plot the diagram salinity versus the methane concentration in different fluid inclusion, I mean aqueous and hydrocarbonate, BIF and transverse vein display a limited range of methane concentration, suggesting a common source of methane with an intraformational fluid. But regarding the salinity data, both of BIF and transverse vein, which are transverse vein, which are the other natural fractures found in this formation, are saltier than the marine sea water. This high salinity range can provide this high salinity range can possibly be explained by the leaching of the retrained formation or probably by the Aquico formation, which are 2 evaporite deposits. The most likely solution is a contribution from the Aquico formation with its gypsum dehydratation in anhydrite during the burial. In addition, several hundred meters of shale of the Aguillo formation are between Witran and the Vaca Muerta formation, and it will create a very low permeability sealed rock. Coupling aqueous and hydrocarbonate fluid inclusion, we can propose a turbobarometric history of calcite veins studied in an outcrop and using the model of Catalano et al. 2018 for the burial history. There are two scenarios. In the first one, pressure and temperature record burial stage, and the second one, the data pressure and temperature record the progressive exhumation stage. Alternatively, both stages are recorded. So during exhumation, therefore, fluids over pressure are not the primary mechanism for beef placement, and it is therefore likely that it is the tertiary tectonic stress that have favored the development of these horizontal fractures. So in order to better constrain which kind of scenario we can choose for the timing of generation of this beef vein, we perform very precise analysis on the oxygen isotope over an entire thickness of beef to see if variation in temperature or fluid composition were recorded during the growth. The results show a clear cooling from the median zone toward edges. In order to know if it is a variation of temperature or a composition, clumped isotope analyses were done in parallel and also show a cooling towards the edges, going from 177 degrees in the median zone to 77 degrees at the level of the last calcite generation. So, in addition, very weakly negative oxygen isotope values suggest that the last fluids inputs were of meteoric origin during the advanced exhumation. So we can conclude that beef were therefore set up at different times during the basin history. So first during burial, as attested by several fluids inclusion results, and may have been reopened during the exhumation of the basin, marked by the compressive episodes, as attested by the deformation of calcite fibers, the result of oxygen isotope and the clumped isotope. So to conclude, beef are vertical barriers, but could also be horizontal brain for the intraformational fluids in a closed system. The main controlling factor of beef are the high TOC area, the organic matter maturity, and also the lithological interface, especially ash beds. And areas with multiple lithological interface, like ash bed, will favor horizontal fracture over large areas in 2 or 3D, and we could have continuous beef. Whereas more discontinuous beef under more uniform will take place under more uniform TOC-rich lithologies, like the mudstones. For the fluid origin, the first generation is fed by an intraformational fluid during the burial in the oil and gas window, whereas the last generation is more a mixing of the intraformational and meteoric fluids during the exhumation. Beef then takes place from the beginning to the early oil window, around 160 million years, and no later than the Miocene, around 47 million years. So fluid overpressure is the main mechanism for beef generation in the oil and gas window. Most probably, the high influence of compressive stress for beef will help of the generation during the uplift. And you have just for the take-home message is that beef are a major geological feature to constrain the history of source rock and in the sedimentary basin. So thank you for your attention.
Thank you very much, Dr. Salome. Okay, we have 1 or 2 minutes. We expect some questions from audience. It was a really interesting talk. As a chemist, as a chemical engineer, I have seen that how a careful observation from a minute data such as talk, geochemistry, some fluidic structural changes, pressures, years, how can you lead to much larger valuable information? It's a good study, Salome.
Thank you, thank you.
Okay, I expect questions.
I have any questions.
Yes.
Thank you very much for interesting presentations, Salome.
Thank you.
I want to ask you about are deep veins contribute or not contribute to the shale porosity formation?
I think it will be contribute because they are the main maturity marker of a source rock. So I think it will be contribute.
Thank you.
All right. Thanks again, Dr. Salome. Our next speaker of this session, Dr. Shamil Sen, my dear friend from University of Istanbul, Cerrahpaşa. And he holds a PhD in geology. He has worked for Vermilion Energy and Turkish Petroleum Company. And now he is holding associate professorship at the Istanbul University, Cerrahpaşa. Okay, stage is yours, Dr. Shamil.
Thank you, Professor Boss. My talk is related with shale porosity and shale porosity prediction based on machine learning. Okay. I would like to start with definition of shale. Shale is thin granite and organic rich sedimentary rock. Left photo shows Dada Shale of the Derindere 1 well. According to the 2008 Time magazine cover photo, shale could power of the world. Shale is very important due to source of the oil and gas, both unconventional and conventional. Topsoil to conventional hydrocarbons, unconventional oil and gas reservoirs, and most importantly, vital to carbon dioxide storage, mainly because carbon dioxide storage is possible under or inside the shales. Shale has three types porosity: matrix porosity, organic porosity, and natural fracture porosity. A and B photos show matrix porosity. C and D photos show organic porosity, and right photo shows natural fracture porosity. Attention please, black areas of the A, B, C, D photos are pores. Clay porosity is less than 3.6 nanometer and organic matter porosity is less than 5 nanometer. Natural fracture porosity is millimeter scale and can be seen in the right photo. One column shows shale, second column shows millimeter scale pores. Attention please, black lines are fracture and pores. For correlation aims, coronavirus change 80 to 100 to 20 nanometer in diameter. Therefore, shale porosities are smaller than coronavirus. Shale porosity forms a complex processes, including mechanical compaction, chemical compaction, diagenetic reactions, cementation, and oil gas formation process related with maturity of organic matters. There are different methods to measurement of porosity. One, mercury interaction Kepler method. Two, scanning electron microscope. Three, nitrogen absorption method. Four, NMR method. Five, helium porosimetry method. It is important to note that standard protocol to the porosity, shale porosity measurement is helium porosimetry method. However, the hydrogen helium porosimetry method is very expensive and time consuming. Thus, aim of this study is to determine shale porosity based on deep learning method. I have created a data set which contains 11 variables and 286 instances from 19 wells of volcano shales of world. These are Barnett, Marcellus, Utica, Eagle Ford, Highness Vale of United States, Second White Spix, Belle Forte, Duarney of Canada, Macamurta shale of Argentine, and Longmaxi shales of China. This table shows variables of the data set: age, burial depth of shale, age of shale, total organic carbon percent of shale, within reflectance based maturity of shales, quartz content, feldspar content, carbonate content, pyrit content, sorry. Mineral based pyritness index, and porosity, helium porosity. Attention please, porosity of shales range from 1.6 to 10.5. Mean is 4.9. Shale particles, shale porosity properties are small, and shale porosity percentages are small. For example, for a sandstone, porosity percentage can be up to 40%. In this study, supervised deep learning method has been used to porosity prediction using neural designer software. You know that data preparation is important section of the machine learning, and I have give more importance to the data preparation. And for example, I have excluded less than 1% TOC and less than 1.5% porosity. After data preparation, I have uploaded the data set to the software. I have used minimum maximum normalization method to data normalization. 60, nearly 60, nearly 20, and nearly 20% of data has been used as training data, selection or validation data, and testing data respectively. I have select main secured loss index and I have performed training using Quasi-Nifto algorithm method. I have applied to the Crude method linear regression analysis. After analysis, I have created or deployed Python model. Porosity top correlation chart suggests that H, quartz content, feldspar, clay and content, and mineral-based Burdens index caused a decrease in the porosity, whereas TOC, carbonate, burial dip, within reflectance maturity, and period content caused the increase in the porosity formation. I have formed a neural network consisting of 2 layers and 7 neurons. You can see variables or inputs and targets in this picture. H, burial depth, TOC, within reflectance, quartz, feldspar, clay, carbonate, period, and mineral based Burdens index are inputs, and porosity is output. Best Quasi-Newton method error history has been formed by this neural network of 6 neurons and 2 layers. After the training, validation, and testing processes, real and predicted porosity linear regression analysis chart has been created, and linear correlation coefficient using the neural network, the neural network parameter was predicted as 90.4% It is important to note that This data set based linear correlation coefficient shows overfitting. I have not used any data augmentation process during training, selection, and testing process. I believe that after that data augmentation, the coefficient will reach to the 99%. Linear correlation coefficient was quickly predicted as high as 90.4% from the dataset of standard exploration and production activities of the petroleum sector, because the dataset have been created by standard petroleum AP activities. You know that abundant natural gas resulting from the shale revolution has especially helped reduce US carbon dioxide emissions by displacing coal-powered plants to producing electricity. Porosity quantification based on deep learning will help to produce more clean light oil and gas from unconventional shale plays, because oil companies that use deep learning and similar technologies focused on light oil and gas, because unconventional method that use data mining and technology-based technologies made possible these processes. It is importantly, carbon dioxide capture and storage technology, is regarded as a promising method to cut down carbon dioxide emission, which can lighten global warming significantly. I am looking all important journals and papers about this concept. I think that you also see similar papers and works. Therefore, deep learning-based porosity model could supply data to increase and manage of carbon dioxide storage capacity. Thank you very much.
And thank you, Dr. Shamil Sen. You have been right on time, actually 2 minutes earlier than your projected time interval. Anyway, do you have, we expect some questions from audiences to Professor Shamil Sen. Okay. Apparently, there is no question, Professor. I would like to thank to all the participants and the panelists for this helpful and intriguing, enlightening talks. Okay, we expect you to see in the next sessions. Goodbye to everybody.
So good afternoon, ladies and gentlemen. Thank you for attending this TÜBA World Congress on Energy Science and Technology. This is Meng Ni from Hong Kong Polytechnic University. So I'd like to chair this keynote session. So in this session, we have two speakers, two well-known speakers. So one is Professor Anvil from Arizona State University, United States. And his presentation title will be Pathways to Sustainability in an Increasing Water Scarce World. So Professor Anvil is a well-known expert in this water area. I think without further delay, I'd like to invite Professor Anvil to deliver this keynote speech.
Thank you very much, Professor Meng Ni. I hope you can hear and see me.
Yes, I can see you and can hear you clearly.
Thank you very much. It's a privilege to be able to address such a distinguished audience in this session. And I will be talking about water scarcity, food, and its linkages to the sustainability pathways into the future. And I will be trusting on the audience to make the linkages from this presentation to the energy issues. And with your permission, I would like to share my screen and present a PowerPoint file. Can you please confirm that you can see the presentation?
Yes.
Thank you very much. I will be covering the topic in 5 sections. I would like to give the definitions, the basic definitions at the beginning. Then I would like to talk about what kind of future that we have committed ourselves to. And then want to give you a status report as to where we are. And then would like to provide you some projections and scenarios, pathways, if you will, according to different directions that our leaders might be taking us, and have a closing section with the outlook that I see for our water, food, and sustainability future. Let me start with the definition of food security first. Food security means that everyone at all times would have physical and economic access to sufficient, safe, and nutritious food that meets their dietary needs and food preferences for an active and healthy life. And this is an official definition that was accepted by all governments in 1996 World Food Summit at the in Rome, Italy, during the UN Food Summit. So as the definition indicates, there are 4 pillars to food security. The first pillar is availability, which is the physical supply aspect. It means that we have to be able to supply food, enough food, both in terms of quality and quantity. But availability is not a guarantee for access, which is about the social and economic factors and conditions. So the second pillar is for the accessibility of the food, which has been made available. So we have food that is available, and we have everyone who is able to access this food that is available. And the third pillar is utilization, which relates to the safety of the food. So we have the food available and accessible, but it has to be safe and nutritious for the use by human metabolisms. And the fourth pillar is stability, which means that all these three pillars should be stable. They should be present at all times and not at some time for some people or for some region of the world. This has been also confirmed by the earlier approval of the human right to food by our governments. Over 170 countries have ratified the International Covenant on Economic, Social, and Cultural Rights as of 1966. And over 30 countries actually have added the human right to food in their own constitution. Then comes the definition of water security, which is relatively recent, coming from the United Nations, from UN Water in 2013. And I have to add that I am proud to have been a member of the team that developed the definition of water security, which follows the same principles. So water security is the capacity defined as the capacity of a population to safeguard sustainable access to adequate quantities of acceptable quality of water for livelihoods, human well-being, and socio-economic development, and for ensuring protection against pollution and water-related disasters, such as floods and droughts, and for preserving ecosystems in a climate of peace and political stability. As you say, this is basically sitting on a similar four pillars, but it's broader and it links to funding and political stability, governance, and cooperation. Like human right to food, water and sanitation have been recognized as human rights, but relatively recently. As a matter of fact, last year we celebrated the first decade or the 10th year of the recognition of the human right to water. And that was a United Nations General Assembly resolution. I have provided active links in my presentation in case some of the participants would like to access these documents and look at them. Okay, so these are the basic definitions. So what kind of future do we want? When I was a small kid, the Jetsons was one of my favorites, along with later on Star Trek. So that was quite futuristic, and all was based on mostly technology and how technology could potentially make our lives easier and our quality of life high. Whereas the future, the outlook that we have nowadays is as on the picture on the right hand of the screen. This is the cover page of the United Nations Environment Programme's Global Environment Outlook, which came out in 2019. And as you see, there is some technology in it in terms of clean energy, for example, but it's all about a clean environment, sustaining our environment, and adapting to a lifestyle that will protect and enhance the quality of our ecosystems while serving our development needs and socioeconomic requirements. And the international community and the United Nations system have responded to this through a number of global arrangements, conventions, and agreements. One is about food security, which I talked about earlier. There will be a food system summit in a couple of months in Rome, Italy again, but on a global scale and for multiple sectors. We have agreed initially on the Millennium Development Goals and most recently on the Sustainable Development Goals, which covers not only the objectives of the humankind in different sectors and towards a sustainable future, but very concrete targets and their indicators for these targets. The goals that I would like to cover here is about hunger, which is today SDG number 2, but during the Millennium Development Goals era, it was basically reducing hunger. Now it's ending hunger. And SDG number 6 is about drinking water and sanitation. And again, Millennium Development Goals identified a meager, a modest objective to increase access for half of those who did not have access at the time. And now the humankind, the international community, has committed itself to providing access for drinking water and sanitation to everyone. So that is basically how water security has been defined. And then there are targets regarding combating land degradation and reaching to a stable state in which no further land degradation occurs, protection and enhancement of biodiversity, and integrated water resources management that allows for all sectors to be a part of the planning and management process. So these are goals and targets that have been globally accepted by all our governments. And these are obviously promises, but when governments promise, they are monitored and they have to report. So as the sketch on the left indicates, those promises do count. And obviously, as the general public, we want to know the truth. And the truth so far is not very encouraging. It indicates that we are not in the right direction for some of the major promises that our governments made. The first one is about zero hunger, eliminating hunger. And as you have seen in this chart, as of 2015, when the Sustainable Development Goals were adopted by all of the governments of the world, they committed themselves to ending hunger. But unfortunately, and ironically perhaps, 2015 was the year when the trend of declining hunger ended, and we have been seeing a rise in the number of hungry people since then. And obviously, the COVID pandemic did not help this. And according to initial estimates, COVID will have added anywhere from 50 to 100 million more hungry people to those who are already hungry. And when we look at the specific targets of the Sustainable Development Goal number 2, for example, the first target is ending hunger and ensuring access by all people. And the trend assessment is one of deterioration, which means that we are moving in the wrong direction, okay? Target 2.A, for example, is about investment by our governments into ending hunger, including infrastructure, agricultural extension and research, technology development and cooperation. And the trend assessment as of this year is again one of deterioration, which means we are in the wrong direction. When we come to the commitments in terms of water, the situation is less negative. At least the direction is not negative. We are not in the wrong direction, but we are not fast enough. For example, for basic drinking water targets, if we want to provide the very basic services to everyone by 2030, the progress right now, or the business as usual, should be dropped and the speed should be doubled. And this is only for the very basic services. But if we want to keep the promise of the Sustainable Development Goal number 6, which is to have quantum jump and not gradual increases. The only target that is being reached in terms of sanitation is the open defecation target. The international community committed itself to eliminating it altogether in 2030, and the current speed, and thanks to the efforts, particularly in countries in Asia, such as the big efforts by India, this target seems to be on track. But sanitation, just like drinking water, for very basic sanitation, we need to increase our speed by 200%. And for providing safely managed sanitation, we have to increase the speed by 400%. Again, we need a jump. We cannot do gradual increases to reach out to that. Coming to the management of water, the international community again committed itself to the integrated water resources management. And IWRM has been on the international agenda since the Rio summit, okay, the first Earth summit. So it's not something that is coming online recently, and it has been a target. And as of 2020, in order to reach the IWRM targets, we have to double the efforts. Again, gradual increase will not do that. When we look at the land resources, and particularly land degradation and the protection and enhancing the biodiversity, terrestrial ecosystems, again, we are way off track compared to the targets that our governments have committed to achieving. And for example, one of these targets was about wildlife trafficking. And obviously the international community was way off track. And we now know that COVID-19, when it first started, it was started through wildlife trafficking, through possibly pangolins, and then going to other animals and eventually people. Another major target that our governments have committed is the land degradation neutrality target, which is extremely important for the sustainability of the whole world. It's not only for food security, but land degradation has an impact on everything, including a major impact on climate change, obviously, and the health of our ecosystems. And again, we are off track in terms of achieving the land degradation targets, although more and more countries, about 127 countries as of the end of last year, have committed to setting targets for land degradation neutrality, but they have to deliver towards these targets. So let's take a look at the projections and some global scenarios in terms of water and food security. And there is a number of scenarios around, ranging from those by OECD, the World Bank, United Nations Development Program, and when it comes to food security, the most recent scenarios have been developed by the Food and Agriculture Organization of the United Nations. And I am happy to share with you that I was a part of this scenario work, and the scenario work has been published in 2 volumes. One is about trends and challenges, and the second one is alternative pathways to 2050. And in the alternative pathways, we looked at 3 different scenarios. One is business as usual scenario. The second one is a scenario of sustainability, which we called TSS, or Towards Sustainable Societies. And the third one is called SSS scenario, which is short for Stratified Societies scenario. Business as usual is what we have been doing. And as I indicated earlier, the business as usual is not taking us where we want to be, okay? And by 2050, we are already projecting that the global food demand will increase by 50%. So we need to provide 50% more food in order to satisfy this demand. And we don't have 50% more water or 50% more land to do this. So we are gonna need to be very much efficient and much more wasteful, eliminate loss and waste to the extent possible. And while doing this, look after the bottom line of equitable distribution of food to provide for food security, and look after our ecosystems and our greenhouse gas emissions. So business as usual is not taking us there. And the sustainable society scenario is the one that has been designed to take us there. But the third one that takes into account the signals, the socioeconomic and particularly political signals that existed 2 years ago when very recently, obviously, when we made these projections, which is basically can be summarized as every country and everybody for themselves. Okay, there is very little cooperation, very little care given for equitable distribution of income or food or land, and everybody wants to maximize their food production without taking into account the need for international cooperation for global issues such as climate change, such as biodiversity loss, and such as land degradation. Okay, and the scenario work. I am not going to go into the details of the scenario work, but the business as usual scenario, unlike most scenarios, is not the worst case scenario here. It's the middle of the road, if you will. The worst case scenario is the stratified societies. If the political signals of everybody for themselves, every nation for themselves, making your own country great without caring for others and global issues, that is the worst case scenario, which might actually happen. So in the sustainability scenario, land use intensities are kept out in control, and efficiencies and productivities are increased substantially, and water abstractions are limited to a smaller fraction of available water resources than what is happening in the business as usual scenario, which means that we have to be using our water a lot more efficiently and productively. In the stratified society scenario, on the other hand, water is not sustainably used, and countries continue to extract water resources in an unsustainable manner, whereas they pay little attention to the efficiency of their water use. They basically target productivity, high production levels, high yield levels, and this may lead to extending the agricultural land, converting land for agriculture, which leads to further climate change, and obviously needs more use of water resources. And as a result, the land degradation increases substantially, as you are seeing in this chart. The red line shows the stratified societies scenario, which basically maximizes land degradation and greenhouse gas emissions, whereas the sustainability scenario maintains a manageable and achievable target that is in line with sustainable development goals. I have to indicate here that both business as usual and stratified societies scenarios, they increase irrigated areas, okay, in order to cater to the increased need for food supply, whereas sustainability scenario actually decreases irrigated areas, intensifying agriculture in the existing areas, and definitely not expanding on that, and substantially increasing productivity and efficiency, water use efficiency at the same time. As a result, and you are seeing that for different regions of the world, we have the projections provided for irrigated areas. And this graph chart shows the greenhouse gas emissions from agriculture. As you know, agriculture emits approximately 1/4 of the global total greenhouse gases, and that needs to be decreased substantially. Again, as you see in these charts, the business as usual scenario will continue to increase the agricultural GHG emissions. The sustainability scenario will decrease towards a manageable and achievable level if appropriate measures are taken. And the stratified societies, everyone going for their own national or personal or community level welfare, the GHG emissions will go way higher than the business as usual. Again, this is not for the lecture, but for possible use by the participants if they would like to see the implications of each scenario on the per capita income, the total agricultural production, the population implications, and the price, food prices. In the end of my presentation, I would like to talk about the prospects. Okay, so I just presented the scenarios. So these are possible pathways, and it's up to us and our governments and the leaders, both in governments, civil society, and businesses, in terms of taking the right path into the future. And it has to be done pretty much now. It should have been done yesterday, but better late than never. But obviously the clock is ticking. So what I would like to do is tell you about the prospects in order to address the scarcity and the quality erosion of land and water resources in a sustainable manner. And I will present 5 headings for this, again, without going into much detail, but I wanted to provide the detail in the slides. The first and probably foremost, the others are not less important, but this is key. Agriculture should be intensified sustainably in order to save land. Okay. We don't have the luxury to convert land for agricultural purposes anymore. And instead, we have to intensify, but intensify it sustainably, which means that in some places we will have to go for low input agriculture and maybe use the land for protection and conservation purposes rather than to increase the agricultural production. And in other places where this is sustainable and feasible, we increase the production through double cropping, triple cropping, and definitely through diversification of agriculture, and not through the monocropping, which is the prevailing mode of production right now. Number two is land degradation, combating land degradation. And this is, as I indicated earlier, this is absolutely necessary. Many of us may not understand the severity of land degradation unless it touches our lives. But on a global scale, land degradation is one of the top global problems that might be leading to a disaster. Okay, there are plans, as I indicated, targets and commitments by governments in dealing with land degradation, particularly through land degradation neutrality, and that is an absolute necessity. Number three is an increase of efficiency in the use of water resources, and this has to go beyond rhetoric. It's not only about technology, shifting our technology to water saving only, but to save water and use it more efficiently in all sectors, ranging from production at the field level to industrial use of water and the use of water for domestic and energy purposes. And that is absolutely necessary. And we need to go beyond acknowledging it, but actually implement it everywhere. The fourth is accepting the trade-off between yield and sustainability, which means that unplanned, unsustainable increases in yield jeopardizes the sustainability and our future. And we need to be aware of that and manage the trade-off in a planned and very much aware manner, okay? And not to the benefit of production, which has been the case in the past to a large extent. And number five, last but not the least, is an investment increase in land and water resources and in making our use of land and water resources sustainable, efficient, and productive, and which covers not only the practices or infrastructure, but also institutional capacities, development of technologies, supporting research, and improving our governance structures. This is a spoiler for a report that is coming out of Food and Agriculture Organization in December this year, and it will be providing insight into the implementation of what I have just summarized within the past 35 minutes. So in closing, there are my take-home points is number one, renewing commitments and anchoring the commitments to national plans, international cooperation by all governments, reforming governance systems, reconciling ecosystems and production, and going away from incremental change and make a jump in making the change the paradigms, and make it happen now. And last but not the least is money, money, money. And thank you very much for your attention. And with this, I would like to go back to the conference room and give the floor back to the chair.
Okay, thank you so much, Professor Okan Anwar. Thank you so much for your very nice presentation and sharing with us your insights in the land, water, and food issues. I think these are very urgent global issues, and they are closely related to each other. So I think, well, now I think it's a very good chance for our audience to have communication with Professor Unwell. Actually, Professor Unwell was the Vice Chair of United Nations responsible for water. And he is also a fellow of International Water Resource Association. So Professor Unwell is really a leading expert in this area. So are there any questions from the audience? Oh, I see there is a question from the audience. Oh, from Professor Dinser. Okay. Can you see the question, Professor Unwell? Maybe I can read it for you. Many thanks for such an eye-opening talk. The question is, the situation has gotten worse with pandemic and climatic events. Do you think that there is enough political will to overcome food and water shortages for people living in poor countries?
Looking at it, this is a very good question, and thank you very much for asking it. The political will is partially there because safe water is and has been and will be our first line of defense against pandemics. It was a first line of defense against COVID, and it will remain so. It will also be necessary for, fighting with future pandemics, but also producing food and healthy lifestyle. So having said this, I think the political leaders have understood the value of water, but and the United Nations and many international organizations have been advocating greening the recovery programs and building back better, meaning that we should be investing into the recovery from COVID in a green manner as sustainably as possible. If the question is, are we doing this adequately? No. There is a global observatory of COVID recovery managed by the United Nations Environment Program and Oxford University. And according to that, only 26% of the recovery packages are green. Since this conference is being organized by the Turkish Academy of Sciences, I have to add that Turkey is one of the very few countries whose recovery package has been particularly deliberately designed as green. So as a Turkish citizen, I'm actually proud to report this. However meager, however modest the recovery package of Turkey was towards COVID, it was designed to be a green recovery. And this, I think, is exemplary for other countries to learn from.
Okay, thank you, Professor Anwi, for your detailed answer. And also thank you, Professor Dinser, for your question. Very inspiring question and very good explanations. And thank you. I think we may still have a little bit time. So if audience have questions, you please use the Q&A, or you can use chat to type your question. Maybe just a short question if you have. Okay, I think if there are no questions at the moment, Professor Anwi, I believe later on some audience may send you email or contact you by other means to to ask questions. So let's thank Professor Anwi again for your nice presentation. Thank you. Yeah, and have a good day. Okay, thank you.
You too. Bye bye.
Bye bye.
Bye bye.
Okay, dear audience, so let's move to the next speaker. So the next one will be delivered by Professor Henrik Lund, who is a Danish engineer and a professor in energy planning. in Denmark. He is a highly cited researcher and editor-in-chief of a highly impact journal, Energy. He is also author of more than 400 books and articles, including the book Renewable Energy Systems. I'd like to invite Professor Henrik Land to deliver the keynote speech. I think Professor Henrik Land is busy for some other things, so he pre-recorded his presentation. I think our IT colleagues will help play the pre-recorded video presentation. Sorry, there could be some technical issues, and we will fix very soon.
Welcome to this plenary keynote on 100% renewable and carbon neutral smart energy systems. It's my pleasure to be here and make this presentation. It will be based on the Danish case, where we have a political target of decreasing carbon dioxide emission by 70% already by 2030. Let me start by introducing myself. I come from Aalborg University in the northern parts of Denmark, and since you cannot see me due to the presentation here, I put in a picture of myself. It's interesting to come from the northern part of Denmark, and Denmark in general, when we talk about how to make the green transition and how to decarbonize countries, because we have been carrying on a lot in Denmark in expanding our renewable energy share. Right now, 50% of our electricity supply is produced on wind power, and we have also additional to that a lot of district heating around the country. 50% of our heating is from district heating, utilizing a lot of excess heat from industry and also from the electricity production, the part that is not on wind power yet. One recent development that is maybe not so much known is that we also started to transfer our natural gas supply into green gas, and right now more than 10% of our natural gas is actually being produced as biogas mainly from manure and organic waste from industry, and that is also being expanded. It's expected to be even 30% within the next decade. Some of the things that I will talk about today, you can read more about in my book, Renewable Energy Systems, that I have a new second edition from 2014, in which there was also a chapter on smart energy systems and infrastructures. That is an important part of what I will be addressing today. The starting point for this presentation here is the political aims. Here's a slide on what we have been deciding in Denmark, but it's similar aims that is in Europe and many other countries around the world. That is to decarbonize our energy systems and go to renewable energy. In Denmark, we have started having on this type of objectives already in 2006, where our Prime Minister at that time formulated that we should be totally free of fossil fuels in the future. And a number of governments, even since then, have supported this long-term targets. So in Denmark, we have the interesting situation. It's not only supported by various governments in a long row now, but it's also supported by a huge, and I mean a huge majority of the parliament. So it's an aim that stands pretty strong in the political debate and decision making. And it's also something that is not only a long-term aim, but also a lot of measures have been taken and initiatives have been taken to implement it. One of them being that we expanded the share of wind to 50% by 2020, and that's actually something we have already achieved. As the latest step on this, the government that started last year, they made an agreement again supported by a huge majority of the parliament to have a target to reduce the Danish greenhouse gases by 2030 with 70%. As down to 30% of what they used to be in 1990, according to how UN define this and how they measure it. And that's sort of the target that I will speak about today. I mean, it's very good that we have politicians and parliaments that decide for 100% renewable energy or fully decarbonized society, but how should we do it? That's something that we work with at our university, but also the industry in the energy industry in Denmark. And just a little bit about how we have been working with it in my research group at Aalborg University. We have for many years, and also from way before it was an official target of the governments, we have worked with how to transform our fossil fuel industry and energy supplies into new green energy supplies based on renewable energy. In our research groups, it dated back as long as in 1976. You can see a small title to the upper left corner. 1976, one of my colleagues was involved in drafting what was the first alternative energy strategy in Denmark, an energy strategy that promoted renewable energy instead of going for fossil fuels. And at that time, it was also debated with nuclear. And we have been engaged in a number of such alternative strategies throughout the years. Since 2006, we have joined forces with the Danish Engineering Society, where that sort of is a union for all engineers in Denmark. And together with them, we have promoted strategies to set the agenda and to promote that the government have an active strategy. In 2006, the government in Denmark did not have an active strategy, and that was something we promoted, and afterwards the government have had, as I just mentioned before, and the parliament, a very active strategy. We think there are a number of good reasons for this. One, of course, is to decarbonize the societies for pollution and environmental reasons, but we also think there is an issue with being depending on fossil fuels. We produce fossil fuels in Denmark ourselves, natural gas and oil from the North Sea, but it's running out, and somehow we have to do something without it, and either we will convert to renewable energy, or we go back to the 70s, where we are depending on importing a lot of fossil fuels. But there's also the business potential that is very essential. We have a lot of strongholds in research and industry. The wind turbines is very well known, but we have a lot of energy industry, and that's also where we being Denmark can make a living in the future when we involve us in that. So we have been involved with a number of NGOs and so on, and the government to identify and formulate and propose strategies on how to convert into 100% renewable energy and decarbonize the Danish society. The way we work with it is that we use a computer tool we have developed here at Aalborg University. It's called Energy Plan. It's a freeware, everybody can download it, and also the results I will show in a minute can also be downloaded, both the data and the input and so on, and the models, so everybody can calculate for themselves and also change if you wish to do that. A lot of people have downloaded it, and it's been widely used all around the world. It forms the basis of more than 100, maybe even many more research papers, and it's also now being taught at several universities around the world, used for training of engineers within energy system analysis and modeling. When we have used and analyzed all this and try to identify doable and affordable ways of going for 100% renewable energy, we have one major conclusion experiments to share, and that is, if you want to identify an affordable and doable way of really decarbonizing the whole society, or going for 100% renewable energy system, then it's very urgent and very important that you take a holistic, we call it a smart energy systems approach. it's not doable and affordable for each sector, subsector, individual. For example, on the electricity sector on its own, or the heating on its own, or the gas on its own to convert and decarbonize. Then it'll be too expensive in terms of storage and infrastructure and so on if you try to do that. It's when you take the integrated cross-sectoral approach and the different sectors can help one another, you will be able to identify the best solutions. And there's a lot of reasons for that, but some of the main reasons are that the storage of energy, to store energy, it's quite a different cost if you store heat or gas or liquid fuel compared to if you try to store electricity. That is very expensive. So it's when you convert the energy in the right way and store it in the right way that you can find the system that works. And that's also why the model we have, Energy Plan, is really designed to make hourly calculations, not only in the electricity, but also in the district heating, the district cooling, the gas and the liquid fuel and the hydrogen, all parts of the system. So here you can really play around with different technologies to convert the different types of energy and different types of storage to storage, hydrogen storage or thermal storage or batteries or whatever. And when you do that, then you can identify a suitable and affordable solution. It's a little bit beyond my presentation here to to go into the details, but we have made a video that is on YouTube called Smart Energy Systems, where we have animated how to do this cross-sectoral and also show how the different sectors assist one another. I will now turn my head to a specific proposal we and the Association of Engineers just made this year in 2020 on giving a concrete proposal on how the Danish government could implement the 70% target of decreasing carbon dioxide emissions in 2030. Quite an ambitious target, so it's also quite a challenging thing to tell exactly how you could do this. First, some considerations that we have in this study. We call it in Danish IDA's klimasvar, and if you translate that to English, it's something like the IDA climate response. IDA is the Danish Engineering Association, and the climate response is sort of how we think that you can address this issue here, our response to how you can implement those ambitious climate change response targets. We have some guiding principles, and one of them is that when you design what to do in 2030, we think it's urgent that you look beyond 2030, because it will be very good if you can reach this aim of 70% reduction in 2030. But after 2030, we have to move on and take the next steps and eventually be fully decarbonized. We have put the year here 2045 as a target year for fully decarbonization. We used to say 2050, but we think it's due to the urgency of the situation, we should move forward. This is very important. It means that it's not only, of course, we have to prioritize using commercial existing technologies when we reach the target of 2030, the best we can, but also we have to develop further some technologies in order to be able to do it. But while we do this, it's very urgent that we do it in a way so we can actually take the next steps after 2045. And it's also additional urgent that we'll try to realize what kind of technologies do we need after 2030 that we do not have in hand now. So we start to make the necessary innovation and technology development, so we make sure that we have commercially tested technologies and proven technologies in 2030, so we can make the next steps, even though those technologies will not make a big difference in 2030, but we'll have to have them ready for the next step. So this is one guiding principle when we look about how to design such proposal. Another guiding principle is that we should make a solution for Denmark that fits well into a context in which the rest of Europe, and by the end of the day, the rest of the world will do the same. We cannot save the world alone in Denmark. We'll have to save our parts together with the rest of the world also doing their share. And that's also pretty important, because I mean you can decarbonize or go to a lot of renewable energy in many ways. You can import biofuels, for example, or you can just build a lot of wind turbines in Denmark and then export the electricity in certain hours and say they replace coal-fired power plants somewhere else. But that will not fit into a situation in which all countries do the same and we all decarbonize. And so that's very important that we do it in a way that fits into such future context. Therefore, Denmark should include our share of international aviation and shipping. And that's actually an issue. I will come a little back to that later on, but that's very important, and it's also important to be aware that this is actually not included in the UN way of calculating. When we in Denmark say we have this 70% decarbonization target, then it's according to a calculation in which our share of international aviation and shipping is not included. And sooner or later it should be. Somebody should take care of that part also. And of course, in Denmark, we should take care of the Danish share of this consumption. And it's very difficult to deal with because it's a lot of oil in this particular way of this part of the energy supply. Another thing that is very important is that we do not exceed our share of sustainable use of biomass in the world. If we should do this in the world, then there's a limited share of biomass we can use for this, and we should not exceed our part of it. It's also equally important that in terms of flexibility and reserve capacity, that we also do our share in Denmark. In our part of the world, it's our share of the European electricity supply. And there's a lot of studies saying that we can build a lot of wind and PV and so around Europe, and then of course we can help one another if the wind is not blowing so much in one part of Europe and the sun is shining more in another part and so on. And of course we should do that, and we should also have interconnectors to level that out and make use of it. But when you calculate it, it cannot do the whole job. And by the end of the day, you need something that can produce when the wind and the solar is not producing enough for the whole of Europe. You need reserve capacity. And of course, we should collaborate with all our neighbor countries and the rest of Europe when we do this, but we should also provide our share of this. And that's also something we have included in the proposal we have here. This slide here shows the Danish carbon dioxide emission in the UN accounting, as I just mentioned, that is without international aviation and shipping. And it starts with 1990, that is the target year defined by UN, and then how it's been involved in 2000, 2010, and 2020. That is our expectation of 2020, not Corona COVID corrected. So it may be a little different, but not a lot different in this diagram here. And then what we call EDA's climate response in 2030, that is how we plan to decrease it. And what we look at in the EDA response is in particular energy and transport, the one that is marked here with the dark blue in the lower part of all the of the showing here. And We do not have agriculture and so on included in ours, but we assume and coordinate with that also agricultural and process and so on will do their share of it. Then we have a proposal. We can show how Denmark looks in 2020. And when we calculate this, we calculate it, as I just mentioned, in our computer models, hour by hour. So we can also calculate all kinds of excess production and all these sort of things. But when we then put it into a Sankey diagram showing for the whole year, the Danish situation now in 2020 is more or less as illustrated here. You can see we have a lot of wind power. You can also see on the top that half of our electricity production is coming from wind power. A little more than half actually is expected this year already. But still, you can also see we have a lot of coal and a lot of oil and natural gas in our energy supply, and a lot of that goes to electricity production, the coal, and a lot of the oil for transport, and also some for industry. And our proposal will be then to do a lot within energy efficiency and insulate houses, expand district heating, replace coal, oil, and gas with renewable energy, and so on and so forth. And when we do that, we can turn it into this proposal here in 2030 with then a lot of investments in all types of different technologies. As you can see here, we expand the wind quite a lot. We get rid of most of the oil and the coal. The oil we have left is still for transportation, but there's a lot of electricity for transportation. There's a lot of biomass. There's still a lot of district heating, and there's a lot of excess heat from industry being recycled in district heating, and there's a lot of heat pumps coming in. So there's also then wind via heat pumps going into the heating sector, both in individual houses and also in district energy. When you look upon it and we've sort of divided into 4 sectors. You can see here the blue is electricity, the orange is heating, and the gray one is industry, and the yellow one on the top is transport. And what this diagram shows here, when we make our proposal and decrease the carbon dioxide emission, it is especially the transport that is the hard one to really deal with. So more or less the other sectors we can more or less decarbonize fully, but not the transport sector. This is where we have the hard problems, and this is where it's very important that we start already now to develop technologies so that we'll be able to do that beyond 2030, because that will be the next steps. A lot of discussion in Denmark is also about the the economics of doing this, and a lot of discussion is centered about how many money will the government have to spend out of the state budget to initiate all these things. In Denmark they will miss a lot of taxes because we have taxes on fossil fuels, and very often they'll have to give some type of subsidies or initiatives to make all these investments here. We have listed up all the investments, what is necessary in order to implement our proposal, and you can see also here what it takes. It's building renovation, it's wind power, electric vehicles, individual heat pumps, and a lot of other technologies we'll have to invest in during the next 10 years. And then we have calculated what the annual cost of the Danish society. Here we are not focusing on the Danish governmental budget, but on the Danish society as such, because many of these investments, of course, will not be carried out by the government. There will be private investors, building owners and wind turbine owners and electric vehicle owners and so on that will make these investments here. And then we can calculate the annual cost of doing that of paying for all this in 2030. And that is taking into account that the lifetime, of course, of a building renovation will be much longer, but this is the cost that you'll have in 2030 that we have calculated here on the annual cost in million euro per year. Then to the diagram to the right, we have showed the cost that we have now in 2020 in Denmark divided into investments, operation and maintenance cost, and fuel costs. And then we have shown, compared to a reference, if we carry on not implementing the green transition, but carry on with fossil fuels. And then we have compared that to our proposal on how to implement the 70% target, the one we call the EDA climate response. Then we are compared to that. And what you can see from this diagram here is that, and as calculated to the left, we really have to increase the cost of investments. That is the dark blue. That will increase a lot. But what you also can see is that the cost of fuel, the yellow one to the top, will decrease equally. And if we use the prices for the markets, international market prices for fossil fuels expected by the Danish Energy Agency for 2030, and that's equivalent to what is expected in the International Energy Agency for the future, then we will save as society, the Danish society, we will save as much on the fuel cost as we will have to pay additional to pay for our investments. So in principle, this do not have to be more expensive if it's carried out in the right way. On the contrary, what you can see here from the diagram is that instead of paying for fossil fuels that is very often imported or in the future will be imported in Denmark, then we will pay money for investment, and that is the investment you see to the left, the building renovation, the wind power and so on. Very often things that we can do in Denmark, at least big parts of it, so this will generate a lot of job and a lot of that money will stay within Denmark. So this will actually be a change in economics of the energy supply, in which we pay less money for import and more money for Danish labor in order to make this green transition. And that will also then, in terms of how you normally calculate economics in growth national products, and then that will increase that, and you can say make us richer. We will have more money to spend in Denmark compared to if we followed the reference and did nothing. At least that's an option if we play our cards right. Then I'll come back to a little bit about the carbon dioxide emission accounting in the UN. If you see the diagram to the upper right corner, that's that's the carbon dioxide emission coming out, and here it's divided on coal, oil, and natural gas, but it's the same numbers that you've seen before, the numbers of 2020. And then if you go to this climate response, this is for energy and transport we look at here. But there are two things that we believe we should be aware of when we do the accounting. The one thing is that actually we do import right now quite some biomass. We burn a lot of wood chips in our power stations for combined heat and power production in Denmark. So we import quite some. And in the UN counting system, depending on how this wood chips and biomass is harvested, then that would generate a carbon dioxide emission somewhere in the world in which we import it from. And according to the UN system, that will then be charged, or that carbon dioxide emission will be accounted for the country of origin of the biomass. But if we include it, actually we have a higher carbon dioxide emission because we import biomass. And right now we import so much biomass that according to what we can analyze here, we are above what is the Danish share of sustainable biomass in the world. So this is actually something we should at least keep an eye on. To the lower left corner, you can see, and the green one that we have put up here, you can see the difference from the imported wood chips. If we calculate that on, and that can be calculated on many ways, but this is a cradle to gate in a 100 years time horizon. We have estimated it here. It's not easy to absolute numbers, but this is an estimate to show it. And also in our climate response, there will still be some, but if we sort of prioritize and first of all decrease how much we import, but also concentrate on the biomass, for example, the manure and the straws, that could give even a positive contribution, then that's something that could also help on this situation. And that's a consideration we have when we put our proposal together. Another issue, and that's maybe much more important, that is the international aviation and international shipping. And here we have also in the report calculated and identified the Danish share of international shipping and aviation. And if you put that on top of it, you can see that to the diagram to the lower right corner, that is the one shown in orange and blue, dark blue. Then you can see it actually makes quite a difference, especially when we go into the future. And that's not included when we define our targets in Denmark and in many other countries. It's not, because it's not included in the UN way of calculating it on the individual country. It's included in as a generic part. But here you can see that that will grow quite important when we do our. It's almost doubling, or not completely doubling, but it's really increasing the carbon dioxide that we will have in 2030. The share from international aviation and shipping, and we just point out that we will also have to consider that in Denmark. And we already now take some proposals and actions in our proposal on how to do something about it. And after 2030, we will have to deal with it in the next steps, and that's quite a challenge to identify what kind of electric fuels and so on that we will be able to decarbonize those sectors also. Then just to sum up, we have a lot of focus on sector integration, and that is how to balance all the wind power and all the solar that we put in here. And when you do smart energy systems and do this, then if you want to do it in an affordable way, then it's not good to invest a lot of in electricity storage, because it's incredibly expensive. But we invest some in thermal storage, and we use the existing natural gas storage capacity. We also invest in additional electrolysis capacity, because and hydrogen storage, because then we can have a much more flexible system. And this is where there's some also investments in which you can integrate wind with the least costs. We also use a lot of heat pump, as I showed in the other diagram, both in district heating systems and also individually. But especially in the district heating systems, you can use then the overcapacity of heat pumps when it's not winter season, and together with large scale electric boilers and the thermal storage, and then you can actually implement a solution that is quite flexible in terms of using wind and storing it as heat that you can then use for district heating. We also have intelligent charging of electric vehicle. That's a very good option, but the battery capacity, even though we convert a lot of cars to electric vehicle, is still small compared to the energy storage of thermal and natural gas and liquid fuel. Then we also have some flexible, intelligent electricity demand to make the system even more flexible. But this is where we have this sector integration. And it's because we have the sector integration, it's because wind is doing power to heat and power to transport that we can identify this much more affordable storage options in the system we design. And again, we calculate this hourly, so we can account for all types of energy conversion and energy storage for every hour of the year. Then we also have a special attention on the biomass. As I mentioned a couple of times, we actually lower the reduces the biomass consumption in our proposal, and that's also needed. We have a focus on, as mentioned here, Denmark, to reduce the use of biomass and also to use sustainable biomass with low carbon dioxide emissions, and also to prepare for that after 2030 that we have a long-term development in which we will limit ourselves to use the Danish share of sustainable biomass use in the world. And we are on the right track with this proposal we have here already. Then, of course, by the end of the day, we have to build a lot of renewable energy then to convert all the coal and gas and stuff. We have some solar thermal both in district heating and individual houses. We also do some geothermal. We have quite good underground conditions for that in Denmark. Then we expand the PV from 1,000 megawatt to 5,000 megawatt, and we expand the onshore and offshore winds for around 6,000 megawatt now to the double, around 12,000 megawatt. And so we have to double our wind capacity within the next 10 years, meaning that we will have to build even more wind turbines for the next 10 years that we did in the previous 10 years. In the previous 10 years, from 2010 to now 2020, we expanded from 20% to 50%, so we expanded with 30%. Here we have to do the same expansion almost twice to reach our goal in the next 10 years. So we have to speed up how many wind turbines we build, and that is also being planned for now. I'll just mention this paper as a last remark, because we have calculated sort of the same type of decarbonization of not only the Danish system but the European system using the same principle. It's called Smart Energy Europe. And in this paper you can see more details if you want to see it in a broader text. And this is also where we sort of align with that if we do what we proposed in Denmark, then it's actually something that fits into that the rest of Europe could do the same. And in Denmark we provide our share of not using too much biomass, and also providing our share of flexibility in the electricity supply, etc. So now this presentation comes to an end, and I'll just show this final slide here. And here is where you can seek more information. I guess this slide will be made available by the organizers. Otherwise, you can take a look here. Here you can see my personal homepage. You can see where you can find the book. You can see where you can find the paper on Smart Energy Europe I just mentioned. There's also the report. Unfortunately, it's in Danish, so I'm not sure that everybody can have, but at least you have the presentation here now. There's the freeware model energy plan that we use, and there also this video on animated smart energy system that I really advocate that you take a look on if you are interested. And by this final word, I really like to thank you all for hearing my presentation. It's been a pleasure making it, and I hope really that we can meet person to person at some other conferences in the not so far future. But for now, I just want to thank you all. Thank you.
Okay, I would like to thank Professor Henry Lang's presentation because he is not online, so there is no Q&A session for this presentation. Of course, I believe audience may have some questions. I would like to encourage you to communicate or contact Professor Henry Lang later on. So I would like to end this keynote session. So again, I would like to thank the two speakers, Professor Oken Anwar and Professor Henry Lang. And also thank you all the audience for your time. And I would like to wish you enjoy the rest of the conference. Wish you all the best. Thank you. Bye-bye.
Hello, everyone. Welcome to TÜBA World Conference on Energy Science and Technology. My name is Selda Öterkoç from University of Stratified in UK. Today, we will have two distinguished keynote speakers in this session. And our first speaker is Professor Igor Pioro. Professor Pioro is a professor in Faculty of Energy and Systems and Nuclear Science in Ontario Technical University in Canada. He is an internationally recognized scientist within the areas of nuclear engineering and thermal sciences and engineering. And he is the author of more than 500 publications. He is a fellow of ASME and foreign fellow of National Academy of Sciences of Ukraine. And he is also an editor-in-chief of ASME Journal of Nuclear Engineering and Radiation Science. And he has received many international and national awards and certificates of appreciation. Today, he is going to give a keynote lecture on current status and future developments in the nuclear power industry of the world. Now, I would like to invite Professor Igor Pioro to deliver his keynote lecture. We are looking forward to your presentation.
Thank you very much. And I would like to thank the Turkish Academy of Sciences and organizers of this TÜBA conference for inviting me. I'm really glad to see this so nice, properly organized conference, very interesting presentations and everything. Due to this, today my presentation will be related to non-renewable and renewable sources of energy as the starting part, and after that I will move to details in terms of current status of future development in nuclear power industry of the world. On this slide, I have more or less standard things which everybody should know, but in next slides I will try to confirm all these things, that electrical power generation is the key factor for advances in any other industries, agriculture and level of living. And electrical energy can be produced by non-renewable sources such as coal, natural gas, oil, and nuclear, and such renewable sources such as hydro, wind, solar, biomass, geothermal, and marine. Marine usually includes tidal and wave. However, the main sources for electricity energy production will be thermal, primary coal, and secondary natural gas. Also in some countries, oil use. Second place will be hydro, and the third one will be nuclear, when we're talking about the world generation. The rest of the sources might be visible in some countries. In addition, renewable sources such as wind and solar are not really reliable sources for industrial power generation because they depend on Mother Nature. Plus, relative cost of electrical energy generated by this and some other renewable source, with the exception of large hydroelectric power plants, can be significantly higher than those generated by other sources. I have prepared this table. This table is electrical energy consumption per capita, means per person in a country, per citizen, better to say, and human development index in selected countries. We have an official parameter which defines the level of living. It's called human development index. If you look at the bottom of this slide, HDI is calculated as a root of power 3. Where we have life expectancy index multiplied by education index and income index. And unfortunately, I cannot include all 189 countries, but I pick up the most selected some examples there. Very high HDI index consists of 4 groups. Very high HDI, 65 countries. High HDI, 53 countries, medium HDI, 36 countries, and low HDI, 33 countries. Due to this, from the left to right, I have HDI rank based on 2019 data. This is the latest that we have. Countries, HDI calculated value by 2019. After that, electrical energy consumption in 2 columns. First one, watts per capita, and second one is total gigawatts hours per country, and population in millions of 2019. Well, of course, we know that the group of the countries which have very high HDI, it will be Norway, Switzerland, Iceland, Germany. Number 54 will be Turkey there. And these countries have relatively very high WOS per capita, means electrical energy consumption in these countries. And by this table, I would like to show you how important to have electricity generation and consumption inside country at a high level. In high HDI group, we have many countries, but world will be here at number 99. And in medium HDI, I just included India. It's second largest country by population. And low HDI, we have also number of countries, 33 of them. Now, if you look at the electric energy consumption WOS per capita, in first group, it's possibly from maybe 300 and going up to 300 watts per person and going up to almost 6,000 watts per person in Iceland. It's unbelievably high consumption of electricity there. But if you go to the bottom where we have yellow highlighted HDI rank, what you can do if you have just 2 watts per person in a country, for example, like Guinea-Bissau, for example, like Chad, is eventually a complete dead end. You cannot have education because you cannot have a computer or laptop. You have no any lights because it's less than the small light in your hand. And if you go into next slide, here all countries in this graph, the HDI scale is linear and the electrical energy consumption scale is logarithmic. You can see that all countries in the world, they lined with accuracy plus minus 20%. And green high HDI, blue, very high HDI, blue high HDI, medium HDI, and red will be yellow HDI. Unfortunately, I cannot show all these points corresponding to the countries because it's too much, but you can see that electrical energy consumption is #1 factor which impact the Human Development Index. Now let's go and see how world and selected countries generate electricity. Unfortunately, up till now, world heavily rely on coal generation. It's around 37%. Second place, gas, 24%. The third one, hydro, 16%. Nuclear, around 10.4%. Before the Fukushima Daiichi nuclear power plant severe accident, we had 14%. Due to this, we dropped by 3% within the last 10 years. And after that will be 5.3% wind, 3.1 oil, 2.7 solar, and 2.5 other sources for electricity generation. Again, unfortunately, the largest countries by population and the population in millions is shown as red numbers to the right of the sector diagram. China heavily rely on coal, 62%. However, China has done a very significant process with this last 10 years. They dropped from more than 80% to 62%, but still it's a very large percent for generation of electricity by coal. Also 18% hydro, nuclear around 5%, but still definitely nuclear should be more to decrease the reliance on coal. In India situation even worse, they rely on 71% on coal, 11% hydro. They also have nuclear, but it's only 3%. Other countries, United States still rely on coal, but more heavily rely on gas, but still both of them, they emit carbon dioxide into atmosphere. Nuclear 19%, and after that wind, hydro, and some other renewables. Indonesia heavily rely on coal, 59% and 21% gas. From large countries with population and territory, Brazil heavily rely on hydro, but it's a unique place because largest rivers are there. They also have a little bit nuclear, 2.6%, not bad biomass and wind, around 9% each, a little bit coal and 10% gas. Russia heavily rely on gas and 46%, a little bit on coal, also 17.5% hydro and 18% nuclear. Turkey still heavily rely on coal, 37%. roughly gas 19%, hydro is good, it's 29%, and also some other renewables. Germany also, in spite of all advances, they heavily rely on coal, 30%, gas 15%, but also they have quite substantial reliance on wind, 20%, solar 7.7%, hydro 4.2%, biomass 7%, and nuclear 12%. But unfortunately, Germany decided to get rid of nuclear within a number of years due to this. I don't know how they will replace the nuclear source in their grid. Now also we have UK. UK heavily rely on gas. They almost excluded coal, 2.4%, wind 20%, nuclear 17%. France is one of the best examples. They heavily rely on nuclear, 70%, hydro 11%, a little bit gas, 7%, coal almost nothing, 1.1%, and some renewables. And South Korea, in spite of all advances in nuclear, they still heavily rely on coal, 40%, and gas, 27%. This table showing that actually China generating 1/3 of the world's electricity. It will be 7,226 terawatts hour. And unfortunately, this electricity generated mainly by coal. And in the United States, it will be second country by electricity generation in the world. It will be almost half of China. And the United States, as I mentioned, they still heavily rely on gas and coal. And India with 1,547, also heavily rely on coal. Due to this, if you're talking about carbon dioxide emissions, eventually these three countries, they control the emissions in the world from power industry. If you look at the bottom to the left, we have carbon footprint, grams of CO2 per kilowatt hour. The largest polluter will be coal-fired power plants, up to 800 grams of CO2, gas twice less, 400, but still quite substantial. And then after that, we have biomass, solar, marine, hydro, wind, and nuclear. Nuclear will be at the almost bottom. To understand why we have nuclear which emit carbon dioxide, to the right, I have a description what we have. We're talking about the whole process, like extraction of ore, producing fuel, construction, after the demolition, many other things. Due to this, still we have generating some carbon footprint, but it's very small in this case. Here we have 22 largest power plants of the world. First two and many others, it will be hydro plants. The largest hydro plant and power plant in the world will be Three Gorges Dam in China. It's an unbelievable power. It's 22,500 megawatts electrical. But also we have to look at the capacity factor, because the capacity factor showing really how much from installed capacity electricity can be generated per year. And hydro plants is not great capacity factors have. For this largest dam, we have only 52%. Roughly what this means per year, this huge plant generating only half of the installed capacity of electricity. Number 3 will be Gansu, also in China, the largest wind plant, capacity factor only 40%. After that, hydro, and number 7 still hydro. On number 8 will be Jebel Ali. It will be United Arab Emirates, it's natural gas. Again, to Crude Dam, Brazil. Number 10 will be Kashiwazaki Kariwa, largest nuclear power plant in the world. Unfortunately, after the Fukushima Daiichi nuclear power plant accident, it's not in service. However, currently Japanese try to put into operation 1 or 2 reactors. Hopefully to the end of this year, we can see 2 reactors running. On 13th place, we will have coal. It will be again China to Ketu. But installed capacity is significantly less, it's 6,720. Capacity factor here definitely can be 100%, but usually coal-fired power plants used to balance the grid. This is artificially induced capacity factors. Number 16 will be largest operated nuclear power plant in the world. It's located in Canada, in our province of Ontario. And for nuclear power plants, capacity factors from 80 to 100% is very high, because what you have as installed capacity, almost all this power can be used for the whole year to generate electricity. 2 plants from South Korea, coal-fired, again hydro in Russia, number 19, and after that 3 plants, 1 from China, number 20, and 2 from South Korea. If you look at the all electricity generating sources, it will be hydroelectric, number 1, wind, number 2, natural gas, number 3, number 4, coal, nuclear, fuel oil. Also, we have 3 different types of hydroelectric plants. It can be run-of-the-river, quite rare plants, or hydroelectric pump storage plants. Number 9 will be biomass, solar, oil shale, geothermal, peat, wind, offshore, internal combustion engines, solar, concentrated solar, tidal, diesel, concentrated photovoltaic. Also, we have something like recovered energy, and the smallest one will be marine wave. We're talking about only 3 megawatt electrical installed capacity. Now about some renewables. What we have here is the map of the United States, and you can see that winds we have everywhere. To the right, we have wind speed meter per second. However, the vast majority of modern wind turbines, they require that per year it will be average not less than 6 meters per second. It is everything what you have green, yellow, and light brown. Definitely there is no point to build power plants. Only in the middle of United States, where we have blue and other colors, red, this is where the wind power plants is properly to build. How wind operates? I have picked up just for reference purpose, wind energy production during a fine summer week, and this is quite large power plant in Denmark, 650 installed capacity, wind turbines. As you can see, eventually you cannot predict what you will get next day. From very low is a black curve to really maybe stormy weather, very high. Plus you can see that the profile eventually following the activity of the sun starting to increase wind capacity from 8 o'clock and more or less diminishing around 22 o'clock. If it will be solar plants, of course, solar we have everywhere, but to have efficient plant, you have to go south and to go to desert. No, in the United States, you can see that it will be to the left, where we have yellow and red. This is the most efficient places where the solar power plants can be built. This is one of the largest world concentrated solar thermal power plant in the United States. It can be different types. This is thermal solar. There are 3 towers with heat exchangers, water there. It's a critical pressure Rankine cycle, and we have heliostats, which operated by computers following the sun and concentrated light on these towers. If it's environmental friendly, it's some sort of question mark, because light is so intensive that birds flying near the towers, they just burn in air due to very intensive light. If you're talking about also important factor, but eventually is very sad factor, is deaths per terawatt hour. Number 1 will be coal. Again, we're talking about the whole process, like building mine, extracting coal and other things. Second place, oil, biomass, peat, gas, hydro, solar, wind. At the lower end, it will be nuclear. What we have in thermal and nuclear power plants. Very important parameter will be thermal efficiency, and here is the table starting from the most efficient gas-fired power plants. They use combined cycle, combination of Brayton gas turbine cycle and supercritical pressure Rankine cycle. The efficiency up to 62%. What this means is that roughly 2/3 of energy introduced by combustion of natural gas or liquefied natural gas transferred into electricity, and only 1/3 thrown into environment or lost. Second place will be supercritical pressure coal-fired power plants. They are quite efficient, up to 55%. Even it's quite rare, but for example, India, they have largest diesel generators as around 50 megawatts electrical each, 4 of them in one small grid. Their efficiency up to 50%. Old subcritical pressure coal-fired power plant up to 43%. And number 5, we have the most efficient nuclear power plants equipped with carbon dioxide cooled reactors in UK, up to 42. Unfortunately, it's quite old designs of reactors. Due to this, all of them will be shut down, and the UK will move into water-cooled reactors. Number 6 is eventually a concept from next generation, generation 4 reactor, sodium cool fast reactor. We have 3 of them, 2 large in Russia, it will be BN600 and BN800, and 1 small one in China. It's around 20 megawatts electrical. Their efficiency up to 40%. And after that, unfortunately, with lower thermal efficiency, we have all light water cooled and heavy water cooled nuclear power reactors and plants. The maximum we can get right now for a pressurized water reactor plant, it can be up to 36-38% gross. And at the bottom will be small modular reactors, pressurized water reactors with efficiency of 26%. Actually, this is KLT40S number 12. 2 reactors are in operation in Russia. This what I'm showing here is known parameters for them. Just for illustration, this is reactor BN600 sodium cooled. It's a very tricky technology. Only Russia and China small reactor they have currently in operation. It's a triple loop liquid sodium inside reactor circulation. After that, heat exchanger sodium to clean sodium and clean sodium outside reactor, transferring heat to subcritical pressure Rankine cycle. At the right bottom, you can see temperature specific entropy diagram, and you can see that this reactor is more or less as the older coal-fired power plants with superheat of the steam up to 505 degrees and superheated steam as reheat. This is the most popular reactors. It will be a typical pressurized water reactor. We have a reactor and primary circuit located in containment building, and we have in the center reactor and core inside pressure vessel. We have usually 4 circulation pumps. We have usually 4 steam generators, pressurizer, and also it's a light water cooled reactor. And in the steam generators, we have light water, which is going from outside. And we have subcritical pressure Rankine cycle with high or medium pressure turbine, and after that 2-3 double flow low pressure turbines. To the right up, you can see TS diagram. You can see that we have this is limitations for all light water cooled and heavy water cooled reactors, that unfortunately we have only saturated steam at the inlet to turbine. We have no any reheat. Due to this, we cannot move above 38% for the most advanced reactor, which is currently EPR, European Power Reactor, which was 2 of them were put into operation in China. The exception will be current designs of small modular reactors, pressurized water reactors in Russia. They have small overheat of the primary steam, but they have no steam reheat. Now, this I hope to show you at the end of my presentation. Here is just a general what means capacity factors, and I have mentioned nuclear usually very high. In USA, 2017, 92% capacity factor, world average in 2017, 81. Geothermal also not bad, 76, bioenergy, combined cycle, coal-fired. It's artificially introduced capacity factors. Eventually, they can also operate if it's new plant and you have 24/7 supply of fuel. You can go to 100%, but they have to compensate, for example, drop of electricity generation by renewables in the grid, or to cover the increased consumption of electricity there. Because they have quite variable capacity factors. Hydro plants, in spite even like the largest in the world, Three Gorges Dam power plant, they have around 52%. Here you can see that world average 45. Of course, it can be very wide range. If you have large lake and small plant, you can have 99%, but on average it's around 45. Wind, approximately 20-40% capacity factor. Of course, solar plants depends on location. For example, in California, it can be 22%. In Spain, it's a very tricky one. It's the most advanced thermal solar power plant. They're using molten salt in tower, and after that, at the surface level, they have heat exchanger to regular Rankine cycle, and during the day they can store molten salt in a storage place and use this at night. Due to this, they can operate in summer more or less 24/7. 24% means 24 hours per 7 days a week. However, in winter time, still they cannot cover 2 hours. No, wave is relatively low. It's only capacity factor 3%. Also, if you look at the levelized cost of energy by different plants, nuclear will be the lowest one here, and the highest one, it will be solar photovoltaic, and solar thermal also can be biomass. Also, don't forget that biomass is also emitting CO2 in atmosphere because it's still combustion process there. Here I would like to show you how province of Ontario, we have more or less isolated grid from the rest of the country, how we generating electricity. Somewhere in 2015, we get rid of coal. Due to this, to the left, we have installed capacity by energy source. The largest one will be nuclear, 32%, gas 26, hydro 23, wind 12, solar 6.3, biofuel 1. But if you look to the right, how electricity generated, nuclear 61%, hydro 25, gas 6.4, wind 7.4, and biofuel 0.3, and solar 0.5. Due to this, in province of Ontario, we have around 15 million people. Due to this, we heavily rely on nuclear. To the left is actually one day, July 17, 2019, Wednesday, working day. Relatively hot weather, 24 degrees. Usually in summer, we consume more electrical energy due to operation of air conditioning. Due to this, you can see to the left is actual power per day, how it's fluctuating, and to the right is capacity factor. Nuclear, this should be absolutely clear. The most efficient, 100% capacity factor, no changes, just very, very small if you look to the right. After that, what we have, of course, grid operators would like to use renewables such as hydro, wind, solar. For example, from 2 o'clock when started to diminish, due to this you need to compensate that. Around 4 or 5 o'clock, the consumption also increasing. Due to this, grid operators try to compensate that with hydro, but not enough. After that, they using gas to compensate that. Summer from 6 to 20, we have solar, but it was sunny day. Due to solar can operate more or less in full. It's like upside down parabolic. Eventually, it's still not enough due to they put in full capacity of biofuel power plants, and of course, in the evening, consumption dropped down, winds slightly recovered, and they decrease in hydro, natural gas, biofuel, and so on. This is proper operation of the grid. In any grid, if you have renewables, we still have to have fast response plants as gas or coal-fired or hydro to compensate quite fast changing of consumption or changing in generation by renewables. So here just I will mention that the major advantages of nuclear power, concentrated and reliable source of almost infinite energy, which is independent of weather conditions, more or less. Still, we need to condensate steam in turbines, which is done by water or by cooling towers. High capacity factors are achievable, essentially negligible operating emissions of carbon dioxide and relatively small amount of waste generated, relatively small amount of fuel required, and as a result, nuclear power is considered as the most viable source of energy for the next 50, 100 years. What we have as of today. I compared number of units, and to the left will be reactor types. We have 6 different reactor types, and power plants are related to that. A number of units I have as of June 2021, and I'm comparing what we had before the Fukushima Daiichi nuclear power plant disaster in March of 2011. After that will be installed capacity, the same comparison at the right. I have 2 columns, number of units which plan to be built and gigawatts electrical of installed capacity of these units. Currently, we have 442 reactors connected to grid, but it's not necessary that all 442 reactors in operation. I will explain this later. Pressurized water reactors, 68% or 303 reactors there. Green and the arrow up means in comparison with before the Fukushima Daiichi accident, it's increased quite substantially. What is important, if you look at the forthcoming units, solid plants for 38 units and plants under question mark for 35. Second one will be boiling water reactors or advanced boiling water reactors. We have 62. And this very significant drop within last 10 years by 30 units. Also, how many these type reactors will be built? 4 under question mark. Why? My personal opinion, I actually don't want to say that this is unreliable reactors, safety compromise, but reality is that Fukushima Daiichi nuclear power plant disaster happened with older designs of boiling water reactors. Due to, for my opinion, perception that it looks like related to such severe accident. It's not everybody would like to consider these reactors for future builds. Number 3, pressurized heavy water reactors. It's only 49 left, but not significant changes within last 10 years, only less by 1 reactor. However, the problem is that also it's better than future of boiling water reactors. 2 definitely will be built. Who is building? Mainly India, 1 possibly maybe in Argentina, maybe a couple will be in Romania, but Canada has the largest number of CANDU reactors, Canada, deuterium, uranium reactors, heavy water reactors. We have no plans to build anything. There is some future, but not so bright as for pressurized water reactors. Number 4, advanced gas-cooled reactors, carbon dioxide cooled, as I have mentioned, the most efficient nuclear power plants in the world. But all 14 of them will be shut down within maybe next 5 to 10 years. And instead of carbon dioxide cooled reactors, we have 1 which will be put into operation in China, possibly within this year. It's relatively small, it's only 200 megawatts electrical. It will be helium cooled pebble bed modular reactor. Number 5, light water graphite moderated reactors, or it's only in Russia. Large one, it will be RBMKs. 1 of RBMK exploded in Chernobyl due to Russia has decided completely shut down any research and development with these reactors, and all these reactors, 12 flat, they will be shut down also within maybe next 15 to 20 years and never will be built again. And number 6, it's, as I have mentioned, next generation 4 reactors. We have 3 of them. I didn't show here a Chinese reactor, it's only 20 megawatts electrical. We have 2, and also possibly 2 plus 1 may be built in China and in India within the next maybe couple of years. If you look at the most developed countries in terms of nuclear power, United States number 1, 94 reactors, but they dropped down within the last 10 years by 10 reactors. France dropped down by 2. Second place, 56 reactors. China, 50. China has real renaissance in nuclear energy. They built 37 reactors within the last 10 years, which more than the whole world built. Russia still moving forward, and they have 6 reactors built inside country. Japan has the most significant drop in number of reactors after the Fukushima Daiichi disaster. They dropped down by 21. They have currently 33 reactors connected to grid. Unfortunately, in March of this year, only 2 were in operation. Last year was 9. We hope that all 33 reactors will be put in operation. When? Difficult to say, but they're still working on these things. South Korea increased by 4 reactors, Canada decreased by 3, Ukraine no changes, UK decreased by 4, Germany decreased by 11, only 6 left, but they will be shut down relatively soon. Spain decreased by 1 reactor, India still moving forward, they put into operation 4 reactors, Sweden decreased by 4 reactors. I will not spend time on this table. This is all countries with nuclear power reactors. In green, they have plans to build reactors in red node. If, for example, like number 3, Bangladesh, there is no units here and no net megawatt electrical, means forthcoming, Russia will put 2 reactors in operation there. If you go to the next one, you can see 32, it will be Turkey. Currently, Turkey has no operating reactors, but hopefully within a short time, they will have 4 pressurized water reactors put into operation. I will go just to summary. 33 countries have operating nuclear power reactors. 3 countries plan to build nuclear power reactors. In addition, 30 countries are considering, planning, or starting nuclear power programs. And about 20 countries have expressed their interest in nuclear power. However, 13 countries with nuclear power plants don't plan to build nuclear reactors. This is shown to the left number of reactors, to the right installed capacities, impact of nuclear accidents. It's a real disaster. First one, which more or less very well known, but was not so severe as Chernobyl and Fukushima. It will be 3 Mile Island nuclear power plant accident in the United States in 1979. You can see that per each 5 years, the number of reactors built and connected to grid grow up. Unfortunately, in '86, we had the most severe accident, Chernobyl nuclear power plant accident in Ukraine. And during these 5 years, from 85 to 89, it was the glorious days of nuclear power industry. Almost 120 reactors were put into operation. After that very significant drop, less than 40. Next 5 years, even less than 20, slightly recovered to maybe 22, dropped down to 17, slightly recovered, and after that, 2011, another severe accident happened at Fukushima Daiichi nuclear power plant. But eventually, the world recovering, and for example, right now, within 2015, 2019, we are at the same level of building and connecting reactors to grid as it was from 75 to 79. It's a huge distance in time, but this is reality what we have. This is how the installed capacity distributed, the most popular reactors in terms of installed capacity from 900 to 999. However, generation 3 plus reactors, so they're usually above 1100. And the largest one will be EPRs, it's 1660 megawatts, but only 2 reactors in China currently there. Who is doing what in nuclear? Russia and China, number 1 and 2 in the world. Russia mainly built outside country, only 5, maybe plus 3 in country, Bangladesh 2, Belarus 1, China 2 and plus 2, Egypt 1 and possibly plus 3, Finland 1, Hungary maybe 2, India 2 plus 2, question mark, Iran 2, and Turkey 4. China mainly built inside country, inside China 9 plus 14 question mark, Pakistan maybe 3, Romania maybe 2, and the closest one will be South Korea and India. They plan to build 7 reactors, and after that the rest of the countries. Why such success in Russia and China? Because it's a government supported nuclear power industry. Like in case of Turkey, Russia will pay for the plant. As I know, they will operate for 20 years and after that transfer to Turkish specialists. And of course, even large nuclear companies, they cannot afford that. Only government support can push nuclear as a very significant source. Without significant CO2 emissions can be done like that. Conclusions I will not read, you can read on your own. Now a couple words of small modular reactors. We counted around 108 concepts of small modular reactors, water-cooled SMRs 33, water-cooled SMRs marine-based 7, high-temperature gas-cooled SMRs helium-cooled 21, fast neutron spectrum SMRs lead-cooled or sodium-cooled 26, and molten salt 17, other SMRs 4. Unfortunately, from all these 108 concepts, only one concept, KLT40S, water-cooled SMR in Russia, two of them operating on a barge. And this slide shows you by countries, which country developing which concepts. Of course, it's a very hot topic right now, but it's not only my personal opinion, but also very well-known scientists as Dr. Romney Duffy and Professor Kirillov from Russia. Our opinion is that it's absolutely impossible to have 108 concepts per designs to put into operation. We're talking about maybe less than 10 within maybe the next 10, 15 years. It's very tricky part. It's not simple to do such things. Now, a couple of words about what we have. It will be KLT40S. Schematic is proven marine reactor, possibly from submarines, and after that for icebreakers. In red lines, it's extra passive safety systems, cooling systems added to there. To the left, central green cylinder pressure vessel, 4 small green cylinders, circulation pumps, gray cylinders, steam generators. It will be generation 3 reactor. Currently 2 of them in operation. To the right, it will be generation 3 SMR, also by Russia, written 200M. What they have done, they increase height of the pressure vessel and they hide inside steam generators. What this brings from 26%, thermal efficiency increased to 31, which is very substantial in this case. This is barge, where Russia has 2 KLT40S from December of 2019 is in operation. Comparison, what also we have to understand that thermal efficiency of small modular reactors never will be larger than the same plant with large reactor of the same type. Also, you have to enrich quite substantially fuel. Otherwise, you cannot work for a long time without refueling, which is also very important for SMRs to work as long as possible, plus smaller size require that. It's clear, for example, fuel enrichment from the bottom 4th row, that currently Russia using 18.6 enrichment of uranium inside KLT40S, and in written 200M, it will be up to 20%. Of course, such enrichment of fuel requires special knowledge of operation, special treatment, and many, many other things. Here is some special consideration for SMRs. You can read on your own because it's too many things which we have to consider before we'll put them into operation. Of course, we have to be honest and to say about the efficiency of modern nuclear power plants. Radioactive waste have relatively low thermal efficiencies, risk of radiation release. Production of nuclear fuel is not an environmental friendly process. Due to this, all these deficiencies should be addressed, and we moving, it's almost my last slide, to generation 4 nuclear reactors. It will be 2 helium-cooled reactors, gas-cooled fast reactor, very high temperature reactor, up to 1000 degrees helium, sodium-cooled fast reactors, lead-cooled fast reactors, molten salt reactors, and number 6 concept, it will be supercritical water-cooled reactors. Why we're going there? Because we need to match thermal efficiency of modern gas-fired and coal-fired power plants. Because it's clear that higher temperatures of the reactor coolant, more efficiency you can get. And here is our publications related to this topic and general references which we have used in our presentation. And thank you very much.
Thank you very much, Professor Feodor, for your very nice presentation and sharing your insights on nuclear, the future of nuclear power industry. And I would like to ask our audience if they have any question, but maybe we have very short amount of time. So maybe I don't see any question in the Q&A section, but I have a very quick question maybe. How do you see the future of nuclear energy as the wind and solar production is increasing?
As I have mentioned, you see, we cannot rely on renewables because renewables very significantly depends on environment, yes, and on location. Now, for example, climate change, we started to get terrible things like fires in Turkey, Greece, many other places. like flooding. If you have clouds, your solar almost gone. If you have very significant eruption of volcano, like we had in Iceland, even flights were canceled. You will not get solar. Due to this, if you rely on solar, wind also depends on solar. Eventually, hydro also depends on solar activity. Something wrong, you will be out of energy. What you will do? You have to live, you have to survive, you have to fight against all these, terrible things which we have around, especially this year. It's absolutely unbelievable what can happen when we changing climate and increasing emissions of CO2. Because we need to have reliable energy, which it doesn't matter what will happen. We will have emergency backup. Because I strongly believe nuclear, of course, gas and coal, more or less they can cover these things. But gas and coal, they emit CO2 due to this most preferential nuclear. However, of course, we absolutely cannot allow it to happen any next severe accident. It will be a complete disaster. And I don't think that we have any other source of energy to replace nuclear as the very valuable non-CO2 or the lowest CO2 emission source.
Thank you very much for a very nice presentation, very informative presentation.
Thank you.
Now it's time for our next speaker, Professor Zhu Han. He's a John and Rebecca Morris Professor in Electrical and Computer Engineering Department, as well as in the Computer Science Department at the University of Houston in USA. His research interests include wireless resource allocation and management, wireless communications and networking, game theory, big data analysis, security, and smart grid. And according to Web of Science, Professor Han is the top 1% highly cited researchers since 2017, and he has received many awards, including NSF Career Award and several Best Paper Awards. And he's a fellow of IEEE and American Association for the Advancement of Science. He's also a ACM distinguished member. Today, he's going to give a keynote lecture on distributed deep reinforcement learning for renewable energy. Now, I would like to invite Professor Han to deliver his keynote lecture. We are looking forward to your presentation. Thank you. Sorry, you are muted, Professor Han.
Sorry.
Thank you.
Okay. Thank you very much for the invitation. This is my great pleasure to give a talk here. And this work is thanks to my collaborator and the National Science Foundation. Okay. And here is the outline. We have this introduction to renewable energy and machine learning. Then we talk about the challenge and the motivation. Then we talk this one for a very recent paper, and then some kind of other related work. Finally, we have the conclusion. And for the renewable energy, everybody say, okay, it's very, very clean. But as a matter of fact, it's not quite. And sometimes they say that the wind energy can be very dirty. So what's the reason for that? The reason is because of unpredictability. Because sometimes there's a wind, sometimes there's no wind, sometimes it's sunny, sometimes it's raining. So the renewable energy cannot be fully predicted. In this case, okay, and for traditional, like the nuclear one that mentioned in the previous excellent talk, or even for the traditional power plant, okay, regular power plant, they have the ramp constraint, so that in order to increase the power, they will take hours for the power plant to increase their power. However, in the reality, the demand and the supply the demand is changing very quick, so there are always a gap between the demand and the supply, while the traditional nuclear or the traditional power plant cannot meet. So in this case, okay, we have to resort some kind of energy sources like the diesel engine. And this diesel engine is not only expensive, but also very dirty. And for renewable energy, it's very unpredictable. So in this case, it will increase the gap between the variance of the gap between the demand and supply. So in this case, sometimes, okay, the wind energy, even though it can be very kind of CO2 kind of, friendly, but due to the unpredictability, it's an indirect consequence for the gas or diesel power plant to fill the gap will make the whole system even more dirty. And for example, in September, Texas have all this kind of wind. It's colder than the North Pole, and and then okay, there are a lot of places that without the power, and well, obviously I mean, there are many reasons for that, but one of the reasons is that, okay, some of the renewable energy, Texas have the highest wind power in the United States. And then, okay, when this wind power kind of stop in the west of Texas, and then the whole system has to collapse. So you can see that, okay, this can be a very dirty and very expensive kind of things, okay. And for this solar panel, okay, is typically regularly, and then this is a kind of a daytime and a nighttime. However, this is typically good for the places like Arizona where there's no rain. And for the regular places like Houston, it's not maybe the case like this. Sometimes it's very, very cloudy. And but it's overall, it can be relatively stable. And I feel that if you have this high voltage transportation from the long distance, then this solar power can make more sense with a solar power plant in the places like Arizona. However, for wind, it's very, very unpredictable. So this is the example for the hours, and this is wind. And in this case, okay, the estimation of the output is basically impossible. So in this case, okay, what we can do for this? And to overcome such kind of problem, and one possible solution is this kind of a microgrid. And so basically it's a kind of active island that's connected to the microgrid. In case of something happens, it will kind of, set up their own kind of generation and to satisfy the demand. And they also have the renewable energy or this kind of, but they need some kind of economy dispatch problem. But overall, you can think about some kind of places like the university or the hospital. And when the microgrid down, and well, those important places have to have the power supply. Otherwise, people will die, or they will have a huge loss. For example, in the building next to my department, there's a generator to support the university microgrid. And the key issue can be some kind of renewable energy and operation cost and the economy benefit, etc. Okay, on the other hand, okay, machine learning has experienced up and down during the last 50 years. And at the beginning, okay, in 1956, they have this kind of, the artificial intelligence was first proposed in Dartmouth. And then, okay, then it's going down in the late 1960s, where there's a kind of, due to this, some technical, some kind of, no equipment, no hardware can be implemented. And then in 1970 and the 1980s, there's a rebirth of the AI. And so basically, okay, they have a new algorithm. If you see the algorithm like this deep learning or all these kind of classic algorithms, they all develop in this period of time. And after that, okay, this kind of AI going down very quick. And in 1997, when I was a first-year PhD student, and I tried to say, okay, whether AI is a good idea. But at that time, okay, AI was a very, very kind of in the downturn, okay. In this popular kind of a conference, now at that time it's about 100 people attendance, but now it's more than 8,000, okay. And then, okay, time passed. In the 2014, 2016, the GPU was invented. So in this case, okay, the deep learning can be implemented by computers. Then it's caused a huge boom recently for this machine learning. So you can see that, okay, machine learning is going up and going down during the history. And now with this GPU, okay, the machine learning have bring many many important kind of applications. For example, face recognition, and for example, in China, okay, this facial recognition, okay, makes a fugitive, almost impossible to escape. And also, okay, people kind of, it's very safe in East Asia, because they have CCTV everywhere. And when you walk on the street 2 a.m. in the morning, it will be typically very safe. And the product recommendation, for example, for Amazon, and self-driving car, okay, this Elon Musk will have the number 5 biggest data center in the world to calculate the data collected by Tesla for the self-driving, okay. And virtual assistant Zero, okay, finally you can understand my accent, okay. And the email filtering, all this, there are many different kind of applications. If indeed they change our human life a lot. Okay, on the other hand, okay, for a specific problem, okay, they also bring this kind of opportunity and challenge. So basically, okay, the challenge is a weak energy dispatch capability and insufficient regulation capability. And the opportunity is that, okay, this microgrid provides a hierarchical structure and which can improve the scalability and scheduling for the renewable energy. And also there are some other problems like this communication problem. And the communication delay and communication fluctuation in wireless network and can affect the renewable energy. And on the right figure, we can see that, okay, with certain delay, okay, the control can make this this kind of things not ideal, okay. So, okay, given this kind of background and allow us to try to talk about for a preliminary trial, which is published very recently, just 3 months ago. And here we have this microgrid, and then we have the energy storage system. And also we have this distribution grid, which is the main grid. And then we also have the upper control unit. And also we have the wind turbine or this renewable energy, this kind of solar power. And the objective function is try to make use of the renewable energy to change the traditional way of power supply. So renewable energy is uncertain, and how to fully utilize this one. So our objective function is to maximize the wind and the power output accommodated at a different time and a different number of the microgrid. And so we assume that the cost of equipment and traditional energy output unchanged. And also we have a smaller the K-tail of the renewable energy is a smaller total cost. If we have this two assumptions, we can transfer the objective function into this minimized cost, where this cost can be related to the operation cost and the exchange power. And there are many different uncertainties, like this communication uncertainty, and also, okay, the communication uncertainty can be quantized in this way. For this kind of, here there are some mathematics for the cost variable, follow certain distribution, and then we have the extra cost. So basically this objective function can be represented in this way. And there are many different constraints. The first one is the power balance for the independent microgrid empirical flow. And here we can write into a certain matrix form and equality form. And then we have a power balance in the hierarchical microgrid. So basically, okay, and this kind of between the microgrid and microgrid, they should be follow the empirical flow. And if they meet each node, the priority should be given to the dispatch. And if cannot meet the requirement, then we need to shred this load. So basically, this is to keep the microgrid stable. And also, we have the constraint for the traditional generator. And I agree with the previous keynote speaker that, okay, there's no way we can replace this traditional energy generator. And also, yeah, except for the safety reason, okay, this nuclear one will have this minimum CO2 generation. Okay, and the output constraint of the renewable energy also follows some kind of constraint, and yeah, so we list it here. And also this kind of a battery, they satisfy this kind of a constraint, and just like we cannot charge and discharge our phone so quickly. So there are certain kind of charging constraint as well. And also we don't want the system to switch from the island mode to the connected mode too often. So basically we have this switching constraint. And well, obviously such kind of problem can be solved by some centralized server like this kind of traditional day-ahead marketing. They use this linear programming or this kind of out in the cloud computing. However, okay, we need some. This is a distributed network. Okay, there might not exist the central server. Moreover, we need to kind of calculate it in a quick way. So in this case, okay, this motivates us to utilize the distributed machine learning algorithm. And here we try to use the MDP Markov decision process. And this is Markov before he worked on the Markov decision process. After that, it looks very different. I'm just joking. Okay. And here they have the state, action, probability, and reward, which we will discuss later. And then, okay, however, the transfer probability is unknown. So in this case, we try to study it. And in this case, we use a temporal difference GAN, generative adversary network. For GAN, most people know that, okay, we have the generator and discriminator neural network, and the generator to make some fake things, and the discriminator try to tell whether or not it's right or not. If it's not right, the discriminator will tell the generator to improve until to a certain point that the discriminator cannot tell the difference, cannot tell whether or not it's from the real side or the fake side. If in that case, okay, the generator will tell the discriminator to improve. So in this case, okay, they will both generator and the discriminator will improve better. And here we use a temporal difference so that it does not depend on the prior probability. Okay, and for state side, we have a different state, and here we have the state of the energy storage and so on. So here is how we define the state. And for the action, we can have the charging power and switch power and renewable energy and so on. So this is the potential action that we have. And this is the transition probability. And so this is probability for the different state to transit. We use a GAN to study it. And also finally, we have the reward. In this case, if the previous state is st-1, and by taking action AT, we will go to the next state st, then what is the reward function that we will have? And based on this framework, we try to decide, okay, under this situation, what is the best action that we need to do? And so basically, okay, among the under this state S, what is the best action we need to do? For example, under this current condition of the COVID, and should I wear the mask or should I not wear the mask? Okay, so this is basically, okay, the optimal policy. The policy is like this one, this pi. And this one is typically, if you're using the Q-learning and or this type of reinforcement learning one, is typically can resort to this equation, which is a Bellman equation. Okay. And to further improve, I mean, for the reinforcement learning, the problem is that, okay, it will take a long iteration for this machine learning to interact with nature so as to get this response. However, okay, sometimes, okay, we do have this this kind of luxury to do that. For example, okay, allow me to say, okay, for the Chernobyl, okay, they have some trial, right? And then when they realize it's a mistake or it's too late. So in this case, okay, we typically want to train this machine learning to be more robust before they interact with this nature, interact with a real network. Otherwise, okay, it might cause some problem. And another example is that, okay, so in this case, we propose the actor critic. So what is the actor critic? You can think about the actor critic as a professor and a student. Professor and a student. Okay, if I ask a student directly go out, and typically, okay, they will make a lot of interesting mistake, unfortunately. So before they graduate, typically, okay, the professor and the student will interact with a lot. And in this sense, okay, the professor works as a critic and tell the student, which as an actor, say, okay, you shouldn't do that, okay, because blah, blah, blah, blah, blah. So get trained, get mentored. And in this case, okay, the actor will be well trained before he graduates and then face the real world. So this is a key idea for the actor critic. And in our work, we do the similar story to do the actor and the critic, so that, okay, when the machine learning really come to this reality, first it will become more material will not try some kind of stupid things. On the other hand, okay, it will be react to this kind of different situation and conduct the best performance. Okay, for details, okay, here we have the gun, and then we have this kind of update, and for the actor and the critic, and with the gun. For detail, you can check our paper for the details. Okay, here is some kind of numerical result, and here we have the three different independent grade, and also we have one upper control unit, and those are the parameters that using the simulation. And here we compare with this kind of deterministic policy gradient method, which is a classical method. And here is our proposed method. We can see that, okay, we can reduce the overall cost significantly. And here are some kind of other comparison with this cost of those days. And then, okay, we can see that, okay, by using this gun and proposed TD gun, okay, they can face a variety of the different situation, and will converge very quick. Okay. Anyway, so that is just a kind of one result for that one kind of related work. Okay. And here we talk about some other related work, and the first one is this security part. And for the smart grid, okay. And they have the different sensors, and these sensors will tell the SCADA system, the smart grid operator, about the current status of the network. And by changing those sensors, the SCADA system will make the wrong decision. So in this case, okay, they will have the either just like a Matrix 2, okay, the movie Matrix 2, okay, how the Trinity can bring down the whole building, the whole block's power, and then they just change this kind of sensor palaces, and then the SCADA system will make the wrong decision, so that when the power flow to there, they cause a shortcut and then black out the whole district. On the other hand, okay, this kind of wrong sensor can make this kind of system to make the wrong decision. So by doing this, they can make a huge fortune for that. And for example, more than 10 years ago, almost 20 years ago, okay, IRA, which is Houston, one of the biggest company in power trading company in the world. Okay, they try to buy this kind of California this power plant, and then deliberately shut down it. And after shut down it, California have to buy the power from outside, because Enron is a trading company. Okay, they earn a huge amount of money at that time. Okay, average California this household power summer power bill is more than $1,000. So after that, okay, I mean the U.S. Congress just got very mad, and then bankrupt Enron in 7 days due to the tax evasion. Anyway, so this is you can see that, okay, there's a kind of attack can not only cause this this kind of system bring down, but also can bring the financial benefit to some kind of malicious companies. So that is an important issue, and if you have interest, we also do some preliminary work there. Okay, for example, DOS and different type of attack. Okay, and our second related work is about big data. And the first one is about big data calculation. And as we know that, okay, we have the microgrid and then the main grid. And typically the constraint is a linear programming. And then we try to find this optimality and optimal kind of control for that. And because, as I mentioned, the microgrid is typically, okay, in a distributed way. So how could we do the calculation without a fully centralized one? And moreover, okay, if we do the fully centralized one, there are a lot of communication between the microgrid and the central server. In this case, they will cause a lot of kind of signaling. Moreover, if the communication link is not reliable, there will be a problem. So what we want is that, okay, we want to have this kind of distributed solution. But in this case, we try to say, okay, how could we make this centralized big data optimization into a distributed one? And here, what we do is that, okay, we use ADMM. And the key idea is that, okay, suppose we have an optimization goal, and suppose that, okay, we have a vector X, which is a huge variable that we need to change. For example, microgrid 1, microgrid 2, and main grid, all their kind of control variable. This can be millions of variables. And suppose we can decouple them. For example, okay, we can decouple the objective function into f1, x1 plus f2, x2. And this is typically the case. And then this x1 is a microgrid 1's control, x2 is microgrid 2's control. And then the constraint can also decouple. Okay. And in this case, what we can do is that, okay, we change to a augmented Lagrange multifunction. This is objective function. This is Lagrange multifunction. We add a kind of extra penalty, quadratic penalty. And then by doing this one, we can ask this kind of microgrid one to optimize its parameter x1 only. And then ask the microgrid 2 optimize its parameter x2 only without changing the information. And after that, in the third step, they try to average their Lagrange multiplier. And after that, this iteration, continue until convergence. And so this is, by doing this one, you can see that the computation and the data is only located within each microgrid. They don't need to exchange too much. And well, the information exchanged is just the Lagrange multiplier, which is a small vector. So how could we understand this one? And you can see that, okay, the California government and the Texas government, as we all know, the California and the Texas are two countries, right? Okay, yeah. For example, okay, I have joint funding with UCLA professor. I try to invite them for a kind of invited talk to University of Houston. And they replied that, okay, California government say that, okay, the state employee cannot go to Iran, Iraq, Afghanistan, and Texas. I'm not kidding, okay? So this is a kind of ridiculous, but you can see that, okay, the California government maybe try to optimize the resources for the left, and well, Texas government will probably optimize resources for the right. However, we have a US Congress, the so-called US Congress just average, right? This is the third step. And then this step, mine is go left, mine is go right, but after averaging, they're still in the middle and to achieve the system overall goal. So you can see that, okay, this is a overall kind of interpretation about this ADMM. And you can see that, okay, also the convergence speed is also relatively high. And moreover, such kind of step can be easily kind of implemented in the big data kind of area. We can use this, the first two steps in the map reduce is in like the map step, and the first step is like the reduce step. So in this case, this algorithm can be easily implemented in this cloud, in the cloud, okay. So that is the first, the second example. And the third example is that, okay, we try to use this big data for the machine learning. And this work is supported by Centerpoint and Direct Energy. And we have millions of smart meters data over last 12 years. And basically, okay, they for smart meter, they have the load profile. And here is a 24-hour. I cannot show you the real one, but those one are what I'm drawing. Okay, I have draw those one, and but it's very similar to the real case. So let's look at the blue line, which is a huge house. And in the morning, they do the breakfast and then go out for shopping. In the evening, they go back for dinner and so on. So this is a kind of CEO 1% and the audience here. And when we look at the red line, okay, in the morning I wake up and realize that it's too late for the breakfast, so I rush out to beat the traffic. And in the evening, I come back to this working, and I live in a middle-sized house. So basically, it's a worker, middle class, and a professor like myself. And in the third line, it's a very small apartment. And in the daytime, okay, they almost have no power consumption. At night, they have to work. So in this case, it's a homeless slave and a PhD student. Sorry, I'm just joking. Okay, and so this one, why we want to do this one? Because in the future, okay, when you try to buy the power kind of plan, what you will do is that you first type your smart meter data, a smart meter number, and then they load smart meter data. And if they found that you are CEO and 1%, and you guys, and they will try to sell you the renewable energy, even though it's expensive. But they say that, okay, you live in such a huge house, okay, you should save the earth. Yeah, so basically this is the case. And for this PhD student case, okay, they can try to sell the power plant, like for the daytime it's expensive, but at nighttime it's free. So this is also attractive to them, because at daytime they work in the lab, at nighttime they come to the apartment. And for myself, okay, I also like that kind of plan because I have the electrical car. And for electrical car, I can schedule my charging after the off-peak hour. So by doing this, I save all my kind of driving cost. So this is also a good plan. So you can see that, okay, why we want to use machine learning? Because by glancing at your smart meter, they realize what is the most likely kind of power plant you want to have, so that they will sell you the customized kind of power plant, power plant that you will not deny. Okay, so this is the third related work we are doing. And finally, we have the conclusion. And in this talk, we talk about the machine learning, and specifically we work in the microgrid and renewable energy, and we feature the optimization with a certain uncertainty, and the traditional model cannot work well. And on the other hand, okay, even though the machine learning is nice, but there are several challenges. First, if it's deep learning, it's a black box. Even though the performance is perfect, but it's a black box. So sometimes, okay, you don't have this kind of performance guarantee. For example, this kind of Boeing 737 Max, okay. Sometimes, okay, it's just you don't know what you don't know what machine learning will cause the trouble. So that is the reason. That's recently there are kind of a lot of work for machine learning to understand the underlying story of the deep learning and make sure that, okay, the performance can be guaranteed. And another thing is the convergence speed for this reinforcement learning. But unfortunately, we use this kind of actor critic, which speedifies this performance and also the gap. Okay, and we also talk about other applications like security and big data. And finally, okay, allow us to advertise about our lab. First of all, thanks. And our lab, okay, have a beyond study, I mean, except for study, okay, we do everything else, okay. So there are a lot of opportunity to study and play together. And I hope in the future after COVID, everybody keep safe. And after COVID, if you have opportunity, do visit us at the University of Houston. And you can go to our lab website or my own website for more details. And I hope that, okay, we can collaborate and study together.
Thank you very much, Professor Han, for your very nice presentation on distributed deep reinforcement learning, and renewable energy. Now it's time to have the opportunity to ask questions to Professor Han. If you have any question, please use the Q&A option. We have time for questions. So in the meantime, I would like to ask my question. So do you think it is necessary to combine physics-based models and distributed deep reinforcement learning models?
No, I didn't get your question. To combine what?
Do you think it's necessary to combine physics-based models and physics-based models, yes, and distributed deep reinforcement learning models?
Yes, I think that is a good idea. Okay, and I think you can easily put the physical model as a regulator in this kind of objective function in the deep reinforcement learning. And typically for deep reinforcement learning, okay, is unconstrained, but you can have the penalty function for your constraint so that okay, all this kind of physics can be satisfied. Okay. In your paper, we indeed put that into the physical put the physical model into the deep reinforcement learning. But I should say more for that. I should elaborate more for that. Okay.
Sure. Great. Thank you very much.
There's one question.
Yes.
Yeah.
Exactly. We have one question from the audience, Professor Ibrahim Dinçer.
Okay. If we hybridize renewable energy source in multiple with a conventional system, what extension will be required to manage it with machine learning? Okay, I think, I think for the renewable energy, okay, there are some kind of, I think there are certain probability that it cannot work. But with the historical data, okay, sorry, I should say in this way. With renewable energy, there you can get this kind of distribution, and for this uncertainty, and with such kind of uncertainty, we can put into this kind of together with a conventional network, a conventional system, which conventional system can reduce such kind of the penalty for such kind of uncertainty. Right, and in this case, okay, they can work together well. And for example, okay, if you know that for example, there's a trade-off between the system stability and this kind of renewable energy. For example, if the renewable energy is under 20%, the current existing conventional system can maintain the system stability, because just in case there are certain probability that this renewable energy cannot supply the source, the current conventional system can still supply to get to fill the gap. On the other hand, okay, if the renewable energy is too high, renewable penetration is too high, and then okay, well the conventional system cannot fill the gap. So in this case, okay, from my personal point of view, the best strategy is to have this power supply infrastructure. For example, those are high voltage, right? So if, for example, Texas do not have the power, and they can attract some power from the nearby to help it. So in this case, it can help. Well, for the machine learning, okay, I will say that, okay, well, for the traditional power, it's a linear programming. Then you can using this kind of traditional OR optimization in a very, very efficient way. However, with the renewable energy, there are many things which you have no model, no idea about it. So in this case, the machine learning looks like, even though it looks like a black box, but machine learning is very good at dealing with this dirty work. In other words, there's no existing model that already can, and then machine learning, because it's non-linear things, and it can handle such things very well. So to answer your question in short, if the conventional system, if the conventional optimization, traditional optimization can solve the problem, then we don't need to the machine learning. However, there are many things like the renewable energy uncertainty that the traditional optimization cannot do a good job. In this case, machine learning indeed can help. So that's my point. Hope I answer your questions.
Yeah, thank you very much for your kind response, and thank you very much for Professor Ibrahim Dinçer for the question. So, is there any other question? I think we have a little bit more time for the question from the audience.
Okay. May I ask you one question?
Sure.
If I'm not mistaken, eventually you are from Texas. Which lessons have been learned from the electrical grid disaster? I think it was due to freezing rain and very low temperatures, yes, this year.
Yeah, I think there are so many debates for that. Okay, different people have a different opinion, and indeed, okay, and yeah, that's a huge. I think among the things is a kind of obsolete infrastructure. And if they have this kind of example, if they have the power connection to the other state, high voltage one, and it will help them a lot. Unfortunately, we don't have that kind of infrastructure. And the other thing is that, okay, during this during this kind of disaster, okay, unfortunately, the capital, the winner is, the loser is Texas. The winner is Wall Street. Whenever there's a disaster and the power price, okay, 1 kilowatt is $9, at that time, okay. At that time, I'm thinking, okay, it's better to go out to take this 5-star hotel to stay at home due to the power. So I shut down my home power and then go to the 5-star hotel, okay. So I feel that, okay, the regulation for such kind of power marketing is also have to be considered. Otherwise, that, allow me to say something, if somebody say, some political say new Green Deal, are they really care about the earth? No, they care about the money behind. Yeah, allow me to be frank. Okay.
Okay, thank you very much.
Okay.
Thank you very much, Professor Igor Piara, for the question, and thank you very much, Professor Zuhan, for your kind answer. So, I don't see any other question from the Q&A session. So, thank you very much for your presentation. I think with this, we can conclude our keynote session. And I would like to thank once again our speakers, Professor Igor Piara and Professor Zuhan, for their really kind and informative presentations. And I would like to thank all our participants for joining this session and asking questions. Now, I would like to wish you to enjoy the rest of the conference. Thank you.
Okay, good. Thank you very much. All the best.
Thank you very much. All the best.
Bye-bye.
Good morning, Dr. Mohammed. Can you hear me?
Yes, I do. How are you?
Thank you very much. You're welcome.
So I presume I can share the screen, right, for my slides?
Yes, please. The green, the below.
I can do that. Can you see my slides?
Yes, please. Please make a full screen, please. That's okay. Good, very well.
So how many people are attending this conference?
Normally, you see that this is quite big conference. They have three sessions at the time. At that time, I've seen a participant like 23 people, but I believe that more people.
How many?
In the screen, I can see 23 participants, but I believe that more people.
You mean for this session?
Yeah.
No, I mean, how many people are at the conference total?
I don't know really.
So are you a professor?
Yes, yes, I am in Izmir. I'm in Izmir Institute of Technology.
Very good.
We have just 1 minute. We can start 1 minute later. Okay?
Fine.
Okay. Dear distinguished participants, ladies and gentlemen, my name is Alper Baba. I'm from Izmir Institute of Technology, Izmir, Turkey. First of all, I would like to thank the organizing committee of the Turkish Academy of Science. I am sincerely thanked to the keynote speakers. Thank you taking time to speak in the TÜBA World Conference on Energy Science and Technology. Dear distinguished participants, ladies and gentlemen, really we have three important keynote speakers today in this session. In this session, we are going to discuss about optical expansion and operational planning of the microgrids. And then also we are discussing about the global geothermal outlook. And then we are also discussing about the sustainable battery chemistry for immobile and renewable energy storage. Please use the chat box. If you have any question, please write in the question and answer section. Now, first, I would like to invite the first key speaker, Professor Dr. Mohammed Shasipour. Dr. Mohammed joined Illinois Institute of Technology in 1983, where he is presently a university distinguished professor. He also served as the Bobbin Chair Professor, Director of the Robert Galvin Center of the Electricity Innovation, and then Association Director of the Wenger Institute of Sustainable Energy Research at the Illinois University of Technology. He is a fellow of the American Association for the Advancement of Science, fellow of the National Academy of Investors. He elected member of the United Nations Academy of the Engineering. He is listed as highly cited research on the Web of Science. Ranking is the top one. Thank you very much, dear Mohammed. You are welcome. Dr. Mohammed will be speak about optical expansion and operation planning of the microgrid using a two-stage full data clustering strategy. Yes, dear Mohammed, floor is yours. Thank you.
Thank you very much. My name is Mohammed Shahidpour. I'd like to thank the organizers for inviting me, in particular Professor Baba, for chairing this panel. The title of my talk is Optimal Expansion and Operation Planning of Microgrids Using a Two-Stage Full Data Clustering Strategy. Of course, it's sort of a technical presentation, and what I would like to do is I'll talk about the microgrids a bit, then I'll talk about the expansion and operation planning for a microgrid, and I present the results. So let me spend a few minutes to talk about microgrids. So in a sense, the first microgrid was built by Edison. You see the picture of Edison here. And it was built in the lower Manhattan back in 1880 and 1881. And then you still see the remnants of that in these figures. So there are two things that Edison did that are very important. One was that he built the DC system, DC microgrid. And interestingly, we are going back to the days of Edison. We are building a DC system, and also we are building microgrid both. DC is getting more and more important, primarily because the generation is DC, you know, solar panels are DC, and the load is getting to be more DC. Your laptop, your cell phone, LED lights, these are all DC loads. So the load is getting DC and generation is DC. So it makes sense to consider DC as a means of transmitting electricity. And we resorted to AC so many years ago, primarily because there was a significant distance between the generation and the load. Like you use hydro, and that was a long distance. So you have to use AC in order to reduce losses. Those days, there was no DC transformer. Transformers were AC, so they increased the voltage in order to reduce the current, and that's how the business was managed. But nowadays, because the distance is much shorter, you put the solar on the roof of the house, the loss is not an issue anymore. So it makes sense to consider DC as a way of transmitting. And the second thing that, as I pointed out, that Edison did and was important was to build a microgrid. Now, of course, those days, there was no infrastructure for electricity. So he built this power plant in the lower Manhattan, pulled the wires to neighboring homes, primarily very rich people who could afford electricity. And that's how he built the islanded microgrid. And as I said, we're going back to the days of Edison. We're talking about microgrids. We're talking about DC. So after all, Edison wasn't that, you know, off the line. So what is a DC, a microgrid? So what you see here on the left side is a microgrid. It's connected to the local distribution grid. So this microgrid, there is a tie that connects these two. In case of an emergency, you can open this tie. So this microgrid will go into an island mode. So this microgrid basically in a normal day connected to the local system. And in case of an emergency or extreme events, it goes to an island mode. And it's got its own generation. It's got its own load, and it can be managed as necessary in case of an emergency and an island. So what's the benefit of building this microgrid as a building block of smart grid? It can locally integrate renewables and other distributed generation sources and provide reliable power to customers. So if you have local resources, as I pointed out, the distance is very short between the generation and the load. So you can essentially build this islanded system as much as necessary. It can protect critical infrastructure from power outages. So in case of an emergency, when you go to an island mode, this system can supply its own load. So even if the larger system is an outage, you can protect this system. So in this case, this could be a critical infrastructure. It could be a hospital, it could be a police station, it could be a military operation, whatever that is, you can make sure that the light will stay on within the system, even if the larger system is an outage. You can also ensure that a critical operation can be sustained during prolonged utility power outages. So if this system is an outage for a number of days, like if there's a hurricane, like what we have in Florida, or events that occurs in the northeastern part of the United States, these microgrids will remain in operation as long as you can supply energy to the system, either through natural resources like solar and the wind, or let's say gas or diesel or whatever else is available. So in this case, we're not talking about revamping the electric power system. We still have the electric power system in the form of generation, transmission, distribution. But what we're talking about is converting the system to the grid of the grids. So defining these clusters to the extent that they can be islanded and individually they can satisfy certain mandates. Like the objective in a hospital would be different from the objective in a police station. So they satisfy their own objectives. And once the system is back to the normal operation, they all be integrated. So one example of that is a microgrid that we have built at the university. We are located about 2.5 miles south of downtown Chicago. This is the downtown Chicago figure. And this is the footprint of the university. It's not a very large university. It's a technical university. Student population is about 10,000. And we have converted a whole campus to a microgrid that you see here. So here we have a certain number of loops, 7 loops. Loop number 1, loop number 2, loop number 3. There are 2 substations. This is the north substation. This is the south substation. Substation is where you connect the system to the local distribution system. So these are the individual buildings within the system. So each loop comes with individual buildings. So the entire campus here is converted to a microgrid with 52 buildings. So in case there is an emergency, we can open the switches at these 2 substations and the entire system goes into an island mode and we can supply the load. So we have a system that decides how you supply the load in a day ahead. And we can buy power from the grid and generate as much as we can ourselves. So the peak load is about 12 megawatt, the average load is about 9 megawatt. And we save the university about $1 million annually by operating it as a microgrid. The savings come primarily from demand response and reduction in the cost of buying power, as well as the reduction in the operational maintenance, because setting up it as a microgrid has reduced the cost of maintaining the system in case of an emergency. So in a sense, this is the representation of the system where the power comes in at the 12.47 kV from the utility. It's downloaded to 4160 at the distribution level. And then these are the 7 loops I was talking about. So loop number 1, loop number 2, all the way to loop number 7. And as you see, each loop comes with its own buildings. And then these are the Vista switches that allow these switches, basically these buildings to talk to each other. So in case there's an outage, let's say if this section is an outage, because it's a loop, we can still connect the system using the other side. So you see a number of PV installation, battery installation. So out of this 12 megawatt, average load of 9 megawatt, our generation is about 9 megawatt. And we can go into an island mode at any time. Usually remain connected at the point of common coupling to the utility grid. However, in case of an emergency, we open the switches at these 2 substations and the system goes into an island mode. So it's a really interesting system that shows the microgrids work. Now, in this case, we have set it up with the goal of enhancing our reliability, but also we are reducing the cost. Now, this operation could be a hospital, it could be a military installation, as I pointed out. In all those cases, you would set up the system to the extent that you could manage it for the day ahead, identifying the amount of load that needs to be purchased from the utility system and reduce the cost of operation. So this microgrid comes, as I said, with its own components, a wind unit. It comes with several charging stations. We also have demonstration setups for people who want to learn about microgrid and how it operates. One of the great advantages of microgrid is to operate it in case of an emergency. So one example of that is a hurricane, set of hurricanes that happens in the northeastern part of the United States, or what happens in Asia, and really devastates the system. So using this microgrid, you can really bring the system back into operation very quickly. Now, of course, we have set up the model as a sort of a stationary microgrid for certain buildings. You can also do a mobile microgrid where you can put generation on the back of the truck and move it around for emergency operations in different parts of this devastated system. So here, for instance, you can see the operation without a microgrid. The system is in the normal operation. It's shown here. This is basically the performance of the system as a function of time. And the system is operated. Here is at the normal steady state operation. Then in case of an emergency, system goes through degradation. Here is when the system is at a down state, then you rebuild it and go back to the normal operation. When you have a microgrid, this red line moves, the black line moves to the red line. As you see in the case of a red line, when you have the microgrid, the duration of the outage is shorter. And also the system performance is improved. You've gone from this point to here. So you can see from this curve, the bathtub curve, the real advantage of having a microgrid in place. So if you sort of look at it from here, the system originally was in the normal operation. Then you went to the degradation, which is here. Then the system is an outage here. And then you rebuild the system and back to normal. This is without a microgrid. Now, in case of a red system, when you have the microgrid, what will happen is that this part that's on outage is converted to a sustained system. Basically, now, because you have the microgrid, the entire system is not an outage. Part of it could be an outage, but using this sort of a distributed technology, you can keep the system in a sustained operation. In a sense, it's not totally out. So it's a great advantage, as you see here, that it allows the system to be operated both at steady state for satisfying certain objectives, could be reliability, security, resilience, sustainability, economics. For any of those objectives, we can build a microgrid. But in particular, in case of an emergency, these microgrids in the island mode can satisfy great advantages as far as keeping the system in operation. So in a sense, what you do in this case is the robustness, then the responsiveness, and the recovery of the system. So in this case, this system robustness is where you're, before you have any outages, then system responds to the outage and then recovers at this stage. So you can go through the planning process in order to make sure that the system is ready for these three stages. And then that's what I'm going to talk about as to how we plan the microgrid to make sure that we can respond to all these stages, both at steady state and in emergencies. One other thing before I sort of discuss the planning is that we are sort of moving into multi-microgrid system in Chicago. So what you see here, this is part of the footprint in Chicago. The red area shows the university microgrid that I just talked about. And sort of the dark area, the black area here, shows the part of the system that's owned by the local utility in Chicago, which is ComEd. So our peak load is about 12 megawatt. The peak load here is about 10 megawatts. So in this part of Chicago, we have a total of 22 megawatts of load that in case of an emergency can be islanded and operated. So these two microgrids can talk to each other to the extent that in case of an emergency, they can exchange power and keep the lights on. So this is a project that's funded by several projects related to this, funded by the U.S. Department of Energy. And we have a large number of sort of participants, Quanta, SNC, Schneider, Alstom, Microsoft, OSIsoft, they all participate to make sure that these two systems will be operated in a fashion that you can keep the lights on even in case of an emergency. So here you can see that this is the university's operation, this is the ComEd's operation. There's an underground 12 kV cable that connects these two systems. And in case of a normal day like today, these two systems both perform and satisfy their own objective. However, in case of an emergency, they both go into island mode and they get connected to this cable and then they start exchanging energy. So great advantage for this distributed system that can satisfy the objectives and keep the lights on in case of emergencies. So let me start talking about how this microgrid planning works. In a sense, what are the conditions to make sure that these microgrids satisfy certain objectives that you have? So the penetration of renewable energy sources, I mean, the reason we build these microgrids, primarily making the generation closer to load, is because of the advent of these renewable energy sources, RES, that have come into microgrid operations. However, as they sort of make the system to be, much more versatile, they also bring many challenges in the sense that when you build this system, the microgrids, you have to consider the fact that you have limited number of resources as opposed to a large utility system that has a number of generations. So this small system comes with its own challenges that you have to deal with for managing an optimal microgrid. So in this case, we use the planning model in order to find the optimal expansion of the system and the power generation of the system, to find the optimal size for energy storage, and also optimal configuration for the distribution lines. As I pointed out, in case of an IIT, the microgrid that we have at the university, we built the 7 loops into the system. Now, whether you have a radial system or you build the 7 loops or 10 loops or 3 loops or whatever, there is no formula. So depending on availability of the resources, depending on how critical the operation of the system is, you can configure and reconfigure the distribution system along with the resources that you have in order to be able to come up with the optimal operation. Now, of course, in the case of a planning of the system, the objective most of the time is to minimize the cost of planning, basically reduce the investment. But at the operational level, you satisfy certain objective. So the point here is that the existing planning models lack strategies considering both long-term horizon and finite time resolution for all the system operations. So a lot of times we do plannings, basically investments separate from operation. And the point I'm making here is that the investment and operation would have to be planned together, because a lot of times you may come up with the investment plan for your system that in case of an operation, it doesn't satisfy the constraints that you have. So in a sense, you have to put together a plan that includes both investment and operation. So in this case, it's also important to consider finite time resolutions for the operation of the system, because when you do the investment is for 20 years, whereas the operation of the system is, let's say, for day ahead. So in case of an operation, you consider a much finer resolution. You consider hourly for the ahead or for the week ahead. Whereas for the investment, you're talking about the next 5 years, next 20 years. So in a sense that the duration of operation and the duration of the optimization that you do in these two cases are quite different. So it's very important to select the reduced representative operation period. We call it ROP in this case, because the point is that, let's say if you're doing the planning for the next 20 years, if you consider the number of hours that you have, it's about 20 times 8760 hours. Each year is about 8760 hours. So 20 times 8760 hours. So here you're talking about a significant number of hours that you have to consider if you go with a finer resolution and satisfy the operation constraints. Whereas if you consider the larger horizon, which is for the investment, you only have 20 of those. So in a sense, what you would have to do is to come up with a representative operating periods or ROPs in order to be able to combine the investment operation with the investment planning, the operation planning, in order to be able to put these two together. So in order to do that, here we use a two-stage full data processing approach for microgrid planning. This is a two-stage because at one stage you do the investment and the second stage you do the operation. As I pointed out, the time horizon for these two are quite different. That's why we go with the ROPs in order to be able to match them. So in this case, we use the chronological operating period, the clustering algorithm, to merge the data that you have for the investment and the data that you have for the operation. So for this case, we use basically, in order to make sure that the chronological operation works, we use the two time series for the two resolutions. One is the reduced time series, RTS, and the other one is the sequence preserving time series, SCS, in order to make sure that the larger time horizon and the shorter time horizons match. In this case, SCS is applied to realize the use of energy storage. And that's very important because the issue with the energy storage is that, or basically if you have any other type of device that has ramping in it, that the solution at, let's say, at time equal to 1 is part of solution at time equal to 2, because it takes, let's say, several hours to charge the storage. So in a sense, you have to make sure that these hours are linked, both from the investment point of view and also from the operations point of view. So using SCS, we make sure that these steps or time steps are linked. And then the accurate planning of the storage devices in microgrid would consider the long-term dynamics as well, in the sense that you would have to consider the long-term dynamics of these elements that have, from the time point of view, there's a coupling between them, both at the investment as well as operation. So this is different from the most other ROP selecting approaches that have been proposed in the past, because we make sure that the chronological order in the planning horizon is maintained. So one example here is if you want to use, I'm going to talk about different sort of models that we have used here in order to compare them with the two-stage approach. The two-stage approach is the one that I've used in this presentation. However, I use the representative day that I call it RD and the representative week, and then a couple others that in order to be able to compare the solution with the one that we come up with for the two-stage approach. So for instance, here is the representative day approach, where what you do is that, let's say if you've got the 365 days in 1 year, and then you're doing planning for 20 years, the number of days that you have is 20 times 365. Definitely you cannot consider all of them because the size of the data is so large. So what you come up with is the representative days. So for instance, you consider 1 day in the summer and 1 day in winter, 1 day in year 1, 1 day in year 2. So you have representative days. The problem with that is that there is no chronological order in this case. I mean, basically, when we use the representative days, we don't consider that. So we take certain days from different periods and then do the sort of an operation study for those days. So each day comes with a certain number of hours, and then that's how we sort of do the investment and the operation study. Whereas in the case of a two-stage and the fact that we use a time series, we make sure that the chronological order stays in place. So that's the significance of this work, that makes sure that not only you identify the certain weeks in this case, and then based on that certain hours, that system satisfies the fact that you have elements that tie the certain hours at the battery operation in order to make sure that they come up with a solution and it's meaningful. So this is a flow chart of the system. I'm not going to go through all of this, but it has certain stages. One is that we do the pre-processing. The first stage, we identify the weeks that are representatives. Stage number 2, we identify hours that are represented within those weeks. And then we run the case and finish the process. So in this case, the operating point selected by the ID approach, as I pointed out earlier, only maintain time continuity. And there is no chronological order in this case. Whereas in our case, when we use the two-stage, the TS approach, we make sure that this chronological order is maintained. Let me talk about different stages, basically the process within this flow chart. The first one, as I showed in the flow chart, was the pre-processing, where in this case, we make sure that all the required data are available. And basically, if you're doing this study for 20 years and each year has 365 days, you make sure that the data, as far as the load and potentials for renewable energy and the wind energy and all the other components that we have, already made available for all those. In a sense, you have to do the forecast. I know the forecast for 20 years may not be exact, but you come up with the forecast as to how the system is going to look like, in particular for the load, in order to be able to do the system planning. At the first stage, you identify the operating weeks that we are interested. So weeks, if there are 52 weeks in a year, we identify the weeks, the certain weeks, let's say that we pick the weeks that represent, like, let's say summer or winter, or if your system is the summer peak, to make sure that there are more weeks available in the summer. If your system is the winter peak, to make sure that there are more weeks available in the winter. You identify those, and then at the second stage, you identify the hours. So here you identify the hours, operating hours within those weeks. So within each week, you identify hours. For instance, you identify the peak hours or other hours. That would be stage number 2, and then you run the case, and then finally you put the results together. So there is a mapping from the SCS to RTS, and that gets to be very important because both RTS and SCS, these are the time series, mark the data processing results. So there is a mapping relationship between the SCS to RTS that gets to be very important to make sure that we maintain the chronological order of the system. So in this case, SCS is an extension of RTS in which the multiple time points can correspond to a single point operating point in the data processing results. So I've discussed these subjects a lot more and in details in some of the publications that we have had on this subject. Here I'm just referring to it and then go through that in order to get to the results. So let me talk about a little bit about this case study. So in a sense, as I pointed out, what we are interested is to put together a two-stage, where in stage number 1, we identify, let's say the weeks or the larger span of cases that are necessary for planning investment. And then stage number 2, we come up with the final resolutions that are necessary for operation. And then we sort of come up with a strategic solution between the investment and operation until we come up with the final solution. So here it's a simple system that it comes up with the number of batteries. These S values represent the batteries in the system. You also have a wind unit, you have a solar unit, and then there's a diesel. And then you've got different loads in the system. So here these S1, S2, S3s. S1 is a lithium ion, S2 is a lead acid, and S3 is a pumped storage. So different types of storage devices. And then here you see the information on these generation resources. C represents the investment, O represents the operation cost, and the number of years, and basically the information on in the system are listed here. And then for the storage parameters, you'll see the number of hours that the battery could be in operation, the efficiency of the unit, and the cost of the battery, and the lifetime of the battery. So here you see the lifetime of the generation. Here you see the lifetime of the batteries, depending on what type they are. Here's a conservative case, for instance, for the lithium ion, we assume the good life is about 10 years. For the pumped storage, we assume it's about 50 years. Now, these numbers are very typical. They can change. But here, what we are doing is that we are assuming that we are designing this system, and the generation is given, information on the storage is given. We know the value of the load. And what we are interested in is identifying what would be the capacity if we want to install this battery and generation at a given location. So we run these cases. Now I'm comparing 4 different sort of strategies here. RD represents the representative day. So first we have the original set of data. Let's say if this is for 1 year, in this case, we're talking about duration of 1 year, about 8760 hours. We have the original data. The other one is the representative days. Representative days means that here we consider a number of days in the system. Representative weeks means we consider such a number of weeks. CC stands for the chronological clustering approach, and then the 2-stage is a TS. So we are comparing the 2-stage with some other sort of existing methods to see which system gives you the best solution. In all these cases, of course, we have set it up in the way that the TS represents the best solution. So you can see that in this case, the TS, which is the red one, is the closest, I mean, visually, closest to the original data. When the load is a data in this case. Same thing with the solar and the wind. So in a sense, we have the load data and we want to make sure that we satisfy the load as much as possible. And then as you see, we are able to satisfy the load the best here. And then here is the solution for the solar and then solution for the wind. So in this case, we have evaluated the accuracy of ROP for different data processing approaches. So in this case, the ROPs that we are using the representative days, in this case, representative weeks, in this case, the clustering approach, and then the 2-stage. And then as you see, the best solutions that we get in this case are for the TS and the RD. So the TS and RD in all 3 cases represent the best solution. And then the worst solutions are for the RW and the CC, the chronological clustering approach. And the representative days gives you the better solution, of course, because you're considering a finer time period, you're representing a certain number of days, and RW representative X does not give you a better solution because you're going with a wider span for the cases that you have. That's why you don't get a better solution. Then here you see the correlation first of all, we consider the RMSD, which is the root mean square, to see basically for these four methods representing the load, solar, and the wind, what's the root mean square deviation in this case, using the representative day, representative weeks, the CC method, and the TS method. And as you see, in all these cases, for satisfying the load, the forecast for the solar and the wind, the two-stage solution that we propose gives you the best solution. So again, the two-stage that uses this time series, as you see, the deviation, the errors are the smallest in this case. And also regarding the correlations, the correlation between the load solar, load wind, and the solar wind, in these cases, again, you'll see that we sort of get the best solution when you use the two-stage approach. And graphically, you'll see it here as well. So the TS is a red one, and then the circle is original. And then as you see in all these cases, the red is the closest to the circle, pointing out that from considering the correlation of the system, the two-stage approach gives you the best solution. And then here we see the overall planning results. The benchmark is the original case. And then this is the planning using the representative and the error, planning using the weekly data and the error, and CC error and the TS error. And as you see, the error in the case of a planning using the two-stage solution, in all these cases, gets to be the smallest. So this is the overall cost. This is the amount of solar, amount of wind, amount of diesel, the batteries, and the design of the line, distribution line of the system. So in all these cases, this is the best case. So in this case, the planning results using different data processing approaches and planning models are compared in this case in table 5. So the raw data containing 8760, we're considering only 1 year, is employed for microgrid planning in order to be able to compare different cases. And then you see in this, in general, the two-stage solution that we propose gives you the best solution and most appropriate compared to all the other ones. And that's an indication that the two-stage and the essence of the two-stage approach that we're presenting here is to make the final resolution for the operation to be much closer to the investment, which is a longer period. And then it goes on here, again, you see that the absolute value of the error for the cost and the computation time, you see in all these cases that for the cost for the two-stage approach and also the computation time for the two-stage approach gets to be the best. So let me conclude here. So again, we propose a two-stage solution, and then we compare the solution that we get from the two-stage with the representative day, representative week, with the chronological clustering approach. And we demonstrated that the two-stage approach gives you the best solution in this case, because the two-stage approach gives us a time series in order to make the final resolution for a number of hours closer to what you have from the raw data. So in this case, we propose a planning approach based on the two-stage to deal with the challenges that exist, for different time periods. And then in this case, we have reduced the number of time that we have in the planning horizons, and then we represented the solution. I think I better stop here because my time is up. And I'll be happy to answer any question that you may have.
Dear Dr. Mohammed, thank you very much for your excellent talk. It's really very interesting and it is very applicable. Any question, dear my colleagues? Okay, I have one question from Nader Javani. They ask, thank you for this informative presentation. All the criteria of microgrid hubs propose a more resilient system, but is there any optimized cost for the create microgrid hubs? They want to know that the optimized cost for the credit microgrid hubs.
Well, I pointed out that the microgrid that we have at our university, we save the system about $1 million annually. So yes, if you operate the system in a optimal fashion, there will be savings which comes through demand response reduction in the maintenance cost, as well as reduction in the generation, because you don't have to buy as much power from the grid when you've got your own resources in the form of solar, wind, and the battery. Now, of course, there is an investment cost. No question that at the beginning, you would have to come up with a cost of installing the battery, cost of installing the solar and the wind. However, when you consider, let's say in the southeastern part of the United States, the amount of money that is spent every year to fix the system after the hurricane hits, and knowing that if you had a microgrid in place, you could have been able to bring the system back into normal operation much quicker and save lives and save operation, the overall cost of the system gets to be much more optimized in case of an microgrid compared to a traditionally utility-based system.
Okay, dear Dr. Mohammed, thank you very much for your nice talk. Thank you very much attend this important congress. Sorry, we have a very limited time. I believe that many people ask questions, but I hope that they will contact you later. And now I am going to move to the second keynote speakers. Our second keynote speaker is Dr. Ronald Horn. Dr. Ronald Horn is the professor of Earth Science at the Stanford University, United States. And then also he's a director of the Stanford Geothermal Program. Also, Dr. Ronald is a member of the United Nations Academy of Engineering and honorary member of the Society of the Petroleum Engineering. He is also fellow of the College of Engineering, University of Tokyo. And then he is also honorary professor of the China University of Petroleum. Thank you very much, Dr. Ronald. You are welcome. And today, Dr. Ronald give you information about the global geothermal outlook and then sustainable development of 2021. And then also I saw the pictures behind the Dr. Ronald about the World Geothermal Congress. Yes, please, floor is yours. You're welcome.
All right, thank you very much. So I'm going to talk to you today about geothermal energy development and somewhat in the context of renewable development in the world in general. And I should emphasize that a lot of what I'm going to talk about today is derived from two papers that will be presented at the World Geothermal Congress actually in October in Iceland. And the authors of those papers were Gerald Hutra, John Lund, and Annika Toth. So if we take a look at the geothermal world, every 5 years when we hold the World Geothermal Congress, actually we have an inventory of the resources of the planet. And so this is an up-to-date image, at least of 2020, of where we are. So collectively across the globe, we're producing at the moment close to 16 gigawatts of electricity from geothermal sources, and projections of projects which are underway are to take us to close to 20 gigawatts by 2025. So you can also see that the geothermal industry globally has been expanding modestly for quite a long time, more than 70 years. So in the World Geothermal Congress, these two papers I'm going to draw from their information actually are summaries of 88 different country updates. So there are 88 countries of the world that are using geothermal energy, about 20, 25 of them for generation of electricity, as well as others that are using geothermal heat directly. And I'll talk about that in a moment soon as well. And as I emphasized earlier, those papers were written by others. You see their names here. So if we take a look at the recent past of where geothermal activity has taken place, although globally we have expansion steadily over that period of time, it's important to note that the greatest activity has been concentrated in a relatively small number of countries. So what you can see in this stacked chart are the countries from the largest producers at the bottom to the smaller producers at the top in 2018 at least. And you will notice that there are some countries that have expanded very rapidly during the last 10 years. So in particular, Indonesia, and importantly, Turkey, very much so, and finally, Kenya, New Zealand to some extent as well. So there are some very important hotspots in geothermal activity in more ways than one in terms of development over the last 10 years. So it's a dynamic industry and it changes continuously from one year to the next. And importantly, if we take a look at the countries which are really active in generating electricity, at least from geothermal sources, this is the list of the top 10. There are another 15 or 16 countries with smaller generation than these. You can see that the United States, which is where I am currently, is number one. And actually the state of California, also where I am, is by itself close to the top, were it to be a country. Indonesia is the second, and you can see the list there. Importantly, this list has changed dramatically over the last 5 years. Japan, for example, 20 years ago used to be number 4 or 5. Now they've dropped to number 10. New Zealand used to be number 1 or 2. Now it's dropped to number 6. So the activity has been concentrated in relatively new countries. Both Turkey and Kenya have been using geothermal energy for quite a long time, however, in relatively small ways. Kenya now has a very significant fraction of its new generation in the nation from geothermal sources. Turkey, not as big a fraction, but a much bigger increment in actual generation. And this is all of the countries actually that have added electricity over the last 10 or 5 years since 2015, the previous World Geothermal Congress. And you can see there's a very significant number. Not all of them have added as much as Indonesia and Turkey and Kenya, but there's been a steady rate of increase in quite a number of places. There's 1 or 2 countries which have actually added some and subtracted some as plants have opened and shut in different places, but a lot of activity taking place across the world. So in terms of who has added the most, so who's been most active recently, again, Turkey is number 1, gold medal for Turkey in terms of geothermal electricity. Indonesia is number 2. Indonesia used to be the number 3 country worldwide for geothermal, but they have in the last couple of years overtaken the Philippines to become number 2 worldwide in total. Kenya's added a lot. The United States has added a lot too, although it's a smaller fraction of our total. And then you see these other countries, Iceland, El Salvador, New Zealand, Costa Rica, Chile generating geothermal electricity for the first time, and the Philippines with some new developments. Now, let me also talk about not just electricity, but direct use of geothermal energy, because that's important in many countries too, many more actually than electricity. And there are many ways in which we can use geothermal energy directly for recreation, swimming, bathing, balneology, health, spas, etc. Space heating and cooling, that's a very prominent application in Turkey. Agricultural applications also prominent in Turkey, growing bell peppers, tomatoes. They grow bananas in Iceland, if you believe it or not, by warming greenhouses with geothermal heat. Growing tropical fish. There are applications growing shrimp, prawns, etc. in some countries, and industrial processes, including, for example, wood pulp industry in New Zealand. It's a very large consumer of geothermal. Food drying in many countries. And finally, geothermal heat pumps, which are prominent in Europe for heating and cooling in places which you would not traditionally actually associate with geothermal energy, as we do in the volcanic countries that generate a lot of electricity. And I'd like to talk for a moment about this diagram that was published some years ago by Jeff Tester, at that time at MIT, now Cornell. And he and his co-workers did a study of how heat is used in the world today. Well, this is the United States. And you can see in this diagram, importantly, first of all, the amount of heat which is used in exajoules, that's the height of the bars, and the temperature of which it is used, as well as all of the different applications that you see in various colors. And what's immediately apparent in this diagram is that a lot of the thermal energy that we use in the United States, at least, and it's true of many other parts of the world as well, is used at relatively modest temperature, between 40 and 80 degrees centigrade. And that happens to be a temperature which is completely suitable for geothermal application. If we want to generate electricity with geothermal hot water and steam, we need quite high temperatures. 150 to 350 degrees centigrade is really necessary for that. But there are many and wider distributed resources of geothermal energy in the world which are not suitable for electricity, but which are very suitable for these lower temperature applications. And as you see on this graph, those are in fact the largest requirements that we have for thermal energy in the world. So space heating, water heating, etc., residential heating, commercial applications, etc., all of those are quite often suitable for those low temperatures. So cities like Izmir in Turkey, as I'm sure you know, have widespread district heating systems with geothermally sourced thermal energy. And if we look at the worldwide community of thermal direct use application from geothermal, you can see it's actually expanding rather more rapidly than that for electricity. And if we count the thermal gigawatts, we are already up to more than 100 gigawatts thermal in our global geothermal direct use industry, and continuing to expand and expand at an increasing rate. And if we look at where direct use is actually used, you can see actually it is prominent in Europe, and it's also prominent in Asia, prominently in China, although not only there. But many countries that we would not normally associate with geothermal activity, like Germany and France and Sweden, have very dramatic applications of direct use geothermal resources. China also doesn't have very high temperature geothermal resources, but they have prominent use of heat pumps and low temperature resources across their country. So these are the leaders. China is actually number one. And you can see there, Turkey is number two if you don't include heat pumps. And other important countries, Iceland is important, and then Germany and Sweden if we include heat pumps, and the United States as well if we include heat pumps too. And if we look at the importance of the energy resource in terms of its relationship to the population. China and the United States, of course, both have quite large populations, but per person, the megawatts per individual in each of these countries, you can see is dominated by the Nordic countries, New Zealand being the only one in this list, which is not. So in Scandinavia, they have made very good use of geothermal resources for direct use in terms of their energy consumption or energy provision per person. And this is a slightly unusual diagram because it goes from right to left in terms of time. But you can see here the rate of expansion of the different applications of direct use geothermal. And number one on the left is heat pumps. And you can see here the inventories from the 5 World Geothermal Congresses, 95 through 2020. You can see how tremendously geothermal heat pumps has expanded during that time. But balneology has also expanded rather rapidly too. Space heating, not as rapidly, but steadily. Agriculture, greenhouse, aquaculture, a lower rate of expansion, but also still also steady expansion. Now let's talk a little bit about the characteristics of geothermal. I'm switching back momentarily here to talk about electricity, not just in terms of their impact of the energy, but also their carbon intensity and life cycle emissions. We don't generate any CO2 with PV panels or wind turbines. However, we actually have to manufacture them, we have to transport them, we have to construct them. So even wind and solar have life cycle CO2 emissions. It turns out actually that the 3 lowest life cycle emissions of carbon energy sources that we have, at least the major ones for electricity, are wind actually is the lowest, and nuclear and geothermal are number 2 and number 3. So there are CO2 emissions from geothermal. Any of you who have drunk Perrier water know that CO2 dissolves naturally in groundwater. So there is some CO2 which comes to the surface. And at least in plants other than binary geothermal plants, some of that may be released. But you can see from this graph, it's a small amount. It is, as I said, one of the lowest, and it's certainly fantastically lower than coal and other fossil fuels. Now, I'd like to talk for a few moments about geothermal in the context of a renewable portfolio that a nation or a state may have. So I want to show you a series of snapshots of the electricity grid in the state of California, where I am living, as well as in some cases the state of Nevada, which is our neighbor to the east. So the first picture I want to show you is in 2010, 10 years ago. And of the total electricity grid of the state of California, you can see here shown in yellow, 6% of the electricity generated in the state of California came from geothermal sources. And importantly, 6% also in Nevada as well. And at that time, excluding hydro, which by legislation in the United States at least is not counted as renewable, even though it is, geothermal was our largest source of renewable power in 2010, as it was in Nevada as well. Now, I do want to draw your attention to hydro actually here in California. We generate a lot of hydroelectric electricity, 33 gigawatt hours in 33,000 gigawatt hours in 2010. But if we move forward to 2013, looking first at hydro, you'll see that 3 years after 2010, we generated only 23,000 gigawatt hours. And the reason for that is we had a drought in California, as we're actually having right now, and the resources for hydro were actually seriously depleted. So everybody knows that wind and solar are intermittent. They go solar on and off every day, but hydro is kind of intermittent too, especially in places like California, where we have series of droughts that may last for 5 or 6 years, and our water resources may be significantly depleted. But in 2013, geothermal was still very high on our renewable portfolio. But I'm showing you 2013 because that was the first year that actually wind superseded geothermal in our yearly generation. In that year, solar was still quite low. Moving forward to 2015, look at hydro again. Hydro dropped now to 13,000 gigawatt hours. It went from 33 to 23 to 13 over that 5-year period because the drought continued. Geothermal still steadily producing 6% of our electricity in California. And then what you see in 2015, looking at solar, solar became number one, overtaking wind for the first time, as well as geothermal. So geothermal dropped from second place to third in our renewable portfolio mix. And then moving finally to 2017, which is the most recent figures that I have, you can see actually geothermal still 6% of our electricity generation in the state of California, completely reliable over that entire period. Hydro came swinging back all the way back to 43,000 gigawatt hours because the drought finished. We had a very high rainfall winter and hydro came back with its kind of 5-year-long intermittency. Solar up to 32,000 gigawatt hours, which then at that time made up 16% of our generation. Importantly, I want to draw your attention to our neighbor, Nevada, which in 2017 generated 9% of its electricity from geothermal sources. And Nevada is kind of important in a worldwide context because the geothermal resources of the state of Nevada are generally much lower temperature than they are in California. So for Nevada to succeed to achieve that expansion to 9% actually represents the development of newer and lower quality resources. And that's significant in the world context. And if we look at a day in the state of California, this is a 24-hour period, a year or two ago, you can see the understandable intermittency of solar and wind. Happily in California, the wind tends to blow more at night than in the daytime. So wind and solar kind of balance each other, although not always. And in spite of the fact that geothermal looks kind of boring and relatively low on this graph, geothermal is a steady and stable resource that actually provides an important resource for our state. And in some days, it's actually the largest cumulative production. And the reason that that's significant is that the inclusion of so much wind and solar into our portfolio produces very strong demands on the overall grid. So during the afternoon hours, again, this is a 24-hour period, the state of California actually has to add about 13 gigawatts of non-wind and solar generation in order to meet the peak demand in the later part of the afternoon. So dispatchable power, steady, reliable power is a good thing, but actually nowadays dispatchable power is more significant. So what we see in the state of California are several different kinds of storage projects. So we have several hundreds of megawatts of battery storage in our state, not used day and night, but largely used to regulate the grid as those conventional power plants, most of them gas-fired, actually need to be switched on to meet the demand as the solar fades away during the afternoon. So you can see on this particular day, a couple of years ago, how the batteries were used in the state of California that day. Sometimes charging, sometimes discharging, but not on a 24-hour basis, often on a 15-minute basis. We do have dispatchable power in geothermal as well. So this is a plant in Puna, Hawaii, which is, of course, an island grid. They can't easily export electricity from one island to the next, and therefore they actually have to dispatch their electricity. And because they have an important geothermal resource, this is a plant which is actually designed to be dispatchable, whereas most geothermal plants are designed to be base load. And another way in which dispatchability and flexibility can be introduced is by hybrids. So this is a hybrid plant in the state of Nevada, and this is a kind of a three-way hybrid. It's a geothermal plant, a solar PV plant, and a solar thermal plant, all in combination. The PVs and the geothermal part of the plant are actually thermodynamically separated. They're only connected electrically. But the solar thermal and the geothermal are actually part of the same cycle. So during the afternoon, when the air-cooled condensers are at their least efficient, actually the solar thermal can't, because the temperature is highest, actually tends to fill the gap. So this is a kind of innovation which we're beginning to see across the world in our geothermal community. This is a different kind of hybrid plant in New Zealand, which is a combined steam turbine, binary turbine at Rotokawa. So bringing this to something of a conclusion, over the last 15 years or so, there's been a tremendous expansion in geothermal activity in the world. A lot of new countries and new companies have joined the geothermal community. Importantly, as I mentioned, Turkey is the most important new development in the geothermal worldwide community. And it's not just traditional developments that we're seeing. We've seen new technologies like the hybrids I've shown you, the new strategies for deployment. Base load used to be our biggest advantage for geothermal. It's now perhaps one of our biggest disadvantages because it's harder to implement geothermal plants into high variable loads that include a lot of solar and PV. So dispatchable plants are our future in any kind of resource. And as I mentioned, in the state of Nevada, lower temperature resources, I'm talking about 140, 150 degrees centigrade, are being developed, have been developed to reach high levels of market impact. And that means that there are many places in the world in which electricity generation from geothermal is now very feasible. And I didn't talk about it today, but enhanced geothermal systems, which have been in development for quite a long time, are beginning to make inroads into commercial application, most prominently in Europe, but in other places as well. Not all countries and not all parts of every country enjoy the kind of volcanic abundance that we do in California and New Zealand and Iceland and Turkey and places like that. But a lot of places have sufficient temperature in their subsurface that if they can introduce permeability into the rocks by enhancing the geology in an enhanced geothermal system, we can have geothermal in a greatly increased space of the world than we do today. And as was mentioned as we began, I talked about the World Geothermal Congress. The World Geothermal Congress 2020 has been taking place since March of 2021. It was, of course, postponed by the pandemic. It's not yet finished. The actual in-person part of the World Geothermal Congress will take place in Iceland in October. There are actually close to 2,000 papers in that Congress, all of which you would probably find interesting. There are a significant number of them that will be presented either as speeches. A lot of them actually already been presented in virtual sessions, and all of them will be available publicly once the Congress concludes in October. So with that, I will conclude and I will invite your questions. Thank you.
Thank you very much, dear Dr. Roland. Really very important data you gave us. Thank you very much. I have one of the questions. First, especially, I would like to thank you for your give the detailed information about hybrid system. It's really nice. And then also it is important you mention about the climate change affected the energy system. And then we say that the California has a good example about this one, hydro and then the other energy. But what do you think about the energy geothermal system? How is it going to in the world? What's your projection? What's your suggestion about for future enhanced geothermal system?
Enhanced geothermal system. So enhanced geothermal system is not an easy concept, you know, because it is like a conventional geothermal system dependent on the geology. So geology, of course, varies a lot from one part of the world to the other. The largest limitation that we have on geothermal development by EGS is that we don't have an accumulation of experience yet. There are certainly quite many projects, there are actually more than 60 enhanced geothermal projects in the world historically. And that's a lot of good experience, but it isn't actually enough. If you look at how many hundreds of thousands of oil wells and oil reservoirs there are in the world, the development of the technology really requires time and experience. We're gaining that experience, and I'm confident that actually EGS will continue to expand as it has been. Again, let me say that once again, because a lot of people don't realize this. There are 61 enhanced geothermal projects that have been undertaken across the world. Some of them unsuccessful, some of them successful, but even the unsuccessful ones have taught us a lot about how to make them work. And there are quite a number of enhanced geothermal systems that are currently commercially operating in Europe and other places.
Thank you very much. I have a second question. Dr. Roland, at that time, some countries such as Turkey, we come across some social, they come across a negative effect, when the social people not happy. I just want to know that you have a very good expert about New Zealand. You have any suggestion, you have any recommendation, what we should do about this one? Because we want to improve the system, we want to, that use this energy type. What's your suggestion, please?
Yes, it's completely true. And it's true of many countries of the world as well. Geothermal is a kind of an industrial development. So you kind of put things on the countryside, which people previously, enjoyed the natural scenery. People are often worried about induced seismicity. That is a worry. And importantly, it's a real concern. Not as important as a lot of people imagine it to be, but nonetheless, it is something that people are worried about, and therefore that makes it something that the industry has to worry about. What I have seen in terms of success in engagement of social concerns, places like the Philippines, for example, where they may be building geothermal plants in quite rural communities where people lead peaceful lives and they don't like the idea of a lot of big equipment and machinery and roads and, industrial components coming into their life. The most important thing in this regard is engagement. Engaging with the community in advance, explaining to them how it works, what it means to them in terms of energy, in terms of jobs, in terms of opportunities, and to be honest with them. I mean, people actually are quite capable of understanding these things and making their own judgments. No community will be 100% happy to have geothermal developments close by, but if there is sufficient engagement with that community, they can have that discussion within themselves and decide, yes, there's pluses and there are minuses, but we decide as a community that we're going to accept and go ahead with this kind of development. Okay, dear Dr. Ronald, thank you very much for your important comment, suggestion, and accommodation. Thank you very much for attending this important Congress. I hope that in near future we can see you in Turkey also. Have a good time. Thank you again. Oh, I hope so too. Thank you very much. Thank you very much. Dear participants and dear distinguished
participant. The third keynote speaker is the Dr. Arumugan Mathiram. Professor Mathiram is the director of the Texas Material Institute and Material Science and Engineering program at the University of Texas at Austin. He received his PhD degree in the chemistry from Indian Institute of Technology at the Madras in 1981. After working as a postdoctoral research at the University of Oxford and then University of Texas, he became a faculty member in the Department of the Mechanical Engineer. Dr. Mathiram, his research is focused on rechargeable battery and fuel cells. This is very critical materials and very important at the time. Today, Dr. Mathiram give information about the sustainable battery chemistries for the e-mobility and renewable energy storage. You are welcome, Dr. Mathiram. Yes, please.
Thank you very much for the introduction. Can you hear me well?
Yes, I hear you well.
Okay, let me share the screen. Do you see the screen?
Yes, it's okay now.
Okay, it's not moving. Why? Let me hold on 1 second. Let me share again.
That's okay.
Okay, but when I hit the button, it doesn't move. So let me see. Okay. Is it okay now?
That's okay. Thank you. Yes, please.
Okay, let me move this. Thank you very much for the introduction. It's a pleasure to give this presentation. My talk is focused on sustainable battery chemistries for both electric vehicles as well as the grid storage of renewable energies. So the chart here gives us the energy use globally as we move forward. The energy use is skyrocketing. I also give the population here. The population of China and India are similar, and they are 4 times more than that in the US. US currently uses 17% of the total global energy use. And if China and India catch up with the US, we will need an order of magnitude higher energy than what we use now. So that's a challenge. The energy use largely now based on fossil fuels. That has 2 issues. One, can we have that for the next 100 years or 200 years? So limited supply. More importantly, they cause air pollution, health concerns, climate change, all those. So what is the solution? The solution is renewable energy, solar and wind, that is available in plenty, but they are intermittent. So storage is the bottleneck. So the option to store the electricity produced from renewable energy is battery technologies, but they don't come easy as well. They have their own challenges. The other aspect is transportation. We cannot use a lot of other forms of energy like solar or wind directly in vehicles. So transportation goes all over the place on the road. So it's not controlled, uncontrolled pollution. So batteries are the most viable technology for vehicles as well, transportation as well. So the audience may not be very familiar with how the battery works. So I'm giving here, let me see. Okay, I have to go back. Hold on 1 second. So I'm taking lithium-ion batteries as an example here and illustrate how it works. The battery will have an anode, negative electrode, and a cathode, positive electrode, separated by an electrolyte that should be electrically insulating. It should allow only the charge transfer in the form of ions, in this case lithium ions. It should not allow any electron to pass through. So during charge, the lithium ions move from the cathode to the anode, as you see now, and the electrons move from the cathode to the anode. That is, let me see this to come down. During charge, we take the electron from the cathode. Using electricity, we store in the anode at a higher energy state using the electricity with an outlet. During discharge, there is a spontaneous reaction because this electron here can fall spontaneously to the cathode, and then the free energy released during this process is taken out as electricity. So battery is an energy storage device. You store electricity in the form of chemical energy, and when you want it, you take out the chemical energy as electricity. It looks very simple, but the user time or energy density depends on two parameters: cell voltage times the amount of charge that can be stored, that can be stored in the form of lithium ions. If it is a sodium ion battery, the amount of charge that can be stored in the form of sodium ions. The amount of charge that can be stored depends upon the number of crystallographic sites available per unit volume or per unit weight. Voltage depends upon the difference between the redox energies of the anode and the cathode. So that means this has to lie as low as possible, the cathode, and the anode has to lie as high as possible. But there is a constraint. They are in contact with the electrolyte. The electrolyte has its own energy levels. The highest occupied molecular orbital, that has electrons, and the lowest unoccupied molecular orbital. If not, if the cathode energy is below the HOMO of the electrolyte, during charge, instead of pulling the electron from the cathode, we will be pulling the electron from the electrolyte, so electrolyte will undergo oxidation. The same way, if the LUMO is below the redox energy of the anode, somewhere here, during charge, the electron will be put into the LUMO of the electrolyte rather than into the anode. Again, the electrolyte will undergo reduction. The electrolyte should not undergo any reduction or oxidation. You should allow charge transfer only in the form of ion, just a medium to transfer the charge when the electron is flowing through the external circuit. Now, there are a lot of batteries. We still use lead acid batteries in the car. There is nickel cadmium, nickel metal hydride, not too much these days, getting replaced by lithium ion. But lithium ions give much higher energy density per unit weight or unit volume, because lithium ions can give 4 volt per cell, since it uses a non-aqueous electrolyte, water-free electrolyte. All other batteries you see here, they all use water-based electrolyte, so they cannot give more than 2 volt. So when we go from this to lithium ion, we double the voltage. That's why lithium ions give longer user time with the same weight or same size. Why? In the case of other cells with water-based electrolyte, sulfuric acid or potassium hydroxide, this band gap is smaller. So the difference between anode and cathode is shorter or smaller. So voltage is less than 2 volt. With non-aqueous electrolyte, this gap is widened. So we can keep the anode energy as high as possible, cathode as low as possible. So we get 4 volts. So that is the basic principle. Now, how did this all happen? It does not happen overnight. The concept of rechargeable batteries was first demonstrated by Professor Stanley Whittingham at Exxon Corporation in the United States in 1976. He demonstrated the concept with a lithium metal anode and a titanium sulfide cathode that has a layered structure. But it has 2 issues. One, with a sulfide cathode, the sulfur 3p band is at a higher energy. So we cannot lower the cathode energy below the top of the sulfur 3p band. So the voltage is limited to less than 2.5 volt or at the most less than 2 volt. Because titanium sulfide does not have any lithium, one has to use lithium metal anode that has its own safety problem. So cells were put into the market, but then they were recalled towards the end of 80s. Professor Goodenough, he started his career in 1950s, and he was familiar with all the oxides. Oh, okay, I can increase the voltage by going from a sulfide to an oxide because oxygen 2p band lies at a lower energy than sulfur 3p band. Very simple. It may look now, but he was the first one to do that. So with an oxide, you can lower the cathode energy very much down. So now the voltage is from here to there. So you can get 4 volt instead of less than 2.5 volt. So that's where energy density is increased. Then finally, Akira Yoshino, he put together the lithium cobalt oxide cathode and the carbon SS anode and demonstrated the lithium ion battery concept. So this is how lithium ion batteries came into picture. And for that, they were given the 2019 Nobel Prize in Chemistry. Now, looks simple, but there are several parameters, at least 6 major parameters we have to worry about with the battery technology. How much energy I can store in a given volume or weight, how fast I can charge, discharge, what kind of cycle life it will have, what kind of safety, what are the environmental consequences of the materials and the processes we use, and overall, what is the raw material cost, and cost is actually everything. With the power, fast charge with acceptable safety, as well as can the cell operate at lower temperatures when it is cold in some cold regions of the world, countries, or at higher temperatures. So which parameter I pay more attention or which battery technology I choose depends upon the application. Cell phone, laptop, energy density, user time is more important. So we pay attention to that. Electric vehicle, energy density is still important. I want to drive as long as possible before I have to charge, but it is a slightly larger battery. Cost comes into picture. Safety also comes into picture because it's on the road. You don't want to cause problems to the other cars or others on the road. Grid storage, it's going to be huge battery, more expensive. Cost is the most important driver. And you also don't want to replace the battery every 4 years, like you do, you throw your cell phone or laptop. You want that to be used 10, 20 years. Life is important. Of course, safety is also important. Big one, it is on the ground. So you see the criteria changes. That means it is not one battery technology. We may be used for all these applications across the board. There are a lot of rooms to find new battery chemistries. Now, all these parameters we are talking about, they are linked to severe material challenges. What is the structure? Where the redox energies are? What is the diffusion? What kind of diffusion they will have? How they react? Are they stable, reversible? All kinds of things. So from a materials point of view, what are all the things that are linked to these parameters? Energy density is determined by voltage and degree of ion insertion, which I have already talked about. The redox potentials are available as a guide in any textbook, inorganic chemistry textbook. Power density, that is charging time, low temperature performance, depends upon the electronic and ionic conductivity of the 2 electrodes, as well as the ionic conductivity of the electrolyte. Cycle life depends on how reversible we can do this, what is the stability of the cathode and anode, and what is the interfacial stability of the 2 electrodes in contact with the electrolyte. Thermal stability or fire hazard or safety depends upon, are we going to have dendrites on the anode? Is the cathode going to release oxygen and speed up the fire? Is the electrolyte going to be flammable? All those determine. Environmental impact or toxicity, what kind of material we use, what kind of process we use. Cost is everything. Energy is cost. If I store more energy, I have to make only 20 cells instead of 50 cells. I save money. If I use for 10 years, 20 years, I do not have to replace it. So that is cost. So materials and all of the above contribute to cost. Now, lithium ions are not the end of the world. There are a lot of other technologies I list here to have an idea. But right now, there is nothing to beat lithium ion. They are based on insertion compound cathodes and anodes. But there is a lot of interest to use conversion reaction anodes like silicon and others. A lot of research is going on. Sodium ion, analogous to lithium ion, but sodium ion brings a big cost advantage as well as supply chain advantage because it's available plenty everywhere. But they will always give a little bit less energy density than lithium ion batteries. Multivalent ion batteries instead of lithium or sodium, magnesium ion, zinc ion, aluminum ion. Interesting because if I store one ion, I store 2 charges with magnesium or 3 charges with aluminum. That's the interest. But these cells will have lower voltage than these cells. And also, it's very hard for a 2+ ion or a 3+ ion to diffuse through the lattice. So your reaction kinetics is limited. And there are not good electrolytes as well for these batteries. Many challenges. My own personal feeling, at the end of the day, we may not be able to get higher energy density with these than with lithium ion. Metal sulfur, all of the above I talked about, they use metal ion based cathodes, lithium cobalt oxide, lithium iron oxide. Metal sulfur means the cathode is sulfur. Available plenty. A byproduct waste in petrochemical industry, oil industry. So you can make use of it. That can be done with any of these above ions I talked about. But so cost is lower, abundant, sustainable, but sulfur is a bad insulator and poor lithium ion conductor. Also, when you discharge, it forms something called polysulfide. It goes from one electrode to another electrode, messing around. If you use multivalent ion, the same problem I talked about here, you have kinetic limitations. Metal air batteries, a lot of work happened during the past decade or more. Non-aqueous systems very difficult because oxygen reduction reaction needs a catalyst. Oxygen evolution reaction needs a catalyst. That catalyst may oxidize the electrolyte. So that's very hard. But aqueous systems are potential for grid storage. Redox flow batteries. So far here, I talked about liquid electrolyte and solid electrodes. Redox flow batteries, you have liquid electrodes, a solution you are flowing through, so you can store a lot of energy in a tank. So that is, so all these, wherever I say grid, they are mainly applicable for grid. The other technologies, grid as well as electric vehicle. All solid state batteries, that is the holy grail of the battery technology. It can give better safety because there is no flammable liquid electrolyte. If you make it right, it can also give higher energy density, but they suffer from sluggish interfacial charge transfer. Why? You can imagine if you bring 2 solids together, how are you going to transfer the ions from one solid to the other solid? If you have one solid and a liquid, it can very well wet the surface. So the charge transfer between a liquid and a solid is easier. So that's the biggest challenge. With a ceramic electrolyte and a ceramic cathode, it's very hard to have good charge transfer. If you have a polymer flexible electrolyte, then it can work, but unfortunately, we do not have one now. The other question is, if you have a ceramic electrolyte, how are you going to manufacture large area, roll to roll manufacturing of the ceramic solid electrolyte? Can you do it like a polymer? The answer is no, hard, difficult. So these are all the challenges. Very appealing, lot of research going on, but very, very challenging, lot of issues needs to be tackled. With that, what is going on right now? Right now, the one I talked about here, lithium-ion technology, the graphite anode, that voltage is lower here. And one of these cathodes, a layered oxide or a spinel oxide or a polyanion oxide, all of them are oxides. If you couple any of these with graphite anode, then you can have a battery of 3.5 volt to 4 volt or 4.2 volt like that. So that is the technology currently available. The x-axis gives the charge storage capacity in this material, few hundreds at the most, 100, 200 like that. Lot of interest to replace these cathodes with oxygen or sulfur. You see here, there's a break in the scale. These are thousands, order of magnitude, higher charge storage capacity than any of these, but they have a lot of problems, as I mentioned earlier. Same way, alloy anodes, instead of graphite, we have silicon or tin, they have an order of magnitude higher charge storage capacity, but these are all at the research now, not commercially used. At the most, little bit of silicon added to graphite, less than 10%. That's what is going on now. The whole technology became feasible because of the oxide cathodes giving higher voltage than sulfide or selenide cathodes. And all the three were developed by Professor John Goodenough's group, both at the University of Oxford and at the University of Texas at Austin, involving 3 visiting scientists or postdoctoral fellows from 3 different parts of the world, all in the 1980s. These are the only 3 concepts, 3 systems practically used even now, 40 years later, but they are all done in the 1980s. First, Mishishima came from Japan, worked with Professor Goodenough. They did lithium cobalt oxide and lithium nickel oxide, layered oxide. He left. Michael Thackeray came from South Africa. He did spinel, manganese, lower cost than that. He left. I came after doing my PhD from India to Oxford. I started working with him as a postdoc. We were the 3 of us were fortunate to work with him, coming from 3 different countries. So both of them were not there. They already left. When I came, I worked on, instead of a simple oxide like this, a polyanion, meaning sulfate here, phosphate here, or silicate here. That is called polyanion rather than a simple oxide anion. When we do this, the voltage goes up. For example, sulfate to oxide, the voltage goes up. I already explained. When you go with the same oxidation state, when you go from a simple oxide to a polyanion oxide, sulfate or phosphate or silicate, the voltage again increases by more than 1 volt. So it's all voltage business. That's how we get longer user time or energy density. You can imagine, now we talk about a lot about sustainability. The 3 are the ones practically used or possible. You see, cobalt most expensive, manganese a little bit less expensive, iron is the least expensive. Cost reduction as well as safety. When you go from here to here, the safety increases enormously. Now, the vision in my group, sustainability, more important. So now, cobalt is most expensive. There are a lot of supply chain issues, child labor in mining. So eliminate cobalt, which we have successfully done last year. Next, throw away all transition metal oxide cathodes, use sulfur. Next, throw away lithium, use sodium. Lithium can also become a problem. Finally, have sodium and sulfur, that's no lithium involved, no metal ion involved other than sodium, which is available plenty, or even sodium organic. This is kind of the path we are focusing on in my research group. And we are already successful to do this. Cobalt is eliminated. We can have cobalt-free lithium-ion batteries. Now, right now, the whole industry is based on something called NMC cathode, where M is nickel, manganese, cobalt. That's why NMC. And they have a layered structure. The question is, why do we have 3 metal ions rather than 1? It's always complicated to mix three and heat and react. The reason is two major factors. First, the relative positions of these redox energies with respect to the top of the oxygen 2p band. As you see here, the cobalt 3+, 4+ redox energy overlaps with the top of the oxygen 2p band. So when we charge more than 50%, meaning when we pull out more than 50% lithium from this during charge, we will be pulling out electron density from the oxide band as well, or you are introducing holes into the oxygen band. There may be physics people sitting here. So you are oxidizing oxide ion to peroxide and oxygen gas, so it will have chemical instability. If you look at manganese, 3+, 4+ band lies well above the top of the oxygen 2p band. So that does not undergo this kind of problem, very much stable. So chemical stability wise, manganese is the best, cobalt is the worst. The other factor is structural stability. When we charge, we create a lot of lithium vacancies here. Positive charge is removed. So if possible, the transition material cobalt, nickel or manganese will tend to fall from this layer, from this octahedral 6-fold coordinated site through a neighboring tetrahedral site to the octahedral site, empty octahedral site in the lithium layer. Because chemical imbalance, you can't have a lot of positive charge in one layer. The other layer is almost getting empty because you have removed a lot of lithium and you have a lot of oxygen 2-2-. They are seeing directly each other. So system is having a problem. So these guys will tend to fall from this 6-fold coordinated site to that 4-fold coordinated tetrahedral site to this. Some will fall, some will not fall. So what is that? You can use basic inorganic chemistry with a calculator in 5 minutes. The octahedral crystal field stabilization energy for each of these ions. You can also calculate the tetrahedral crystal field stabilization energy, because in octahedral, tetrahedral, the d orbital will split like this due to the ligand field or negative electric field introduced by the oxide ions. So I don't want to go through all those, but basic, simple inorganic chemistry. I don't think they teach in a high school, but undergraduates, they will be teaching. So if you take the difference between the two, it will tell you to what extent these ions are stable in the octahedral site or low octahedral site. You see cobalt 3+, all the 6 electrons are in the low-lying T2G band, very stable. Cobalt hates to move from this site to a neighboring tetrahedral site because it loves octahedral site. It hates tetrahedral site, so that doesn't happen. That is a gift. Good structural stability cobalt has. Manganese, very small difference. It easily migrates from this layer through a neighboring tetrahedral site to this. So if 25% migrates, then the structure transforms from a layered structure to something called the spinel structure. And that causes voltage drop, all kinds of problems. So structural stability, cobalt is good, manganese is bad. You see here, these are the two important parameters. Too bad, cobalt is good for one thing, manganese is good for another thing. My gosh, why can't we get both in the same? We don't. There is no way to get around this. Nature has all the electronic configuration. What they do depends on the intrinsic properties or characteristics of different ions. There are other issues I will also do here. I think I already mentioned cobalt is becoming metallically conductive, manganese is abundant, manganese low cost, environmentally benign, all this. But these are the two important factors. Interestingly, in all these parameters, nickel is in between manganese and cobalt. The nickel band also barely touches the top of the oxygen 2p band. Therefore, we can charge the nickel containing cathode to a greater extent. So nickel can give more energy density than cobalt. Nickel is lower cost than cobalt. That's why all the action in the industry is to increase the nickel content in these materials. Keep on increasing nickel content in the material. When you do that, you get higher capacity, of course, lower cost, of course. Nickel is way right in the periodic table. Nickel oxygen bond is more covalent. So electronic conductivity is not very much compromised. It's wonderful. But it has three problems. Cycle instability, thermal instability, air instability. What does that mean, air instability? You cook the material, keep it in the air, tons and tons of material. If you store in the air, it will form lithium hydroxide, lithium carbonate on the surface. That is called residual lithium. It will clog the electrode making process. It will degrade the performance. It's a big headache. So these issues are involving the bulk of the material, the surface of the material, and how the surface of the electrode and the electrolyte interact with each other. Complicated. Slowly, incrementally progress is being made. The commercialization began in 1991 by Sony with the pure lithium cobalt oxide because cobalt has good structural stability. After that, for the past 30 years, slowly reducing the cobalt and increasing the nickel. That is what is happening in the industry. Remember, it is 30 years and we have not completely accomplished using pure nickel yet. We have almost 80% nickel. Now, in my lab, we make good quality material. That's the first step. We can use a tank reactor controlling pH, temperature, pumping rate. We can get consistently 10 kilogram per batch of these hydroxide precursors of the transition metal or other metal ions we use. Then we mix that with lithium hydroxide, heat it at appropriate temperature to get any of those compositions. You see here when the nickel content increases from here to here, capacity increases. That's why everybody is interested to go to higher and higher nickel. But you see here as we cycle, the capacity is fading, cycle life problem. So we can make good material. We also make pouch cells, full cell to demonstrate the viability. And we have good analytical capability at the University of Texas at Austin to know what is really happening during charge-discharge, degradation mechanism. With those, we have made a lot of headways. So I'm comparing here two materials. One with 80% nickel, another one with 94% nickel, only a little bit more. You see here the material with 80% nickel cycles better, the green one. The material with 94% nickel fades, capacity fades. That means your user time between charges keep on decreasing. You have done it for 1,500 cycles with full cell. So what is really causing the capacity fade? The more capacity you try to get, you have weak lattice changes, lattice parameter changes that can introduce crack. You can see the two materials, the 80% nickel and 94% nickel after 1,500 cycle. If you look at the particle, you see more cracks here than there. The crack by itself is not a big problem for the cathode, but the cracks create new surface, and that surface can react with liquid electrolyte to form something called cathode electrolyte interface layer that will consume the active lithium ions. So that's the problem. So how do we know that? I'm again comparing here both the materials after 1,500 cycles with time of flight secondary ion mass spectrometry. That can depends upon the mass to charge ratio. So you can detect different species. You see here, whenever you see the red, that means you are seeing the graphite. Before that, you have something called the solid electrolyte interface layer. By the way, this is not the cathode. The cell is made with this cathode or that cathode with graphite anode. We take the graphite anode from both the cells and then we analyze. The graphite that was paired with this 80% nickel has the solid electrolyte interface about say 75 to 100 nanometer. The one graphite that was paired with the 94% material has, like, say, 150 or 200 nanometer solid electrolyte interface layer thickness. Also, that higher nickel material has more nickel migrated from the cathode through the separator to the graphite anode. This has less. So meaning, when you go to higher nickel content, more metal ions are dissolving, going from the cathode to the anode. It deposits on the anode, decomposes the electrolyte catalytically, and that causes problem to anode performance, and it also traps active lithium. So that's all with respect to cyclability. What is causing the cyclability problem? Safety problem. 111 means 33% nickel. This is 90% nickel. This is 100% nickel. As the nickel content increases, the thermal stability is decreasing. So safety becomes an issue. The third aspect is air stability. So you make the material with the different lithium nickel content. As you go from 33% nickel to 100% nickel, the amount of lithium hydroxide and lithium carbonate on the surface is exponentially increasing, not linear. This is very stable. If you keep it in air, this forms a lot of surface lithium hydroxide, lithium carbonate, because lithium moves from the bulk structure to the surface to form that. That will cause clogging problem when you make electrode, big headache. These residual lithium have to be less than 2000 parts per million. Otherwise, Samsung or LG or any big companies, they will have a problem to make electrode, or even in my own lab. Why it happens? You see here, manganese, we have all kinds of oxide, M1O, M3O4, M2O3, M1O2, all stable, no problem. Cobalt, we have COO, CO3O4, CO2O3, no problem. Nickel, only NiO. There is no Ni3O4 or Ni2O3 or NiO2. It also already tells you nickel 3+ is unstable. That's why lithium nickel oxide has nickel 3+. It reacts very easily with air. A lot of good things with the nickel, but there are these problems. Okay, nice. We understand all these problems, 3 problems. Cycle instability, thermal instability, and air instability. It's good always to tell problem, but how do we solve it? So that problematic material, 94% nickel, now we are putting 2% aluminum per nickel. That is the red curve. You see, only 2% aluminum, you can turn around the capacity retention as well as the voltage stability. Why? We have again analyzed the graphite that was paired with this material and this material in the cell. If you do that, the graphite that was paired with the undoped material has more nickel on the graphite and more lithium trapped on the graphite anode than the material that was, than the graphite that was paired with this. Or in other words, adding aluminum, only 1 or 2% decreases metal dissolution from the cathode and its migration to the anode and damaging the anode. That is suppressed. I see so few other things comparing all the 3. I mentioned all the 3 problems. So doping helps cyclability, better cyclability. Doping also helps to improve the thermal stability. The temperature increases, stability increases. This is after storing 14 days or 30 days. The undoped material without aluminum degrades fast after the storage. The 2% aluminum material stays better without too much degradation. So it's amazing. In my experience, 40 years of experience, whenever you try to do something to solve one problem, you will create another problem or you will magnify another problem. Here, fortunately, when you dope, you are gaining or you are minimizing all the 3 problems: cyclability problem, thermal stability problem, and the air stability problem. Amazing. Now, what is really happening? Can we understand what does that aluminum or magnesium doping or any other doping do? We have all these bands close to each other. Some of them are touching, some of them are not touching, but they are very close to each other. So charge can easily, electron can easily hop from one to another, and they have layered structure. So all these metal ions are here. They may be nickel or manganese or cobalt. They can transfer very easily, meaning the electrons are very much delocalized. They have good mobility, highly covalent. As soon as you put aluminum into this, that acts like a speed breaker. It introduces electron localization because the electron cannot hop from here to here. So that's a speed breaker. That means the lattice becomes more robust. So highly covalent, when you have good electron mobility and oxygen mobility, the metal oxygen bond breaking is easy. That breaks, that's why things dissolve. As soon as you put a little bit of aluminum, you make the lattice more robust. It reduces oxygen electron mobility. It introduces something called Anderson localization. The physics community is familiar. So that suppresses metal oxygen bond breaking. So metal dissolution suppressed. That's why we get better or lower dissolution and better cyclability. Now, good, nice. Would all metal ions dissolve? The answer is no. What is causing really the dissolution? Anytime you have an ion in which if you have an odd number of electrons in the EG band, that will undergo something called Untitled distortion. Again, the chemistry and physics community is familiar. Why Untitled distortion? If it distorts from cubic symmetry to tetragonal symmetry, the electron will be occupying a lower lying z-squared, for example. So energy is lower, so they will spontaneously tend to do that. So whenever you have an odd number of electron, manganese 3+, high spin iron 4+, or low spin nickel 3+, you have an odd number of electron, they will have lattice instability. They may tend to charge ordering of Mn2+ and Mn4+, for example. That can be protonated by trace amount of proton present in the electrolyte. That will lead to dissolution. So cobalt 3+, all electrons in the T2G, no Untitled distortion, no lattice instability. That's why cobalt is perfect, but we cannot get more than 50% capacity. So we can understand all these from the basic inorganic chemistry. Now, in the battery community, 50% of the cost comes from the cathode. That's the most expensive. And cobalt is the most expensive in the cathode. So that's why cobalt needs to be thrown away. So we have successfully eliminated cobalt. The NMA here, there is no cobalt. The C, whenever you see here, they have 5% cobalt. You see NMA, 90% nickel, 5% manganese, 5% aluminum is as good as or better than some of the cobalt containing material. The thermal stability is also good. We are also not compromising the charge discharge rates. Wonderful. So cobalt is no longer needed. We can throw away. We can have cobalt free. More expensive cobalt is eliminated. Cobalt free batteries. I said sustainable. Cobalt is removed. The next is lithium removal, sodium ion batteries. The cathodes are, layered cathodes are similar to the lithium ion cathodes, but sodium likes both octahedral and prismatic coordination. So they undergo more phase transformations, more cracks and things like that. The electrolyte instability. So this is very early stages sodium ion batteries, but a lot of work is going on. Also, sodium cannot use graphite because sodium does not insert into graphite. So we have to use hard carbon. That has its own some problems as well. So that's the second sustainable technology. The third one is sulfur. I love a couple of slides. Sulfur is abundant. You see here, you can get an order of magnitude higher charge storage capacity. It's environmentally benign, but it has three problems. One, sulfur, poor electronic ionic conductivity, so you cannot utilize all the sulfur, low capacity, practical capacity, low capacity. The sulfur has 8-membered ring. During operation, the rings break, so you get these linear polysulfides. They dissolve in the liquid electrolyte, move from the cathode to the anode, messing around the anode. So that causes a lot of poor cyclability as well as self-discharge. Finally, sulfur does not contain any lithium. Therefore, we have to use lithium metal, and then lithium metal has its own plating and stripping problems. So that is actually the major issue. Right now, a lot of progress has been made. So what the literature does mostly a lot of work, throw a lot of liquid electrolyte so that these polysulfides will move, that can overcome the lithium ion diffusion problem, and add a lot of conductive carbon that can overcome the electronic conductivity problem. But that will pathetically reduce the practical energy density because you have unwanted lot of electrolyte, lot of carbon. That's not good. So we have been focusing on these kind of parameters, 5 5s. The loading has to be greater than 5 milligram per centimeter squared, sulfur loading. The carbon content has to be less than 5%, and the electrolyte to sulfur ratio has to be less than 5 milliliter per gram. And the amount of lithium we take on the anode has to be very little or no lithiums. And also, a lot of work is on little button cell. That doesn't tell too much. So we are making pouch cells to demonstrate. So I'll quickly show some results. So we have used something called an anode-free cell, where you take Li2S cathode instead of sulfur. On the anode side, you don't have any free lithium at all. You charge this, you plate lithium, you strip, you plate, you strip. That eliminates the handling problems with lithium foil, as well as maximizes the energy density. Also, these cells in assembled state will not have any self-discharge, and we have also done some work to reduce the polysulfide diffusion and damaging the anode. You see here, if you do the things right, you can get better cyclability than the ones without unstabilized lithium deposition and plating and stripping. So what is really causing the problem? Lithium degradation. It turns out the lithium sulfur cells will need some lithium nitrate. So that lithium nitrate is oxidizing whatever polysulfide migrating from the cathode to the anode to some oxidized species. We have done this with time applied secondary and mass spectroscopy and XPS. We can see more species are converted from the sulfide to oxidized species. As you see here, by the time you go to 300 cycles, you do not have any sulfide at all. Everything is oxidized. So that is the source of the problem. So what do we do? Tellurium is in the same group as sulfur. So if you add 10% tellurium, for example, you can suppress that kind of oxidation of sulfide species to sulfate species. So your cyclability is turned around much better compared to without the tellurium. So what does tellurium really do? Tellurium substitutes into the polysulfides to form polytellurosulfides, which migrate to the lithium anode, get reduced to form Li2, TeS3 on the lithium metal anode as a stable solid electrolyte interface layer. So that stabilizes the lithium deposition. That's why we get better cyclability. Final fourth one, only one slide. Sodium sulfide. Sulfur is my dream technology. Not much done. The electrolyte is a major problem. I can't tell all the details now. With proper electrolyte, we have been able to turn it around. So I think it has good future. With that, this is the roadmap, I think. Right now, lithium-ion cells are 240 watt-hour per kilogram. If we increase the nickel content, it can go to 300 watt-hour per kilogram. If we replace graphite anode with lithium metal, that can go to 400 or 450 watt-hour per kilogram. If you throw away all these oxide cathodes with sulfur, that can potentially go to 500 watt-hour per kilogram. If you replace lithium by sodium, all of these numbers will be maybe 50 to 100 watt-hour per kilogram less. So that's what I have done here. If you go to sodium sulfur, again 400 to 450. All solid state potentially could do 500 watt-hour per kilogram, but a lot of challenges. Finally, I would like to thank all the students and postdocs who have worked with me over the years. So far, 270 people, including undergraduates. And I'm very grateful to all of them. This is my current group. And also the funding agencies, the Department of Energy particularly, as well as some of the industries you see here. I'm very grateful to them. Thank you very much. I'll be happy to answer questions.
Thank you very much, dear Matiram. It's really very interesting topics. You know, I learned many things. Thank you very much.
Thank you.
And then you give all the very good suggestions also. I have one of the question. Also, one of the colleagues want to ask a question directly to you.
Okay.
You mentioned your test, but Dr. Dinçer, the question is said that you have stated that nothing can be beat.
You have stated that nothing can beat lithium-ion batteries. We really need something else beyond this. Which one do you think will potentially make it next to?
Yes.
Okay. Question. What I meant was, there is nothing to beat lithium-ion at the moment. That's what my slide said. Nothing to beat now. But the whole concept was demonstrated in 1976. 1980s, 4-volt cathodes become possible. We are 40 years later. All the things which have happened so far during the past 40-45 years is incremental. The same cathode, nothing changed. The same anode, nothing changed. Engineering improvements, that's what is happening. So it will take time. Sodium ion, lot of work is going on. There is a potential possibility sodium ions can come into picture. But right now, cobalt can be eliminated. That is one step forward. Maybe I will go, let me, I don't know. Okay. I showed earlier, that is a good slide. Okay, sustainability. You see here, this is where we are current now, rightly here. Cobalt free, cobalt eliminated. Can we eliminate all these oxide cathode with sulfur? Lithium sulfur is potentially a possibility, lot of challenges. So right now, nothing to beat lithium ion, but it is possible. Lithium sulfur to come into picture, it is possible. Cobalt free sodium ion batteries come into picture, and eventually sodium sulfur. This is kind of the incremental pathway to achieve the goal. So I'm not saying you have to use lithium ion forever. I don't say that. Right now, nothing to beat. That's all I meant.
Yeah, thank you. Thank you very much. Thank you very much for the detailed explanation. Yes, dear Yıldız Bayazıtoğlu, you can ask your question, but you are mute, please. Please unmute, please.
Whoever wants to ask the question, you are muted. Looks like we can't hear anything.
Yeah, I think she is unmute now. Okay. She said that thank you very much for your nice presentation.
Okay, thank you very much.
Any question, please? We have a few times. Okay, no question, dear Dr. Matiram. Thank you very much for excellent explanation. Thank you. Attend our important congress. I hope that in future we can see also in the Turkey face-to-face. I believe that many people will see our YouTubes, they know that all our presentation, they maybe ask you question later. Thank you again. Thank you very much for your effort, time, and then energy. Really great. Thank you very much, organizing committee. Thank you very much, all the keynote speaker. Dear participant, now I'm going to close the session. I would like to again thank to the organizing committee of the Turkish Academy of Science. Energy is very critical, especially today we mentioned about the different type of energy, geothermal energy, lithium storage, that grid system. All of them is very important on the world. We believe that the energy will do new energy and then storage capacity, that lithium battery system will be changed in the futures. Maybe, but I hope that in near future, we can solve all the energy of the world. Okay, thank you very much. This is the important meeting. Have a good time. Have a good health. See you.
Thank you very much. Have a good time.
Bye-bye.
Bye.